Hey guys, welcome back. Good morning everyone. I hope all of you are doing great, having the good time. So dear students, quickly let me know in the chats if all of you can see me, if I'm perfectly audible and visible to everyone. Welcome back all my lovely students, welcome back. Quickly give me some green signal from the chats. Give me some fire symbols from the chats if all of you can hear me, if I am perfectly audible and visible to everyone. Quickly, everyone in the chats, yes. Am I perfectly audible, visible? All cool? All cool guys? So there was a delay for like 10 minutes. I'm really sorry about that because of some technical issues. I hope everything is sorted now and all of you can properly hear me and see me. Yes, perfect. Guys, the chat should be continuously running. And I can see like more than 800 people watching live and the likes are only few. That's not done. You have to take the likes count to 800 to 900. Quickly, everyone. And call up all your friends so that we can start directly without wasting a lot of our time. Take the live count right now to 800. And call up all your friends quickly so that we can start the session without wasting a lot of our time. Yes, it's going to be the class 11th chemistry marathon today, right? It is going to be class 11th chemistry marathon, yes, absolutely. Call up everyone quickly, call up everyone. Call up everyone, yes. Of course, today after the session, you'll be getting the notes in the Telegram group. For sure, you'll get the notes. Do not worry. Everything will be done. Everything will be taken care of. And guys, this session will be for 10 to 12 hours. Okay, I hope you know that. This session will be for 10 to 12 hours. So are you guys ready to be with me for like 10 to 12 hours? Yeah? Are you guys ready to be with me for like 10 to 12 hours? Quickly. Let me know. Alright, people are asking about the inorganic marathon also. Inorganic marathon will be also happening, right? Let's first complete the chapters which I have come up with. And just tell me, which chapter do you want me to start with? I told you I'll be starting with like chemical equilibrium. So are you guys ready for that? Should we start with chemical equilibrium? Should we start with the chemical equilibrium, everyone? Majority wins. Yes or no in the chats? Should we start with chemical equilibrium? Majority wins. All right, wonderful. Perfect, guys. Let's get going then. Let's get started, yeah? Let's get started with the chemical equilibrium chapter. Whatever things I'm going to tell you in the session, every single thing is going to be very, very important. So please have an eye on everything, okay? Just a second. Just a second, guys. There are basically a lot of slides in the today's session, so it is hanging a bit. Yeah, now it's fine. Just perfect. Perfect, guys. So let's start with the first chapter today. That is our chemical equilibrium chapter, okay? Chemical equilibrium. So first of all, let me quickly tell you, we have to deal this equilibrium today, right? We have to deal with this particular equilibrium chapter, which is considered as one of the toughest chapter of your physical chemistry. Okay, and I'll be starting from the basics only, but I'll be a little quick. Okay, so please and please follow properly with me. So what is equilibrium in chemical reactions? How do you define the equilibrium? Equilibrium is basically defined as it is a state. It is a state of a system. It is a state of a system at which entropy of the system is maximum and Gibbs free energy of the system is minimum. This is the thermodynamic definition of the term equilibrium. Equilibrium is just a state of the system at which entropy attains its maximum value, Gibbs free energy attains its minimum value. And as per your thermodynamics is concerned, any such state at which entropy becomes maximum, Gibbs free energy becomes minimum, that state is considered to be the most stable state of the system. So if I talk about equilibrium in particular, equilibrium is considered to be the most stable state of the system. It is considered to be the most stable state of the system. Why? Because as per thermodynamics, that state of the system at which entropy is maximum, Gibbs free energy is minimum, we call that particular state as the most stable state. Point number one. Point number two. Since we have to deal with the chemical reactions basically today, we have to deal with the chemical reactions. And how do you define equilibrium in the reactions basically? Let me tell you that as well. Equilibrium is that state of the system. Equilibrium is that state of the system at which all the measurable properties, what are the measurable properties? Measurable properties are your moles, measurable property is pressure, measurable property is concentration, etc. Equilibrium is basically that state of the system at which all the measurable properties like moles, pressure, concentration becomes constant. This is one important statement here which you need to understand. So understand properly now what I'm going to say. Just a second. Now understand properly what I'm going to say. See, when we say in a chemical reaction equilibrium has established, what does that mean? That means in the reaction, the moles of reactants and products, they have attained a fixed value. They are now not going to change at all. Concentration of reactants and products, they have attained a fixed value. They are not going to change at all. Pressure of reactants and products, it's not going to change at all. When equilibrium is established in the reaction, all the measurable properties like your moles, like your pressure, like your concentration, right? It attains all the things, they attain the fixed value. They are not going to change at all. This is one very important statement which I would want you guys to remember from now onwards. And at the same time, my dear students, at the same time, when we talk about the chemical reactions, we say at equilibrium, rate with which the forward reaction goes will be equal to the rate with which the backward reaction goes. This is one more important statement. At equilibrium, you'll always see rate of forward and rate of backward reaction becoming equal. Okay? Now, dear students, let's have a graphical overview of the term equilibrium first. Let's see graphically how equilibrium is defined, and there is a graphical question that can be asked from here. Okay? There is a graphical question that can be asked from here. So let me make you understand the equilibrium with the help of certain graphs, okay? So for example, I'm taking a simple reaction. Let's say A gives B. This is a reaction which I have, okay? A gives B. I'm assuming this particular reaction will be happening in a container. This particular reaction is taking place in a container whose volume is, for example, V liters. Let's assume that. Now, dear students, let's say initially at time t is equal to 0, I have got some 10 moles of this reactant. So this will be 0 because the reaction has not started yet. Okay. I am assuming the reaction to be reversible. I'm assuming this reaction to be, happening in both the ways, forward as well as backward. Now, as you can categorically see, I have taken 10 moles of reactant initially. Right now, the reaction has not started. Now, what is going to happen? The forward reaction will start first. If the forward reaction will start, what will happen to the moles of A? Moles of A will start to decrease. Moles of B will start to increase due to forward reaction. Then after that, backward reaction will start. And there will be a time when the rate of forward and backward reaction becomes equal. And that state in this reaction where the rate of forward and backward reaction becomes equal, we call that particular state as equilibrium. I hope you got it. Let's have a look on it a bit more in detailed way. Have a look, guys. For example, I'm assuming when 20% reaction is completed, when 20% reaction gets completed, let's say at that point of time, equilibrium is established in the reaction. This is something which I'm assuming. For example, when 20% reaction is completed, let's say at that point of time, equilibrium is established in the reaction. Now, what is meant by this term, 20% reaction completed? What do you mean by that? That means at equilibrium, if I'm saying 20% reaction is completed, that means 20% of reactant has got converted into products. 20% of reactant has got converted into products. How many moles of reactant we had in the beginning? 10. So what is 20% of 10? That means 2 moles. 20% of 10 means 2 moles. That means at equilibrium, we saw out of 10 moles of reactants, 2 moles of reactant got converted into products. So how many moles of reactants I'll be left with? I'll be left with 8 moles of reactants, right? Since 1 mole of reactant gives 1 mole of products, so 2 moles of reactant will give 2 moles of products. So this is something which I assumed. I assumed when 20% reaction gets completed, equilibrium is established, right? And as you can see, 20% reaction completed means 20% reactant getting converted into products. So I'm assuming at equilibrium, 20% reactant has got converted into product, right? Now, since this is the state of equilibrium, that means now the rate with which forward reaction takes place, with the same rate backward reaction takes place. If 1 mole of reactant now is getting converted into product, at the same time, 1 mole of product will be getting converted into reactant. Okay. Now you tell me, if the rate of forward and backward reaction becomes equal, if the rate of forward and backward reaction has become equal, can you tell me, are the number of moles of reactants and products going to change now? The number of moles of reactants and products are not going to change now, because the rate with which forward reaction is happening, with the same rate backward reaction is happening. Perfect, right? As simple as that. That means the number of moles of reactants and products now, after equilibrium is established in the reaction, the number of moles of reactants and products are not going to change at all. Yes, they are not going to change at all. You must be knowing about concentration. Concentration is simply defined as number of moles per unit volume. Number of moles per unit volume. Since the volume of container is fixed, at equilibrium, moles of reactants and products, they have attained a fixed value. At equilibrium, moles of reactants and products, they have attained a fixed value. That means concentration of reactants and products will be also fixed, right? So I can say at equilibrium, the concentration of reactants and products, they have attained a fixed value. Since the moles have attained a fixed value, therefore concentration also has attained a fixed value. As simple as that. Okay. Now, as you can see, if I ask you how many moles of reactants are there in the container at equilibrium, there are 8 moles of reactants in the container at equilibrium. How many moles of products are there in the container at equilibrium? There are 2 moles. Can I say this is one particular scenario where the number of moles of reactants, at equilibrium are greater than that of number of moles of products at equilibrium. In the similar way, If number of moles of reactants at equilibrium are more than that of number of moles of products, you can say concentration of reactants at equilibrium is again greater than that of concentration of products at equilibrium, right? Now, if I want you guys to define the same thing in the graphical manner, how you guys are going to define it? Have a look. Let me make a curve. Concentration versus time. Concentration versus time. See, when we were at time t is equal to 0, there were only moles of reactant left. There were only moles of reactant in the container. Now what happened? Moles of reactants started to decrease, right? Then moles of reactants, they attained a fixed value. Perfect. So at time t is equal to 0, moles of reactants were maximum. With time, moles of reactant kept on decreasing. And when equilibrium was established, moles of reactant, they attained a fixed value. So, same thing has happened to the concentration as well. So, I would say at time t is equal to 0, the concentration of reactant was maximum, then it decreased, and then it attained a fixed value. Then it did not change at all. Perfect. Similarly, dear students, the concentration of product initially was 0. Then it started to increase. Then it remained constant. So, the concentration of product at time t is equal to 0 was 0. Then it started to increase and then became constant. Right? This particular one, it's for the reactant. This particular one, it's for the product. Right? Can I say this is basically the time? Can I say this is the time? This is the time after which the concentration of reactants and products is not changing at all. This is the time after which the concentration of reactants and products is not changing at all. And that time wherein the particular reaction, the concentration of reactant and products does not change at all, that time is something which you call as equilibrium. So I would say at this particular time, equilibrium is established in the reaction. I would say at this particular point of time, entropy of the system becomes maximum, Gibbs free energy of the system has become minimum. Right? So this particular state of the system, I'll be considering now as the most stable state of the system. I hope this is clear to everyone, right? Perfect. So if I ask you whether this graph is representing equilibrium or not, absolutely it is representing equilibrium. What is the condition? At equilibrium, the concentration of reactant and product, it becomes fixed, it becomes constant. And this is one particular scenario wherein the concentration of reactant at equilibrium is greater than that of concentration of product. Now there can be one more scenario as well. The concentration of reactant and product at equilibrium can be same as well, right? So there can be one more graph representing the equilibrium. There can be one more graph representing the equilibrium like this. So if I make concentration versus time curve, you know, concentration of reactant decreases with time and then becomes constant. Concentration of product increases with time, then becomes constant. So this is the particular time wherein, this is the particular time after which the concentration of reactant and product has attained a fixed value. It's not changing. So this particular position is representing the equilibrium position. So this graph also correctly represents your equilibrium. This graph also correctly represents your equilibrium. In the similar way, can there be any other graph representing the equilibrium? Absolutely, my dear students. Absolutely. Like this. Concentration versus time. Concentration versus time. We know the concentration of reactant decrease with time, then becomes constant. Concentration of product increase with time, then becomes constant. Right? Now, it's not necessary that at equilibrium, moles of reactant will be always greater than that of moles of products. No. It's not necessary the moles of reactant and products will be equal at equilibrium. It's not necessary. Moles of product at equilibrium can be greater than that of moles of reactant at equilibrium. That is also one possibility, right? And this is the particular scenario. This is the particular scenario after which I can say equilibrium is established in the reaction, right? This curve represents that the concentration of reactant at equilibrium is equal to the concentration of product at equilibrium. This curve, as you can see, this particular point represents the concentration of reactant at equilibrium. This particular point represents the concentration of product at equilibrium. I must say the concentration of product at equilibrium is greater than that of concentration of reactant at equilibrium, right? And what about the first one? This curve represents that the concentration of reactant at equilibrium is greater than that of concentration of product at equilibrium. So all these three graphs, this one, the first one, the second one and the third one, all the three graphs, they correctly represent the equilibrium. I hope this is clear to everyone. Let me know once in the chats with the thumbs ups if it is clear. Quickly let me know in the chats if it is super clear to everyone. Let me know quickly. Let me know quickly in the chats if it is super duper clear to everyone. So from now onwards, you are just going to remember one thing. Whenever in reactions, you will be defining equilibrium. You just have to say one thing. At equilibrium, the concentration of reactants and products, they should attain a fixed value. Then there are three cases which arise. Concentration of reactant at equilibrium can be greater than concentration of product. Concentration of reactant at equilibrium can be equal to the concentration of product at equilibrium. Concentration of product at equilibrium can be greater than that of concentration of reactant at equilibrium. Then these are the sub cases. I hope this is clear to everyone, right? One more thing, guys. Will there be any other curve representing equilibrium? Absolutely. Now have a look. If I'll be plotting a graph between rate of the reaction versus time. Rate of the reaction versus time. When we define equilibrium in terms of rate, we say at equilibrium, rate of forward and backward reaction becomes equal. In terms of rate, if we want to define the equilibrium, there will be only one graph representing the equilibrium in terms of rate. Rate of forward reaction has to be equal to rate of backward reaction at equilibrium, right? So, if you want to plot a graph, the graph is going to be like this. The graph is going to be like this. And at this point, we can say rate of forward and rate of backward reaction has become equal. So, it is going to be your equilibrium stage. Got it? Right, people? I hope everything is clear till here. So, this was something real basics and something really important as far as equilibrium is concerned. Now comes a point. Understand it properly what I'm going to say now. Okay? Now comes a point. There is something called as a law of mass action. Now we are actually entering into the chapter. Okay? Now we are actually entering into the chapter. Law of mass action. What law of mass action states? What is this law of mass action all about? Understand properly. Let's have a look at the statement first of all. Law of mass action says that the rate of the reaction that is directly proportional to the product of active masses. The product of active masses of reactants raised to the powers of their stoichiometric coefficients. What it means exactly. Have a look. Properly have a look, guys. Let's say I have got a balanced chemical equation in this format, N1A plus N2B. It gives N3C plus N4D. This is a reaction, for example. Okay. If I ask you whether this particular reaction is reversible, yes, it's reversible. The reaction goes in the forward direction as well as in the backward direction. So if I ask you, actually, is this one reaction or two? Actually, if you want to analyze it in detail, these are actually two reactions. One is the forward reaction, one is the backward reaction, right? One is forward, one is backward. So let me just classify them into two. This is the forward reaction. And what is the backward reaction? Backward reaction will be like this. N3C plus N4D, it gives N1A plus N2B. This is your backward reaction, correct? This is forward and this one is backward. I hope this is clear. Now, dear students, if I talk about this particular forward reaction, as per law of mass action is concerned, rate of reaction, and right now I'm talking about this forward reaction, I can say rate of forward reaction is directly proportional to the product of active masses of reactants. What are reactants here? A and B. So I have to take the product of active masses of reactants. I can say active mass of A multiplied by active mass of B raised to the powers of their respective stoichiometric coefficients. Stoichiometric coefficient here is N1, here it's N2. So raised par N1, raised par N2. What are these active masses? You'll get the idea in some time. What are these active masses? You'll get the idea in some time. Rate of forward reaction is directly proportional to the product of active masses of reactants raised to powers their stoichiometric coefficients. Similarly, if I ask you, what about rate of backward reaction? You tell me in the backward reaction, which is your reactant? In the backward reaction, this C and D is your reactant. In the backward reaction, this C and D is your reactant. So I'll say rate of backward reaction as per law of mass action is directly proportional to active mass of C multiplied by active mass of D raised to the powers of their stoichiometric coefficients. The coefficient here is N3 and here it's N4. As simple as that. Right? Now dear students, just do one thing. Just do one thing. Remove the proportionality sign. Rate of forward reaction is equal to, I'll put a constant Kf. This is going to be active mass of A raised par N1, active mass of B raised par N2. Similarly, rate of backward reaction is equal to, put a constant Kb, active mass of C raised par N3, active mass of D raised par N4. Now you must be thinking, what is this Kf and Kb here? Kf is something which you call as the rate constant for forward reaction. This is called as the rate constant of forward reaction. And similarly, this Kb over here, I'll be calling it as rate constant for backward reaction. Rate constant for backward reaction. Okay, rate constant for backward reaction. Now, dear students, one thing. Few minutes back, I told you, at equilibrium, rate of forward and rate of backward reaction becomes equal. At equilibrium, what do we see? Rate of forward and rate of backward reaction becomes equal. So what is rate of forward reaction? What is rate of forward reaction? Have a look on this statement. I would say rate of forward reaction is equal to Kf multiplied by active mass of A raised par N1, active mass of B raised par N2 is equal to rate of backward reaction Kb multiplied by active mass of C raised par N3, active mass of D raised par N4. Correct? Absolutely correct. Yes. Now dear students, if I just write something like this, Kf divided by Kb. Kf divided by Kb I'll write as active mass of C raised par N3, active mass of D raised par N4 divided by active mass of A raised par N1, active mass of B raised par N2. Right? What is this Kf? Rate constant of forward reaction. Rate constant of backward reaction. If I take the ratio of the two, since this is a constant, this is a constant, division of two constant becomes one more constant, right? Division of two constants becomes one more constant, and that particular constant is called as equilibrium constant, right? So instead of Kf divided by Kb, I can write Keq, where Keq represents your equilibrium constant, and this is how you write the expression for equilibrium constant. This is how you write the expression for equilibrium constant. And let's try to analyze things a bit more in detail so that you won't feel any sort of difficulty in understanding afterwards. This is how you write the expression for equilibrium constant. This is this Keq, this is your equilibrium constant here. This is your equilibrium constant here. Now you must be thinking what this active mass etc is all about. Just one thing which I would want you guys to remember. Just one thing which I would want you all to remember at this point of time. Let's not go into the details. Let's solve the questions quickly by just having a look on the things which are used in the questions. Okay? Dear students, I would want you guys to remember few things. Whenever you will see any reactant or product present in solid state, solid form. That means if in a reaction, for any reactant or product, in the bracket they are mentioning S. That means this reactant is in solid form, right? Any reactant or product which is going to be in solid form, its active mass is generally, it's taken as constant basically. Its active mass is taken as constant. And just to reduce the calculations, we assume the value of constant to be 1. just to reduce the calculations, we assume that the value of that constant is 1. So any reactant or product which will be in pure solid state, its active mass will be unity. Number 1. Any reactant or product which will be present in pure liquid state, any reactant or product which will be present in pure liquid state, generally its active mass is also taken as constant, which is unity. Any reactant or product which will be in aqueous state, in the bracket if they mention AQ, in the bracket like it was mentioned S here, in the bracket for example they are mentioning AQ, any reactant or product which will be present in aqueous state, remember its active mass is taken as its concentration. And any reactant or product which will be present in gaseous state, its active mass can be either taken as concentration or you can take it as pressure as well. For gases, concentration as well as pressure is defined, right? For gases, concentration as well as pressure is defined. So these 4 things are important. Any reactant product in solid state, its active mass, unity. Pure liquid state, generally unity. Aqueous state, its active mass is the concentration. Gaseous state, its active mass is either concentration or pressure. Both the things are defined, right? Both the things are defined. Is it clear till here quickly? Yes or no in the chats with the thumbs ups? Yes or no in the chats with the thumbs ups quickly? Quickly everyone. Quickly everyone. All clear till here? Now what are we going to do after this? Have a look. We know how to write the equilibrium constant expression. In the numerator, you have to write the active mass of products. In the denominator, you have to write the active mass of reactants. In the numerator, you have to write the active mass of products. In the denominator, active mass of reactants. Now, based on all these things, what we do, we classify equilibrium constant actually into many types, but in your syllabus, there are only 2 things. In your syllabus, in your NEET syllabus, we have to discuss only 2 things. Equilibrium constant, I'll be dividing into 2 categories. One will be called as Kc, one will be called as Kp. One is Kc, one is Kp. When do we write Kc instead of Keq? And when do we write Kp instead of Keq? When do we do that? When do we do that? When do we do that? Do remember, whenever in this particular expression, the active masses are replaced by the term concentration. Whenever the active masses in this particular expression are replaced by the term concentration, at that point of time, instead of Keq, you write Kc. Whenever in this particular expression, active masses are replaced by the term pressure, at that point of time, instead of Keq, you can write Kp. You can write Kp. I hope this is clear. I hope this is clear. Yes? Right? So, in this particular expression, whenever instead of these active masses you are writing concentration, you are writing concentration of C, concentration of D, etc., etc. That means, at that point of time, your Keq becomes your Kc. If you take partial pressures here in this expression, then you have to write Kp instead of Keq. That's it. This Kp, Kc, these are the equilibrium constants only. But only differences, what is the difference? When you write Kc expression, you have to take the terms concentrations. When you write Kp expression term, you have to take the term partial pressure in this expression. That's all. Right? Now let's have an exact look how to write the expression for Kp and Kc properly. Let's have a look on that. Let's have a look on that. Okay? Now guys, for example, this is a reaction. Let's say this is a reaction. One simple reaction we have, okay? Let's see exactly how to write its Kc expression and Kp expression, okay? Let's see how to write its Kc and Kp expression. Understand what I'm going to say. Since this is in gaseous phase, gaseous phase, gaseous phase, all the reactants are present in gaseous phase, right? That means it's a homogeneous gaseous phase reaction. It is a homogeneous gaseous phase reaction, yeah? Now, dear students, if I want to write, since all the reactants are in gaseous phase, for gases, we define concentration as well as pressure. So, you can write Kc expression as well as Kp expression. If you want to write the Kc expression, how exactly? Start with the product. It's going to be concentration of H2 at equilibrium raised power stoichiometric coefficient multiplied by concentration of I2 at equilibrium raised power stoichiometric coefficient divided by, it's going to be concentration of Hi at equilibrium raised power its stoichiometric coefficient, that's 2. Right? Similarly, if you want to write the Kp expression, you can do that. Kp expression is simply going to be, start with the product again. It's going to be partial pressure of H2 at equilibrium raised power stoichiometric coefficient, that's 1, multiplied by partial pressure of I2 at equilibrium raised power stoichiometric coefficient, that's 1, divided by, it's going to be partial pressure of Hi at equilibrium raised power stoichiometric coefficient, that's 2. Simple. You wrote the expression for Kc as well as Kp. Now there is one more thing. Look at this particular reaction. This is an aqueous state, this is an aqueous state, this is an aqueous state. What is the active mass taken for those reactants or products which are in aqueous state? It's concentration, it's not pressure. So can you write the expression for Kp? You cannot write the expression for Kp, right? Since here all the reactants products were present in the gaseous state. Therefore, for gases, active mass can be taken its concentration as well as pressure. But here, all the reactants products are in aqueous phase, correct? So I can only write the expression for Kc. Kc expression is going to be concentration of NH4 positive raised power stoichiometric coefficient 1, concentration of OH negative raised power stoichiometric coefficient 1 divided by concentration of NH4OH raised power stoichiometric coefficient 1. Yeah, very simple and basic. Very simple and basic, right? Perfect. Similarly, let me take few more examples so that you properly master it. Okay, let me take few more examples so that you can properly master it. All right, have a look. I've taken two reactions over here. This is solid, this is solid, this is gas. Since the states are different, so should I be calling this as homogeneous or heterogeneous? It is a heterogeneous reaction first of all. Now, dear students, just tell me, how do we write Kc expression? I'll start with the product. Solid, its active mass is unity, nothing to do with this. Gas, I'll write, since I'm writing Kc, so it's going to be concentration of carbon dioxide at equilibrium raised power 1 divided by reactant which is in solid form, nothing to do with that. Its active mass is already unity. Now write the Kp expression. Start with the product, active mass unity. What about this one? This gas. Now I'll be writing partial pressure of carbon dioxide at equilibrium raised power stoichiometric coefficient 1 because I'm writing Kp now. Perfect. Okay, one more thing. All right, let's keep it here only. This is Kc, this is Kp. Now look at the next one. This is solid, nothing to do with this. This is gas and this is gas. Homogeneous or heterogeneous? Quickly. Homogeneous or heterogeneous? Heterogeneous. Right? Heterogeneous. Now, dear students, since this is in gaseous phase, this is in gaseous phase. For gases, we define active mass. Either as concentration or partial pressure. Right? So, people, if I ask you to write the Kc expression for this reaction, start with the product. It's going to be concentration of SO3 at equilibrium raised power stoichiometric coefficient divided by concentration of O2 at equilibrium raised power stoichiometric coefficient, that's 3/2. Let's write the Kp expression as well. Kp expression, start with this. It's going to be partial pressure of SO3 at equilibrium raised power stoichiometric coefficient divided by, it's going to be partial pressure of O2 at equilibrium raised to the power the stoichiometric coefficient, that's 3/2. Correct? Let me know once in the chats if it is super clear. Let me know once in the chats if every single thing is clear till here. Everyone. Now one more thing, dear students. You got to know how to write the Kp and Kc expression, right? Now, for a particular reaction, how do you calculate delta Ng? What is delta Ng first of all? Delta Ng is defined as number of moles of gaseous reactants minus number of moles of gaseous products. I wrote the reverse, sorry. Number of moles of gaseous products minus number of moles of gaseous reactants. What is meant by this? This is very important. How to calculate delta Ng for any reaction, this is important. whenever you need to calculate delta Ng for any reaction, you have to consider only those reactants and products which are in gaseous state. You have to consider only those reactants and products which are in gaseous state. So, number of moles of gaseous products. Let's have a look. This is product, this is product. This is in gaseous state, this is in gaseous state. How many moles here? 1. How many moles here? 1. So, 1 plus 1 comes out to be 2. So, we have got 2 moles of gaseous products minus number of moles of gaseous reactants. This is in gaseous state, okay. How many moles of it? 2. So, 2 minus 2 comes out to be 0. So, delta Ng for this particular reaction is 0. Delta Ng for the first reaction is 0. Number of moles of gaseous products minus number of moles of gaseous reactants, right? Similarly, have a look on this these two reactions. Can you let me know in the chats what should be the delta Ng value for this reaction? Delta Ng for this reaction, quickly. Everyone, start with the products, but take only those reactants products which are in gaseous state. So, this is in solid state, nothing to do with this. Solid state, nothing to do with this. Start with the gaseous product. This is the gaseous product. Its moles are 1. So, delta Ng for the reaction is 1. Look at the next one. This is in solid form. Nothing to do with this. This I have to consider. This I have to consider. So, delta Ng for this particular reaction is going to be equal. Number of moles of gaseous products. That's 1. Minus. Number of moles of gaseous reactants. That's 3 by 2. Right? Solid. Get the value of delta Ng. I hope this is clear. I hope this is clear. So, you got to know till now how to write the Kp expression, Kc expression and Kp expression, Kc expression and delta Ng expression. So, let me quickly summarize this. These are the two reactions. Let's analyze them and let's move ahead. Have a look. This is the first reaction. Tell me first of all, what about delta Ng for this reaction? Number of moles of gaseous products 2 minus number of moles of gaseous reactant, that's 1. So, the value comes out to be 1. So, this is delta Ng for the reaction. Look at the next one. What about delta Ng for the second reaction? Number of moles of gaseous products, that's 1. Number of moles of gaseous products, 1. 1 plus 1 makes it 2. So, it's 2 minus number of moles of gaseous reactant, 0. So, delta Ng for the reaction is 2. Right? Delta Ng for the reaction is 2. Perfect. Now, people, if I want you guys to write the expression of Kc for this reaction, Kc expression, to start with the product, it's going to be concentration of NO2 at equilibrium raised by stoichiometric coefficient divided by concentration of N2O4 at equilibrium raised by stoichiometric coefficient. Simple. Similarly, write the Kp expression. This is gas, this is gas. So, write partial pressure of NO2 at equilibrium raised by stoichiometric coefficient, that's 2, divided by partial pressure of N2O4 at equilibrium raised by the stoichiometric coefficient, that's 1. Simple, right? Simple. Yes, delta Ng can be negative as well. Yes, absolutely. Similarly, look at this particular reaction. Write the Kc expression. Start with the product. Concentration of NH3 at equilibrium raised by 1. Concentration of H2S at equilibrium raised by 1. This is solid, nothing to do with this. Write the Kp expression. Kp is going to be partial pressure of NH3 at equilibrium raised by 1. Partial pressure of H2S at equilibrium raised by 1. That's it. Let me know once in the chats, everyone with the thumbs ups, if every single thing is clear till here. Yes, after this we'll be doing the ionic equilibrium. After this we will be doing the ionic equilibrium as well. Once in the chats, if it is all clear till here. If it is all clear till here. Quickly. Everyone guys in the chats. Perfect. Perfect guys. Now what is the relation between Kp and Kc for a particular reaction? What is the relation? Let's say you've got a reaction like this. N1A gas plus N2B gas. It's in equilibrium with N3C gas plus N4D gas. Let's say this is the reaction which is carried out at constant temperature, for example. Okay? Right? Now, dear students, since you can calculate Kp value for this reaction, you can calculate Kc value for this reaction. If I ask you what is the general relation between Kp and Kc for a particular reaction, do remember? Just a second. Do remember, your Kp is equal to Kc RT raised by delta Ng. Just this particular result you have to remember. Just this particular result you have to remember. For a particular reaction, Kp is equal to Kc RT raised by delta Ng. If I ask you what is the delta Ng value for this reaction, delta Ng is equal to number of moles of gaseous products, which is N3 plus N4. Number of moles of gaseous products minus number of moles of gaseous reactants, which is N1 plus N2. This is how you'll be calculating delta Ng for this reaction as well. Perfect. Let's take few examples so that you can master it properly. Let's take few examples so that you can master it properly. Let's take few examples, just a second. These are 4 reactions which are given. These are 4 reactions which are given. We have to write the Kp expression in terms of Kc for everyone. Okay, have a look properly. If you look at the first reaction, people, if you look at the first reaction, just let me know what is the delta Ng value for the first reaction. Delta Ng for first reaction, number of moles of gaseous products minus number of moles of gaseous reactants. 2 minus 2 is 0. So delta Ng is 0 for the first reaction. If delta Ng is 0, we know Kp is nothing, it is just Kc RT raised to the power delta Ng. Now, dear students, if you see, since for the reaction, for the first reaction delta Ng is 0, anything raised to power 0 is 1. So that means for the first reaction, Kp is equal to Kc. For the first reaction, Kp is equal to Kc, right? Look at the second reaction. For the second reaction, let's calculate delta Ng. Delta Ng is going to be number of moles of gaseous products, which is 1 plus 1, that's 2, minus number of moles of gaseous reactant, that is 1. So 2 minus 1 comes out to be 1. So delta Ng is 1. If delta Ng is 1, I can say Kp will be equal to Kc RT raised power delta N, that's 1. So this is the relation between Kp Kc. Correct? Similarly, if I take the third reaction into consideration, for the third reaction, calculate delta Ng. Delta Ng is going to be number of moles of gaseous products, that's 2, minus number of moles of gaseous reactants, that is 3 plus 1, makes it 4. So 2 minus 4 makes it minus 2. So this is delta Ng. If this is delta Ng, I can say Kp is equal to Kc RT raised to the power delta Ng, that's minus 2. So this is the relation. The last one you can try on your own, right? The last one you can try on your own. So can you once quickly let me know in the chats what is delta N for this particular reaction? What is delta Ng for this reaction quickly? Can you quickly let me know in the chats what is the delta Ng for the last reaction? Everyone. Everyone. Delta Ng for the last reaction. Everyone, guys, everyone. Majority is saying 1. That means you are perfectly right. It's 1 only, okay? Perfectly done. All right. One more thing. How do you calculate the units of Kp and Kc? How do you calculate the units of Kp and Kc? In general, you have to remember this. Kc units you'll be always writing as moles per liter raised by delta Ng. So first of all, you'll be calculating delta Ng for the reaction. Then moles liter inverse raised by delta Ng. That's going to be the unit. Similarly, unit of Kp, it's going to be ATM raised by delta Ng or bar raised by delta Ng. Matlab unit of pressure raised by delta Ng. Right? For example, have a look. Just a second. Just a second. Look at the first reaction. Look at the first reaction. What should be the unit of Kp if the pressure is in atm? For the first reaction, what is the Kp unit? Tell me. For the first reaction, what is the Kp unit? Let's say pressure is in atmosphere, raised power, delta Ng. Delta Ng for the first reaction is 0. Anything raised power 0 is 1. So Kp is unitless here. Kp is unitless. Right? Similarly, Kc units. It's going to be moles liter inverse raised power delta Ng. Delta Ng is 0. Anything raised power 0 is 1. So Kc is also unitless here. I hope you are getting it. Right? So Kp, Kc units, just remember it directly. I'm not going to derive all these things right now. Okay? So Kc units are directly going to be moles per liter raised power delta Ng for the reaction. Similarly, Kp units are going to be pressure units, which can be atm, bar, whatever, raised power delta Ng. That's all. That's all, people. Okay? Perfect? Clear? I hope this is clear to everyone. Quickly, once in the chats, if you can do all these things from now onwards. Then there are few characteristics of equilibrium constant from which question comes. There are few characteristics of equilibrium constant from which question comes, okay? And what are these characteristics of equilibrium constant? Few you need to remember, and we'll see exactly how questions are to be solved, right? See guys, for example, I'm taking a reaction. Let's say I've got a reaction, and the reaction is, for example, in this format. Let's say I've got a general reaction as A in equilibrium with B. This is the reaction, let's say. A general reaction. A in equilibrium with B. Okay? Now people, one thing which I would want you guys to remember. Let's assume the equilibrium constant of this reaction I'm representing by K1 or K. K represents the equilibrium constant, okay? K represents the equilibrium constant of this particular reaction. Now remember a few things. If you multiply this particular reaction by some number, okay, if you multiply this reaction by some number, for example, you are multiplying this reaction by number n. So it becomes n times A in equilibrium with n times B. Now if you want to know the equilibrium constant of this reaction, do remember, whenever a reaction is multiplied by some number, that number goes to the power of the equilibrium constant. Now the equilibrium constant of this reaction is going to be K raised power n. This is now going to be the new equilibrium constant. Yeah? In the similar way, for example, if you reverse the reaction, if you reverse this reaction, if you make it like this, B in equilibrium with A, if you reverse this reaction, equilibrium constant is inversed. Equilibrium constant is inversed. Initially, the equilibrium constant was K. Now, it's going to become 1 by K. Now, it's going to become 1 by K. Right? It's going to become 1 by K. First of all, whenever you multiply a reaction by some number n, that n goes to the power of equilibrium constant. When you reverse a reaction, the equilibrium constant is inversed. Right? Now, people, if I ask you like this, let's say I've got a reaction like this. A in equilibrium with B. Then you have got B in equilibrium with C, or let's keep it as C in equilibrium with D. Equilibrium constant of first reaction is K1, the second reaction is K2. Since both the reactions are at equilibrium, if you just add them up, when you add them up, the net reaction becomes A plus C in equilibrium with B plus D. This is the net reaction. Now, if you ask me what is the equilibrium constant for this particular reaction, on adding the two reactions, their equilibrium constants are multiplied. Now, the equilibrium constant of this final reaction will be K1 multiplied by K2. Right? K1 multiplied by K2. Yes? So, people do remember all these things from now onwards. When you multiply a reaction by some number, that number goes to the power of equilibrium constant. Right? When you reverse the reaction, equilibrium constant is inversed. Okay? When you add two reactions, their equilibrium constants are multiplied. That's it. Let's try to solve some questions out of these simple concepts so that you can understand it. This is a question, a very simple basic question this is. We are given with a reaction. The reaction is N2 gas plus 3 times H2 gas. It is in equilibrium with 2 times NH3 gas. This is the reaction. Its equilibrium constant K value is given to me as 49. Okay. Now I have to calculate the equilibrium constant for this particular reaction. How you guys are going to do these questions? These are frequently asked. These are frequently asked. I'm given with a reaction whose equilibrium constant is given to me. Now there is one more reaction given to me whose equilibrium constant I need to calculate. How? What you should do exactly? The reaction whose equilibrium constant is to be calculated. The reaction whose equilibrium constant is to be calculated. You will have to make that reaction. You will have to make that reaction from the given reaction. From the given reaction. So how exactly? See. What I'll be doing first of all, I'll be reversing this given reaction. If I reverse this reaction, it becomes 2 times NH3 in equilibrium with N2 plus 3 times H2. Since I have reversed this reaction, and on reversing the reaction, equilibrium constant is inversed. Now the equilibrium constant of this reaction is going to be 1 by 49. 1 by 49. After this, let's just multiply this reaction with 1 by 2. Let's multiply it with 1 by 2. So it becomes NH3 gives 1 by 2 times N2 plus 3 by 2 times H2. I'm multiplying this reaction by 1 by 2, right? Now that 1 by 2 has to go in the power of this equilibrium constant. See, it was 1 by 49 raised power 1 by 2 makes it 1 by 7. So 1 by 7 is basically the equilibrium constant value of this reaction which we made and calculated. Done? Yes? Clear? Let's solve one more question of the same manner so that you can understand it properly. One more simple question let's solve. What do you think? What do you think? Two reactions we are given with. Equilibrium constant of first reaction was K1. Equilibrium constant of the second reaction was K2. The relation between K1 and K2 I need. What do you think? Look at both the reactions. Look at both the reactions. Look at both the reactions. What do you think? Should be the Kp? What do you think should be K1, K2 relation? Relation between the equilibrium constants of these two reactions. Quickly. Quickly, everyone. Quickly. See, first thing, let's do it like this. Have a look. Look at the first reaction. The first reaction is like this. A2 plus B2, it is an equilibrium with 2 times AB. This is the reaction whose equilibrium constant is K1. Alright. Let's do one thing. Let's just reverse this reaction. Let's see what happens. It's 2 times AB in equilibrium with A2 plus B2. Since you have reversed this reaction, so its equilibrium constant now is going to be 1 upon K1. Simple. It's going to be 1 upon K1. Now, dear students, if I multiply this reaction by number 3, its 3 2's are going to be 6 times AB in equilibrium with 3 times A2 plus 3 times B2. Right? 3 times B2. Since you multiplied this reaction by number 3, that 3 goes to the power of equilibrium constant. So it's going to be 1 upon K1 raised power 3. Now look at this particular reaction and this particular reaction. Are both the reactions same? Absolutely. Its equilibrium constant is K2. Its equilibrium constant is this one. So that means K2 has to be equal to 1 upon K1 raised power 3. So this is the relation between K1 and K2. Done and dusted. This is the relation between K1 and K2. I hope you can easily solve these sort of questions from now on. Yes? Perfect. Basic question. You tell me the answer in the chats. Tell me the answer in the chats. Two reactions. One is having K as equilibrium constant. Another one is K dash. Relation between K and K dash. This is 30 second, not even 30 second, 10 second question. 10 second question it is. Everyone quickly. Everyone quickly. I can see majority are coming up with option C. Is that? Sure? Let's have a look. Okay. Look at the first reaction. N2 plus 3 times H2 in equilibrium with 2 times NH3. Its equivalent constant is K. Okay. Let's do one thing. Let's multiply this reaction with 1 by 2. It becomes 1 by 2 N2 plus 3 by 2 H2 gives what? Gives NH3. Now, since you have multiplied this particular reaction by number 1 by 2, that 1 by 2 goes to the power of equilibrium constant. So, it's going to be K raised power 1 by 2. Let's call this as K dash. So, you got to know your K dash is equal to under root of K. That's it. Your K dash is equal to under root of K. All of you are perfectly correct. Wonderfully done. I hope everything is clear till here. So, let's move on now to one more question and you tell me its answer. In which of the following equilibrium Kp and Kc are not equal? When are Kp, Kc equal? You know Kp is equal to Kc RT raised power delta Ng, right? So, I would say Kp will be only equal to Kc if delta Ng value is 0, because anything raised power 0 is 1. And you know, and if delta Ng is non-zero, that means Kp won't be equal to Kc. What do we have to check? In which of the following Kp and Kc are not equal? So check which of the following reaction has got delta Ng non-zero. Check which of the following reaction has got delta Ng non-zero. If you look at option D, calculate delta Ng for option D. Number of moles of gaseous products, which is 2, minus number of moles of gaseous reactant, that's 1. So 2 minus 1 comes out to be 1, which is not equal to 0. So this is non-zero. Non-zero means Kp won't be equal to Kc. So option D is the one where Kp won't be equal to Kc. I hope this is clear. I hope this is clear to everyone. Yes? Absolutely, guys. Wonderfully done. Option D is the answer. Option D is the answer. One last question of the same format. Value of Kp for this reaction. What is the Kp value for this reaction? Everyone in the chats. Everyone in the chats. Kp you have to write for this reaction. Isn't it simple? Quickly. It is just Kp is going to be, start with the product. It's going to be partial pressure of carbon dioxide at equilibrium raised power stoichiometric coefficient. This is solid, nothing to do with this. This is solid, nothing to do with this. So this is the Kp value. Done and dusted. Okay. Moving on to something which is really important, that is Kp, Kc calculations. This is important. Kp, Kc calculations, right? There are two ways by means of which we can calculate Kp and Kc for the reaction. One method is called as mole method, one is called as degree of dissociation method. So let's analyze the mole method first. Let's see with the help of mole method, how can we calculate Kp for the reaction and how can we calculate Kc for the reaction. Let's analyze it. Okay. So what I'll be doing exactly? I'll be directly going into the questions, because through the questions it will be properly clear. Or let's just have a look on little basic things first. Okay. So my dear students, let's first of all understand how with the help of mole method, you can calculate Kp and Kc for the reaction. It's a very simple thing. Have a look. For example, you have got the reaction in this format. A gas is in equilibrium with B gas plus C gas. Let's say this is the reaction. Okay. For example, this particular reaction is taking place in a container whose volume is V liters. Let's imagine initially at time t is equal to 0, I have got A moles of reactant. So this will be 0, this will be 0. All clear till here? Right? Initially, let's assume we have got A moles of reactant. This will be 0, this will be 0. Now let's assume when equilibrium is established. Let's assume out of A moles of reactants, X moles got converted into products. So at equilibrium, I'll be left with A minus X moles of reactants, right? I'm assuming at equilibrium, out of A mole of reactant, X moles got converted into products. So I'll be left with A minus X. Now use the stoichiometry. Since 1 mole gives 1 mole, so from X moles, you are going to get X moles of products. Similarly, 1 mole gives 1 mole. From X moles, you get X moles of C. Correct? What did we get? What did we get till now? We got the number of moles of reactants and products at equilibrium. We got the number of moles of reactants and products at equilibrium. Since we got the number of moles of reactants and products at equilibrium, if I ask you how to write the Kc expression is going to be simple. Concentration of B at equilibrium raised by stoichiometric coefficient, concentration of C at equilibrium raised by stoichiometric coefficient divided by concentration of A at equilibrium raised by stoichiometric coefficient. Since we need the concentrations, what did we get? We got the moles. How can you convert moles into concentration? Concentration of reactant and product at equilibrium. Concentration is moles per unit volume, right? So it's going to be A minus X moles of reactant divided by total volume. This is the concentration of reactant at equilibrium. Similarly, moles of B at equilibrium divided by total volume. Moles of C divided by total volume. So these are the respective concentrations of each reactant and product. This is the concentration of A at equilibrium. This is the concentration of B at equilibrium. This is the concentration of C at equilibrium. Since now you can put all the values. Concentration of B at equilibrium is X by V. Concentration of C at equilibrium is again X by V whole divided by. Concentration of A at equilibrium is A minus X divided by V. So this V got cancelled. So it's going to be X square divided by V multiplied by A minus X. This is the value of your Kc. This is the value of your Kc. Right? This is the value of your Kc. This is how you write the Kc expression. Now, if I ask you how to write the Kp expression, this is how you write the Kc expression, okay? Now, similarly, how to write the Kp expression? There is one more phenomenon for that. I mean, there are some more rules which you need to follow. In order to calculate Kc, you have to write the concentrations of each reactants and products at equilibrium. Now, let's try to write Kp expression. So what we'll be doing, see, understand. You tell me, since this particular reaction is taking place in a closed container, it's taking place in a closed container. When equilibrium is established in the reaction, tell me how many moles of reactants are there in the container, A minus X. How many moles of B are there in the container, X. How many moles of C are there in the container, again X. So can you tell me how many gases, how many total number of gases are there in the container at equilibrium? Can you tell me that? How many total number of gases are there in the container at equilibrium? 3 gases. There are A minus X moles of reactant, X moles of B, X moles of C. So in total there are 3 gases present in the container at equilibrium. Correct? There are 3 gases. Yes? Perfect. So can I say at equilibrium we have got a gaseous mixture? At equilibrium we got a gaseous mixture. I'm assuming total pressure of that mixture I'm representing with PT. PT mixture, it represents the total pressure of the gaseous mixture. It represents the total pressure of gaseous mixture. Now dear students, this total pressure of gaseous mixture, the total pressure of the mixture won't be only due to A, won't be only due to B, won't be only due to C. The total pressure of the mixture will be the sum of partial pressures, right? So basically, A minus X moles of reactant as well as X moles of B as well as X moles of C. All the 3 will contribute towards the total pressure of the mixture. So I will say total pressure of the mixture will be equal to the sum of partial pressures. Partial pressure of A at equilibrium plus partial pressure of B at equilibrium plus partial pressure of C at equilibrium. I hope this is clear, right? Apart from that, if I ask you how many total moles are there in the container at equilibrium, total moles present in the container at equilibrium, that's going to be A minus X plus X plus X, which comes out to be A plus X. These are the total moles present in the container at equilibrium. Now, if I divide these moles by the total moles, if I divide A minus X with A plus X, if I divide X with A plus X, if I divide this X with A plus X, what do I got? What did I get? I got the mole fraction. I got the mole fraction of each reactant product at equilibrium. I got the mole fraction of each reactant product at equilibrium. If I ask you, what about the partial pressure? What about the partial pressure of each reactant product at equilibrium? What about partial pressure? Partial pressure. How do you get the partial pressure? Partial pressure is basically equal total pressure multiplied by mole fraction, right? So total pressure of the mixture is PT mix. Mole fraction of reactant is this much. So multiply the mole fraction of a reactant with the total pressure of the mixture. You got the partial pressure of A. Partial pressure of B is going to be mole fraction of B multiplied by total pressure. Partial pressure of B. Partial pressure of C is again going to be mole fraction of C multiplied by total pressure. This is the partial pressure of C. Since you got the partial pressure of each reactant product, you can now write the Kp expression. And Kp expression, how do you write? Partial pressure of B at equilibrium, that's X divided by A plus X multiplied by Pt, raised power stoichiometric coefficient 1. Partial pressure of C at equilibrium, that's X multiplied by Pt divided by A plus X raised power 1, divided by partial pressure of A at equilibrium, that's A minus X divided by A plus X multiplied by Pt, right? So this is the general way of calculating Kp. So again I'm telling you, in order to calculate Kc, you need the concentration of each reactant product at equilibrium. In order to calculate Kp, you need the partial pressure of each reactant product at equilibrium. I'll be making you understand all these things again in the form of questions. Have a look. Have a look. Understand. Have a look. Look at this question, guys. As far as this question is concerned, we are given the reaction, and the reaction is given in this format: A gas plus B gas. It's in equilibrium with 2 times C gas. This is the reaction. Okay. Now, it's mentioned in the question initially 2 moles of A, 1 mole of B, and 1 mole of C are placed in the container. So initially you have got 2 moles of A present in the container. You have got 1 mole of B present in the container. And at the same time, you have got 1 mole of C in the container as well. So initially, we have got 2 moles of A, 1 mole of B, and 1 mole of C in the container. Alright. This particular reaction is taking place in a container whose volume is 10 liters. So volume of the vessel in which reaction takes place, that's 10 liters. Okay. Now, as per the question, in this particular reaction, equilibrium is getting established after some time. When the reaction starts, finally equilibrium is getting established, right? And it's mentioned that the final concentration of C is 0.2 molar. That means the concentration of C at equilibrium is equal to 0.2 molar, right? Which is going to be the final concentration of C. Which is going to be final concentration of C, right? So initially 2 moles of this, 1 mole of this, and 1 mole of this was kept in the container. Now, as per the question, equilibrium is established, and when equilibrium is established, the concentration of C in the container is 0.2 molar, right? It's given. It's given. What do we need to calculate? We need to calculate Kc. Understand? For example, let's assume out of 2 moles of reactant, out of 2 moles of A, let's assume X moles of A reacted with B. So at equilibrium, can I say I'm left with 2 minus X moles of A? I was given with 2 moles of A. I assumed out of 2 moles of A, X moles reacted with B. So I'll be left with 2 minus X moles of A. Now use the stoichiometry. Since 1 mole of A reacts with 1 mole of B, so X moles of A would have reacted with X moles of B. I had taken 1. Out of 1, X is reacting. So I'll be left with 1 minus X moles of B as well at equilibrium. These are the moles of B present in the container at equilibrium. Similarly, already in the container, I had 1 mole of C. Already in the container, I had 1 mole of C. Now, due to the reaction, few more moles of C would have got formed. Since 1 mole of A gives 2 moles of C, so X moles will be giving me 2X moles. So these are the moles of C present in the container at equilibrium. You got all this? Right? Moles of A in the container at equilibrium, moles of B in the container at equilibrium, moles of C in the container at equilibrium. What do I need to calculate? I need to calculate Kc. But to calculate Kc, do I need moles or concentration? I need concentration of each reactant and product at equilibrium. How do I get the concentration? Moles divided by volume. So 2 minus x divided by volume is 10 liters. This is the concentration of A at equilibrium. 1 minus x divided by 10 liters, concentration of B at equilibrium. 1 plus 2x divided by 10 liters, concentration of C at equilibrium, right? So concentration of C at equilibrium is 1 plus 2x divided by 10, right? It's given to me as 0.2. 0.2 means 2 by 10, 10, 10 cancelled. So x value will come out to be 2 minus 1 is 1, 1 by 2 is 0.5. So x value you got to know is 0.5. You got the value of x. You got the value of x. You got the value of x, right? Since you got the value of x, you can put the value of x everywhere here. If you put the value of x here, it will give you the concentration of A at equilibrium. If you put the value of x here, concentration of B at equilibrium. If you put the value of x here, concentration of C at equilibrium. If you get concentration of all the reactants and products, you can easily write the Kc expression, which is going to be equal to concentration of C at equilibrium raised power 2 divided by concentration of A at equilibrium raised power stoichiometric coefficient, that's 1, concentration of B at equilibrium raised power stoichiometric coefficient 1. Correct? You got all these values here. All these values. After putting the value of x in these three terms, you'll be getting concentration of each reactant product. And concentration of each reactant product after getting, you can easily write the Kc expression and get the answer. Let me know once in the chats if it is super clear to everyone. Yes, these types of questions are asked. Yes, absolutely. Tell me once in the chats if it is clear to everyone. Quickly. Quickly, everyone, quickly. Quickly. Everyone with the thumbs ups, quickly. Perfect. Look at one more question like this. Look at one more question. The question is, similar type of question we have. X plus y is in equilibrium with what? X plus y is in equilibrium with 2 times z. This is the reaction, number 1. Now, as per the question, 1 mole of X, 1.5 moles of Y, and 0.5 moles of Z were taken in a 1 liter vessel. Allowed to react. At equilibrium, the concentration of Z was 1 molar. At equilibrium, the concentration of Z was 1 molar. The equilibrium constant Kc for the reaction is given to us as x by 15. We are supposed to calculate the value of x. Now understand how exactly I'm going to do it. Guys, just give me a second. What? Get me the bottles. Okay. So look at the question carefully. I wrote all the data. All the data is written here. We have 1 mole of X, 1.5 moles of Y, and 0.5 moles of Z initially. Right? This reaction has to take place in a container whose volume is 1 liter. Concentration of Z at equilibrium is 1 molar. What do we need to calculate? Kc is given to us as x by 15. We need to get the value of x. Now see how exactly we are going to solve this. My dear students, let's assume at equilibrium, out of 1 mole of reactant, let's assume x moles of this reactant reacted with Y. So at equilibrium, I'll be left with 1 minus x moles, right? As simple as that. I'm assuming out of 1 mole of this particular reactant, x moles reacted. So I'll be left with 1 minus x. Now, 1 mole of X reacts with 1 mole of Y. Perfect. So, X moles of this reactant would have reacted with X moles of Y. I had taken 1.5. Out of 1.5 X reacted, I'll be left with 1.5 minus X. These are the moles of Y present in the container at equilibrium. Already in the container, there were 0.5 moles of Z, right? Already in the container, there were 0.5 moles of Z. Now, due to the reaction, few more moles of Z would have got formed. So, 1 mole of this reactant gives 2 moles of Z. So, X moles of this reactant gives 2 times X, right? Gives 2 times X moles of Z. So, this will be 0.5 plus 2X. So, basically, what did we get? We got the moles of each reactant product present in the container at equilibrium. But do we need the moles or concentration? We need the concentration, right? So, you'll be dividing all the terms by the volume, right? You'll be dividing all the terms by volume. Volume of the system is given to us as 1 liter, right? Divide every term by 1, you'll be getting the concentration. And since you got the concentration of all the reactants, write the Kc expression. It's going to be concentration of Z at equilibrium raised power 2 divided by, it's going to be concentration of X at equilibrium raised power 1, and it's going to be concentration of Y at equilibrium raised power 1. I hope it's super clear till here. Now, my dear students, concentration of Z at equilibrium. Concentration of Z at equilibrium was given to me as 1 molar. Concentration of Z at equilibrium is also given to us as 0.5 plus 2X. So, 0.5 plus 2X is equal to 1. So, you can say 2X is equal to 0.5. So, X value will be equal to 0.25. You got the X value. You got this particular X value, right? You got this particular X value. This particular X value you got. Perfect. Since you got this particular X value, put the value of X everywhere here and get the actual concentrations. I'm sure you can do that. Let me just erase this once. So, 1 minus 0.5 comes out to be 0.75. And this term will be 1.25. And this term will be 1. So, you got the concentration of all the reactants products at equilibrium. Now, I would suggest you to write Kc expression. Kc expression will be simple concentration of Z at equilibrium raised power 2 divided by concentration of X at equilibrium raised power 1 and concentration of Y at equilibrium raised power 1. What is the concentration of Z at equilibrium? That's 1. 1 ka square is 1 divided by concentration of X at equilibrium, that's 0.75. Concentration of Y at equilibrium, that's 1.25, right? And this term is basically the value of Kc, and Kc as per the question is given to me as X by 25, X by 15. X by 15. Now, if you solve this particular equation, this is one equation, one unknown, you can get the value of X from here. That's something which you were supposed to calculate. Isn't it simple? Right? Clear? Yes? Is it super clear to everyone? Is it super clear to everyone? Let's do one more different type of question so that you can understand all the types, all the patterns. My dear students, as per this question is concerned, we are given the reaction N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. This is the reaction that's given to us. Okay? This is the reaction that's given to us. Now, when equilibrium will be established in the reaction, you will see some moles of N2 present in the container. There will be some moles of H2 in the container. There will be some moles of NH3 which would have formed in the container at equilibrium, right? At equilibrium, you will find the moles of all these three in the container. So basically, I can say at equilibrium, in the container, there is a mixture of gases present. There are few moles of N2 present. There are few moles of H2 present. And there are few moles of NH3 which have got formed, right? Yes. Now, dear students, since we have got a mixture of gases present in the container at equilibrium, so I can say the total pressure of the mixture at equilibrium will be equal to pressure of the mixture due to N2, right, plus pressure due to H2 plus pressure due to NH3. Since the total pressure of the mixture, as per the question, is given to me, the total pressure of the mixture as per the equation should be given to me. It's 2.8 atm. is equal to the contribution of N2 towards the total pressure of the mixture is also given to me, 0.8. Contribution of H2 towards the total pressure of the mixture, 0.4. Now I'll be getting from here the contribution of NH3 towards the total pressure. So I can say the contribution of NH3 towards the total pressure of the mixture is equal to 1.6 atm. This is the partial pressure of NH3. This is the contribution made by NH3 towards the total pressure of the mixture. Towards the total pressure of the mixture, right? Now what do I have to calculate? I just have to calculate the Kp value. Kp is just going to be partial pressure of NH3 at equilibrium raised power stoichiometric coefficient, partial pressure of N2 at equilibrium raised power stoichiometric coefficient, partial pressure of H2 at equilibrium raised power stoichiometric coefficient. Partial pressure of NH3 at equilibrium is basically 1.6, so it's 1.6 ka square divided by partial pressure of N2 at equilibrium is 0.8, partial pressure of H2 at equilibrium is 0.4 raised power 3. When you solve it, the value comes out to be exactly equal to 50. That's something which you were supposed to calculate. Is this clear? Is this clear to everyone quickly? This sort of a question can be asked as well. Okay, this sort of a question can be asked as well. Let me know once in the chats, guys, with the thumbs ups if it is super clear to everyone. Let me know quickly in the chats with the thumbs ups if it's clear to everyone. Everyone. Perfect. Perfect, guys, perfect. Just a second. Okay. Now have a look on one more concept. Usage of pressure instead of moles in a gaseous phase reaction. What is meant by this? What is meant by this? Let's say I've got the reaction in this format. A gas, it's an equilibrium with B gas plus C gas. This is one balanced chemical equation. I'm assuming this reaction is taking place at constant volume and temperature. This reaction is taking place at constant volume and temperature. Now, as far as your ideal gas equation is concerned, PV is equal to nRT, right? PV is equal to nRT. Since I'm keeping the volume and temperature constant, R is already constant, can I say pressure is directly proportional to moles? Yes, pressure is directly proportional to moles. What does that mean? That means if moles are decreasing, pressure will decrease. If moles are increasing, pressure will increase. Correct? Now, if I ask you initially at time t is equal to 0, in the container, there will be only moles of A. Now, with time, when the reaction will start, the moles of A will start to decrease. And if the moles of A starts to decrease, the pressure due to A will start to decrease as well. The pressure due to A will start to decrease. Since the moles of B and C will keep on increasing with time, so pressure due to B and C will start to increase as well, right? So pressure due to A will start to decrease with time. Pressure due to B and C will increase with time till equilibrium is established. Till equilibrium is established, right? Is that clear? The ratio in which the moles increase or decrease, the proportion in which the moles increase or decrease, in the same proportion, the pressure is going to increase or decrease. Right? Do remember this thing. The proportion in which the moles are going to change, in the same proportion, pressure is also going to change. So whatever treatment you were doing with the moles till now, same treatment you can directly give to pressure from now onwards. Same treatment you are going to give the pressure. For example, let's assume initially at time t is equal to 0, There is only reactant in the container. So whatever pressure is there at time t is equal to 0, that's due to A. Let's call it as P naught. Since B and C, they are not formed yet, so contribution towards the pressure by B and C is 0. Now, I can directly say at equilibrium, this is going to be P naught minus X. 1 mole gives 1 mole, X gives X, 1 gives 1, so X gives X. So, directly I am doing whatever treatment I was doing with the moles till now. Same treatment I am directly doing with the pressure. Isn't it very simple? This is the pressure due to A at equilibrium, pressure due to B at equilibrium, pressure due to C at equilibrium. Correct? At equilibrium, you have got a mixture of gases. And this is the contribution made by A towards the total pressure of the mixture at equilibrium. Contribution made by B towards the total pressure of the mixture at equilibrium. Contribution made by C towards the total pressure of the mixture at equilibrium. Right? Now, if you got to know, you can easily write the Kp expression now. Partial pressure of B at equilibrium, that's X raised power 1. Partial pressure of C at equilibrium, that's X raised power 1, divided by partial pressure of A at equilibrium, that's P naught minus X raised power stoichiometric coefficient, that's 1. So this is the Kp expression for this particular reaction. I hope you got it. I hope you got it, right? Perfect. Similarly, if I change the stoichiometry, let's see what happens. Let's say you got a reaction like this. A gas in equilibrium with 2 times B gas plus 3 times C gas plus 3 times C gas. Okay. Let's say initially at time t is equal to 0, the pressure due to A is P naught. This is 0, this is 0. Let's assume that. Now at equilibrium, let's make it as P naught minus X. 1 mole gives 2 moles, so from X you get 2X. 1 gives 3, from X you get 3X. Now, what are these terms? These are the pressures directly. These are the pressures directly. I'm starting directly from the pressure. So these are the pressures directly. Okay. So from this concept also questions are asked. Let's do 1-2 questions so that you can analyze and understand how questions are asked from the same concept. Have a look. Have a look, guys. As far as this question is concerned, the reaction is AB3. AB3 gas, that's in equilibrium with AB2 gas plus 1 by 2 times B2 gas. 1 by 2 times B2 gas. This is the reaction. Okay, this is the reaction. Now, as per the question, initially at time t is equal to 0, the pressure due to AB3 is given to me as 900 torr. So this will be 0 and this will be 0. Now at equilibrium, let's call it as 900 minus X, right? Now 1 mole gives 1 mole, from X you get X. 1 mole gives 1 by 2 moles, from X you get X by 2 moles. If I ask you, are these moles or this is pressure directly? Now this is pressure directly, right? This 900 minus X torr, this is the pressure of the mixture due to AB3 at equilibrium. This X torr, this is the pressure due to AB2 at equilibrium. This X by 2, this is the pressure due to B2 at equilibrium, right? As far as the question is concerned, it is mentioned that the total pressure of the mixture at equilibrium is equal to 1000 torr. If I ask you, what about the total pressure of the mixture at equilibrium? Can I say the total pressure of the mixture at equilibrium is going to be 900 minus X plus X by 2 plus X by 2. So this X got cancelled. The total pressure of the mixture is 1000 is equal to 900 plus X by 2. The value of X comes out to be what? It comes out to be 200 torr. You got the value of X. You got the value of X, right? Since you got the value of X, so 900 minus 200 comes out to be 700. This is the pressure of AB3 at equilibrium. This is the pressure due to AB3 at equilibrium. X value we know, that's already 200. This is the pressure due to AB2 at equilibrium. X by 2, 200 by 2 comes out to be 100 torr. This is the pressure due to B2 at equilibrium. Right? Yes? Right, people? So I got the partial pressures of each reactant product at equilibrium. Now, as far as the question is concerned, I was supposed to calculate Kp value, right? So Kp as per the question has to be equal to partial pressure of AB2 raised power stoichiometric coefficient, that's 1, So it's 200 raised power 1. Partial pressure of B2 at equilibrium, that's 100, raised power stoichiometric coefficient, that's 1 by 2, divided by partial pressure of AB3, raised power stoichiometric coefficient. So it comes out to be 2000 by 700. That means 20 divided by 7 is going to be the final value of Kp, which you were supposed to calculate. Is this clear to everyone? Quickly. Quickly, everyone. I hope this is clear. I hope you can solve these sort of questions easily. Clear? Ones in the chats? With the thumbs ups? Everyone here, quickly. Yes, for the gaseous phase reactions also same concept is used. Le-Chatelier principle will be after this. Just wait for it. Everyone, quickly, let me know if it's clear. Perfect. All right, there is something called as degree of dissociation, which is represented by alpha. Degree of dissociation, which is represented by alpha. Now people understand. For example, you have got a reaction like this. A in equilibrium with B and C. Okay. Let's say initially I have got A moles of reactant. This is 0. This is 0. This is something which I'm assuming. Initially, you have got A moles of reactant. This is 0, this is 0. Now, we have to define the degree of dissociation alpha. Alpha we have to define. How do we define alpha? Alpha is defined as number of moles of reactant dissociated. Number of moles of reactant dissociated into products divided by initial moles of reactants. Number of moles of reactant dissociated into product divided by initial moles of reactant. Now, my dear students, let's do one more thing. Let's keep alpha as such is equal to number of moles of reactant dissociated divided by how many initial moles of reactants I had? A. I had A moles of reactants. So from here, can I got the number of moles of reactants dissociated? Can I say I got to know it as A alpha? So what is this A alpha over here? These are basically the moles of reactant which dissociated into products. These are the moles of reactants which dissociated into products. Initially, I had A moles of reactant. Now at equilibrium, I got to know out of A moles of reactant, A alpha moles are getting converted into products. So I'll be left with A minus A alpha moles of reactant at equilibrium. Simple. Now 1 mole of A gives 1 mole of B. From A alpha you get A alpha moles. 1 mole of A gives 1 mole of C. From A alpha you get A alpha moles. So I got now, again I got the moles of each reactant's products at equilibrium. In terms of alpha now. I got moles of each reactant's products at equilibrium. If you got the moles of each reactant product at equilibrium, you can easily write Kp expression, you can easily write Kc expression, right? This is important. How to get the moles of reactants and products at equilibrium in terms of alpha. Now for example, if I change the stoichiometry, let me see if you can, calculate the moles of reactant products at equilibrium or not. Let's say the reaction is like this. A in equilibrium with 2 times B plus 5 times C, right? Let's say initially I'm starting with A moles of reactant. This will be 0, this will be 0. Let's assume degree of dissociation is alpha. Now you tell me, at equilibrium, can I say out of A moles of reactants, A alpha would have got dissociated. So I'll be left with A minus A alpha. Correct? Now 1 mole of A gives 2 moles of B. 1 mole of A gives 2 moles of B. From A alpha you get 2 times A alpha. 1 mole gives 5 moles. From A alpha you get 5 times A alpha. So these are basically the moles of reactants and products present in the container at equilibrium. Since you got the moles of reactants and products present in the container at equilibrium, you can easily calculate the concentration. You can easily calculate Kc value, and at the same time, you can easily calculate the Kp value. Correct? This is important. Calculation of moles present in the container at equilibrium. Only that's important. Rest, everything is very simple. Tell me in the chats quickly if it is clear, so that I can do few questions on this as well. Quickly, guys. Quickly, everyone with the thumbs ups. We'll finish chemical equilibrium, then I'll take a break. Right? We'll finish chemical equilibrium first. Okay, so let's try to do one question. One very simple question. Yes, it's a 10-hour class. Alright, so before solving this question, there is one more thing that's called as percentage dissociation. That's called as percentage dissociation. How do you define the percentage dissociation? It's always equal to degree of dissociation multiplied by 100. Degree of dissociation multiplied by 100 gives you the percentage dissociation, okay? Gives you the percentage dissociation. Calculate the Kp for the dissociation of 1 mole of PCl5. So basically you are taking PCl5, and when PCl5 dissociates, do remember, it gets converted into PCl3, and with this PCl3, you get Cl2. This is what happens when PCl5 is dissociated, okay? Now people, as per the question is concerned, initially how many moles of reactant we have? We are given with 1 mole of reactant, 1 mole of PCl5. So this will be 0, this will be 0. Percentage dissociation is 20. If percentage dissociation is 20, what about degree of dissociation? It will be 20 by 100, that means 0.2. That means 0.2, right? Right? So alpha value is 0.2. So at equilibrium, we know if the degree of dissociation is alpha, so at equilibrium, how many moles of PCl5 will be left? From A moles of reactant, A alpha would have got dissociated. I'll be left with A minus A alpha. Similarly, 1 mole gives 1 mole. So from A alpha, you get A alpha. Again, this is going to be A alpha. Simple. Correct? We know the value of A as well as we know the value of alpha. We know the value of A as well as we know the value of alpha. A is 1, alpha is 0.2. So 1 minus 0.2 comes out to be 0.8. So these are the moles of reactant present in the container at equilibrium. A times alpha. A is 1, alpha is 0.2. So 0.2. Even this is 0.2. I got the moles of each reactant product present in the container at equilibrium. Right? I got the moles. What do I need to calculate? I need to calculate Kp. I need to calculate Kp. Okay? If I ask you how many total moles are there in the container at equilibrium, you will say 0.8 plus 0.2 plus 0.2 makes it 1.2. So basically we have got 1.2 moles in total present in the container at equilibrium. These are the total moles present in the container at equilibrium. If I divide this 0.2 by the total moles, this term by the total moles, even this term by the total moles, this is something which I call as mole fraction of PCl5 in the container at equilibrium, mole fraction of PCl3 at equilibrium, mole fraction of Cl2 at equilibrium, right? But do I need the mole fraction or I need the partial pressure? I need the partial pressure, right? I need the partial pressure. So multiply the mole fractions by the total pressure of the mixture, and total pressure of the mixture at equilibrium is 1 atm. So multiply this with total pressure, total pressure, total pressure. I got the partial pressures of all. I got the partial pressures of all. Now you can write the expression for Kp. It's going to be partial pressure of PCl3 at equilibrium, that's 0.2 divided by 1.2 raised power stoichiometric coefficient 1. Partial pressure of Cl2 at equilibrium, that's 0.2 divided by 1.2 raised power 1 whole divided by partial pressure of PCl5 at equilibrium. That's 0.8 divided by 1.2 raised power 1. Solve it, get the value of Kp. Is this super duper clear to everyone? Is it super clear to everyone, guys? Quickly. Quickly. Quickly, everyone. Guys, say yes or no. Everyone. Perfect. All right, that's great. Now moving on to something called as calculation of degree of dissociation using vapor density measurement. This is one more way of calculating alpha, basically. One more way of calculating alpha. Okay. So first of all, let me take the case of dissociation. I'm not going to derive anything. I'll give you the relations and I'll show you how to apply them in the questions. For example, I'm taking the reaction as A in equilibrium with N times B. This is the reaction, for example, and I'm assuming N value is greater than 1. So N can be 2, it can be 3, it can be 4, etc., etc. Okay. So what is the stoichiometric coefficient here? It's 1. So 1 mole gives N moles. 1 mole gives N moles, and N is greater than 1. So it can be 2. 1 mole gives 2 moles. 1 mole gives 3 moles. 1 mole gives 4 moles. So can I say this is basically the case of dissociation? A is breaking into more than 1. I can say one part of A, 1 mole of A, 1 particle of A is breaking into more than 1 particles, right? So this is basically the case of dissociation, right? This is basically the case of dissociation. Now in case of dissociation, we have got one more way of calculating alpha, and I would want you guys to remember it from now onwards. Alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Now, what are these terminologies all about here? What are these terminologies? So dear students, alpha here, you know, it's degree of dissociation. What is capital D? Capital D is something which you call as theoretical vapor density. It's called as theoretical vapor density, right? And it is always equal to molar mass of reactant divided by 2. Theoretical vapor density, it's always equal to molar mass of reactant divided by 2, number 1. Small d, that's what you call as equilibrium vapor density. I'll write it first of all as experimental vapor density. Experimental vapor density, or you can call it as vapor density of the equilibrium mixture. Vapor density of the equilibrium mixture. It is always equal to average molar mass of the mixture. Average molar mass of the mixture at equilibrium divided by 2. What about this N? N represents number of moles of products produced from 1 mole of reactant. Number of moles of products produced from 1 mole of reactant. So first of all, remember all these things. Capital D is basically the theoretical vapor density. Molar mass of reactant divided by 2. Small d is the experimental vapor density, or you call it as the vapor density of equilibrium mixture, which is basically average molar mass of the mixture divided by 2. And N, everything you know. So this was the case of what? Dissociation. I'll show its application in some time. This was the case of dissociation. Now similarly can be the case of association as well. Similarly can be the case of association as well. Let's say, I'll say n moles of A gives An. The stoichiometric coefficient here is 1, here it's N. And I'm assuming N value is greater than 1. If N value is greater than 1, what does it mean? If N value is greater than 1, what does it mean? N can be 2, 3, 4, whatever. So 2 moles of A gives 1 moles of product. 3 moles of A gives 1 moles of product. 5 moles of A gives 1 mole of product, right? So what does it mean? So I would say more than 1 particles of reactant are associating and forming 1 particle. More than 1 particle of reactant are associating and forming 1 particle, right? So my dear students, in this particular case of association, how do we calculate degree of association, alpha? Degree of association is calculated as capital D minus small d divided by small d multiplied by 1 divided by n minus 1. This is going to be the result which you guys are going to remember. Rest everything is same. Theoretical vapor density, experimental vapor density. This N is basically N, you know what is it? Moles of reactant associating to form 1 mole of product. Okay, so these 2 results, these you have to remember and we have to utilize them in the questions. And what kind of questions are asked from here? Let's have a look. What kind of questions are asked from here? Let's have a look. Only basic questions are asked. Understand properly. The vapor density of N2O4 and NO2 mixture at a certain temperature at equilibrium. So can you let me know in the chats whether this 30 is the value of capital D or small d? That's something which I expect from you. Is it the value of capital D or small d? Calculate the percentage dissociation of N2O4 at the same temperature. So till then, I'll write the reaction. You tell me in the chats whether this is small d or capital D. Just tell me in the chats. Just tell me in the chats whether it's capital D or small d. Quickly. Quickly, guys. Capital D or small d, everyone? Exactly. See. So first of all, as per the question is concerned, we are given with the vapor density of the mixture at equilibrium. And you know, vapor density of the mixture at equilibrium is represented by small d, that's 30. Tell me, is this the case of dissociation or association? The stoichiometric coefficient here is 1, here it's 2. From 1 mole you are getting 2 moles, right? So N is equal to how much? N is equal to. If I ask you what about the value of capital D? Capital D is basically molar mass of reactant divided by 2. Capital D is molar mass of reactant divided by 2. Reactant molar mass, N2O4 molar mass is 92 grams per mole divided by 2. The value comes out to be 46. So capital D value is 46. We got it. What do we need to calculate exactly? Exactly, we need to calculate the percentage dissociation. So basically, if I talk about the percentage dissociation, it's degree of dissociation multiplied by 100, right? Percentage dissociation is basically the degree of dissociation multiplied by 100. So basically, we need to calculate alpha. How do we get the alpha? Few minutes back, I told you the formula. Capital D minus small d divided by small d multiplied by n minus 1, right? So what about capital D? 46, small d 30 divided by small d multiplied by n minus 1. N value is 2, 2 minus 1. The value after solving comes out to be 0.53. So this is the degree of dissociation. This is the degree of dissociation, right? So if you got the degree of dissociation, so what about the percentage dissociation? 0.53 multiplied by 100 is basically 53%. Done and dusted, right? Clear to everyone? Is it super clear to everyone? Quickly. Yes? Is it clear? Everyone. Give me some thumbs ups in the chats if it is clear to everyone. Right? All right, perfect. There is something called as reaction quotient. What is this reaction quotient all about? It's simple. See, for example, you have got the reaction like this: N1A plus N2B, N3C, N4D. I want you guys to write the equilibrium constant. I want you guys to write the equilibrium constant expression for this particular reaction. Kc expression. It's going to be concentration of C at equilibrium raised per N3, concentration of D at equilibrium raised per N4 divided by concentration of A at equilibrium raised per N1, and this is concentration of B at equilibrium raised per N2. Right? This is the expression for Kc. Yeah? This is the expression for Kc. Now, dear students, I am going to write the similar expression, but there will be certain changes. I am writing the similar expression, but certain changes I am doing. What all changes I am doing? See exactly. Here I took the concentration of C at equilibrium, right? But now I am going to take the concentration of C at any stage apart from equilibrium. Just the concentration of C at any stage apart from equilibrium. Raised per stoichiometric coefficient N3. Similarly, concentration of D at any stage apart from equilibrium, N4. Concentration of A at any stage apart from equilibrium. Concentration of B at any stage apart from equilibrium. Do these two expressions look alike? Yes, they look the same. What is the difference only? The difference lies in these concentration terms. These are all the concentration terms which I have taken at equilibrium. And these are the concentration terms which I have taken at any stage apart from equilibrium. Whenever you see this sort of expression, this particular expression is called as reaction quotient. And this particular expression is called as equilibrium constant. I told you in the beginning itself, at equilibrium, entropy of the system is maximum. Gibbs free energy of the system is minimum. That means equilibrium is the most stable state of the system, right? Equilibrium is the most stable state of the system. Every system wants to attain equilibrium as soon as possible. Every system wants to be at equilibrium quickly because equilibrium is the most stable state. Okay? So, can I say something like this? If reaction quotient of a particular reaction is equal to equilibrium constant, if reaction quotient is equal to equilibrium constant, can I say the system is at equilibrium at that time? At that point of time, the system is at equilibrium. Can I say something like that? Yeah? Perfect. Similarly, if for example, if QC value is less than Kc, if for a reaction QC is less than Kc, if QC is less than Kc, what QC will does? What QC is going to do? See, it's simple. I told you, every reaction wants to attain equilibrium as soon as possible. So, every reaction wants to have its QC value to be equal to Kc. Then only the reaction will be at equilibrium. Every reaction wants to have its QC value to be equal to Kc. Then only it will be at equilibrium, correct? Now, you must be thinking, if for a reaction QC is less than Kc, I would say QC will try to increase its value. QC will try to increase its value so that it becomes equal to Kc, so that reaction comes into equilibrium, so that system is stable, right? If QC is less than Kc, then QC will try to increase its value. How QC will try to increase its value? QC will try to increase the numerator and decrease the denominator. Decrease the denominator matlab concentration of A and B should decrease. How concentration of A and B will decrease? When the reaction, when the equilibrium shifts in the forward direction. Right? Perfect. Similarly, now you tell me if QC is greater than Kc. If QC is greater than Kc, then QC will try to decrease its value. Then only it can get equal to Kc. How QC will decrease its value? QC can decrease its value only if numerator decreases. If numerator decreases, denominator increases. Numerator decreases, that means C and D concentration should decrease. C and D concentration should decrease. How C and D concentration will decrease? when the reaction goes backward. So here backward reaction is favored. Remember these three things. Remember these three things. Is it clear? Perfectly done. Perfectly done. Okay. This is something which we discussed. Backward reaction, forward reaction, equilibrium. Correct? Now a lot of people were asking about this topic, Le-Chatelier principle, which is the last topic of the chapter. Right? And after this, I'll be giving a break. Okay? Le-Chatelier principle. I'll keep it very simple. I'm not going into the details of it. I'll keep it very simple so that you can solve the questions quickly. That's my motto here. Let's not go into the details of it. So basically, look at this particular statement. What Le-Chatelier principle says. As far as this particular principle is concerned, if any change is imposed on the system at equilibrium, the equilibrium will shift in such a direction in which the effect of change is nullified. What does that mean? That means if you'll be having any reaction at equilibrium, system is maximum stable. So any reaction at equilibrium means stability is maximum. Correct? Now if you will try to do some change, if you will try to disturb the equilibrium, equilibrium is going to do exactly opposite of what you do to the reaction, so that effect of change is nullified. It's very simple. Whenever you'll be having a system which is at equilibrium basically, so system is maximum stable there, right? Now if you are going to impose some change on the system, so equilibrium is exactly going to do opposite of what you do, so that the effect of change is nullified, so that stability is restored back, right? Exactly. In short, it is tit for tat, right? Okay. So let's have a look on this a bit more in detail now. Let's have a look on it a bit more in detail. I'm telling you, I'm not going into the details. I'm not going to show you this in terms of reaction quotient, etc., etc. I'll just tell you how to remember it and how to do the questions. That's it. Let's say you've got the reaction like this. Reactants and products, they are in equilibrium. Reactants and products, they are in equilibrium, right? The first thing, let's say if I increase the concentration of reactant, or if I decrease the concentration of product, what will happen? You tell me in the chats. If I increase the concentration of reactant, equilibrium will try to decrease it. If I decrease the concentration of product, equilibrium will try to increase it, right? Let's focus on the things one by one. Wait. If I increase the amount of reactant, what will happen? Equilibrium will try to decrease the amount of reactant. How? It will make sure that the equilibrium shifts forward. Okay. Second, if you decrease the amount of reactant, equilibrium will try to increase the amount of reactant. How? It will shift the reaction backward. It will shift the equilibrium backward. Correct? Similarly, if you increase the concentration of product, equilibrium will try to decrease it. How? It will shift it backwards. If you decrease the concentration of product, equilibrium will try to increase the concentration of product. How? Forward. This is how you can remember it. This is how. This is not the exact explanation of it. Explanation is in terms of reaction quotient. But I'm not going into the details. Just remember this in short. Right? Whatever you do, I'm going to do opposite. That's it. Right? Perfect. Take a note of one thing. Any reactant or product in solid state will not shift the equilibrium if its amount is changed. If its amount is changed. So any reactant or product, for example, look at this particular reaction. Calcium carbonate solid, this is gas. If you change the amount of this solid, if you change the amount of this solid, nothing is going to happen. Nothing is going to happen. Because their active mass is unity. They are not going to change the value of QC. If QC does not change, no shift will happen. So do remember, if you will change the amount of solid, right, nothing, no shift will happen. Okay, no shift will happen. Number one. Number two, effect of change in pressure. Effect of change in pressure. This is the second term. Effect of change in pressure. On increasing the pressure, reaction will shift in that direction in which the total gaseous moles decreases. When you increase the pressure, I'm assuming this particular reaction is at equilibrium. When you increase the pressure, the equilibrium will shift in such a direction in which the total gaseous moles will decrease. In which the total gaseous moles will decrease. Only this statement you need to remember. For example, on the reactant side, how many moles you have? How many gaseous moles you have? 3 plus 1, 4. On the product side, you have 2 moles. In the forward direction, the gaseous moles are decreasing. In the backward direction, gaseous moles are increasing. Now, since the reaction is at equilibrium, if you increase the pressure, reaction is going to shift in such a direction in which the total gaseous moles decreases. Gaseous moles are decreasing in the forward direction. So, if you increase the pressure, the reaction will shift forward. It will shift forward. It will shift. Don't remember it like this, it will shift forward all the time. No. Remember it will shift in the direction in which gaseous moles decreases. In this particular reaction, gaseous moles are decreasing in forward direction. That's why it's shifting forward. In some other reaction, it can shift backward as well. Right? Simple and basic thing. Similarly, any reaction whose delta Ng value is 0. Look at this reaction. Its delta Ng is 0. On the reactant side, you have got 2 gaseous moles. On product side, you have got 2 gaseous moles. Now, moles are not changing. 2, 2, right? So, if you change the pressure, here, if you increase or decrease the pressure, nothing is going to happen. No shift will happen. No shift will happen at all. Do remember this particular scenario as well. Okay? On increasing the pressure, equilibrium shifts in such a direction in which total gaseous moles decreases. Right? The reaction whose delta Ng is 0, there will be no shift in that. There will be no shift in that. Now comes one important case. Effect of change in temperature. Effect of change in temperature. On changing the temperature, how equilibrium constant is going to change. See guys, understand. Let's say, first of all, I'm taking an endothermic reaction. This is important, understand it, okay? Let's say I have got an endothermic reaction. I have got an endothermic reaction, for example, A gives B. This is an endothermic reaction, right? Let's assume that this reaction is taking place at temperature T1. When the reaction is taking place at temperature T1, let's assume its equilibrium constant is K1. Now I'm changing the temperature of the reaction from T1 to T2. Let's assume now its equilibrium constant is K2, right? Let's assume now its equilibrium constant is K2. Initially at temperature T1, its equilibrium constant was K1. Now at temperature T2, its equilibrium constant is K2. Correct? Its equilibrium constant is K2. Now understand few things. For example, if T2 is greater than T1, what does that mean? That means I have increased the temperature. Right? If T2 is greater than T1, can you tell me T2 minus T1 value, will it come out to be positive or negative? If T2 is greater than T1, then T2 minus T1 will come out to be positive. Absolutely, right? Since the reaction is endothermic, for endothermic reactions, delta H value is positive also, right? Delta H is positive. Now you look at this particular equation. Since the reaction is endothermic, delta H is positive. It is going to be T2 minus T1. T2 minus T1 value is positive. Matlab this term is positive, even this term is positive. If this is positive, can I say the whole term is going to be positive? Right? The whole term is going to be positive. Whole term positive means log of K2 divided by K1. This value will be positive. Now you must be knowing, when is the log of x to the base 10 positive? When is it positive? When x value is greater than 1. Similarly, log of K2 by K1, when can it be positive? When K2 divided by K1 is greater than 1. That means K2 has to be greater than K1. Right? So in this particular scenario, understand, if I increase the temperature, T2 minus T1 will be positive. That means K2 will be greater than K1. So look at this particular scenario. T2 greater than T1, K2 greater than K1. So what do you think is the relation between equilibrium constant and temperature? So equilibrium constant is directly proportional to temperature, but in case of your endothermic reactions. In case of your endothermic reactions, if you increase the temperature, the equilibrium constant of the reaction is going to increase. As simple as that, right? Let me know once in the chats if everything is super clear. Similarly, we can discuss about the exothermic reactions as well. So in exothermic reactions, you can directly remember, in case of exothermic reactions, equilibrium constant is inversely proportional to temperature. For the exothermic reactions, right? For endothermic reactions, equilibrium constant is directly proportional to temperature, and for exothermic reactions, equilibrium constant is inversely proportional to temperature. That's all. That's all. That is all. Okay? Now there is one more thing. Again, I'm not going into the details. Few things which I want you guys to remember so that you can solve the questions quickly. Effect of inert gas addition at constant pressure. For example, this is the reaction. If you add the inert gas at constant pressure, what will happen? I'm again telling you, I'm not going into the details. I'm just telling you the things in such a way so that you can solve the questions quickly, because we don't have a lot of time left. Okay? What happens when we do the inert gas addition? What happens to the shift? Have a look on this particular statement. On adding the inert gas at constant pressure, the reaction shifts towards highest moles, towards more number of moles. For example, look at this particular reaction. The moles on reactant side is 1. The moles on product side is 2. So in the forward direction, moles are increasing. In the backward direction, the moles are decreasing, right? In the forward direction, moles are increasing. In the backward direction, moles are decreasing, right? Now, if you add an inert gas at constant pressure, the reaction will shift in such a direction in which total moles increases. Total moles are increasing in the forward direction. So the reaction will shift forward here. This is effect of inert gas addition at constant pressure. I want you guys to remember it directly. Okay? Its explanation will take a lot of time. I don't want to go there. Perfect? On adding the inert gas at constant pressure, reaction shifts in such a direction in which total moles increases. That's it. Reaction moves towards more number of moles. That's all. Similarly, effect of inert gas addition at constant volume. At constant volume, nothing happens. When you add inert gas at constant volume, there'll be no shift. Remember it directly as well. No shift at constant volume. No shift at all. Okay? Similarly, when you talk about the catalyst just increases. A positive catalyst, if I talk about, a positive catalyst simply increases the speed of forward and backward reaction. A positive catalyst, it just increases the speed of forward. It just increases the rate of forward and backward reaction. Nothing else. It does nothing to equilibrium constant. In presence of catalyst, equilibrium is attained in the reaction quickly. That's it. In presence of catalyst, equilibrium is attained in the reaction quickly. That's all. Nothing else. Okay? So a catalyst, it does not affect the equilibrium constant. It only changes the time taken to attain the equilibrium state. and a positive catalyst increases the rate of forward and backward reaction by equal amount, right? When you put a positive catalyst, right, it increases the forward reaction as well as backward reaction rate by equal amounts basically. So I hope you remember all these things what I told you here. Now let's do one question and after that I'll give you a break. Let's summarize this Le-Chatelier principle with the help of this particular question. Summarize it. Summarize it quickly. Predict the direction of shift of equilibrium. It is one reaction given, N2 plus 3 times H2 plus the energy. That means it's a hypothetical reaction first of all. Okay. It is endothermic, so delta H is positive. It's endothermic, correct? If more H2 is added, if you add more H2, equilibrium will try to decrease it. If you increase the amount of H2, equilibrium will try to decrease it. That means the reaction will shift forward, right? If more NH3 is added, if you add more NH3, equilibrium will try to decrease it. So, backward. A reaction is endothermic. On increasing the temperature, equilibrium constant increases. Equilibrium constant increase, that means reaction moves forward. Inert gas is added at constant volume, there will be no shift. Inert gas is added at constant pressure. On adding inert gas at constant pressure, what happens? Equilibrium shifts towards more number of moles. More number of moles means backward here. Clear? I hope this is super duper clear to everyone. So, here let's take a break and then let's start something called as ionic equilibrium. Okay? So, let's take half an hour break. Break till, what is the time? 1:30, 2 p.m. Okay. Next NEET predicted paper will be mostly on Sunday. Guys, be there everyone at 2 p.m. okay? And the ones who have not liked the session yet, the ones who have not subscribed to the channel yet, do that right now. Do that right now, okay? Chalo, I'll see you after the break. Everyone be there on time. Everyone be there on time. Guys, am I audible? Am I audible, visible to everyone? Let me know quickly in the chats. Am I audible, visible to every one of you quickly? Quickly. Am I perfectly audible, visible? Say yes or no in the chats quickly. It's going to be ionic equilibrium, the most phobic chapter. Right? No, I did not have my lunch. I just had tea. That's enough for me. Are you guys done with your lunch, everything? Are you guys done with your lunch and everything? Call up everyone because this is the most important chapter, okay? Most important chapter. I think everybody came, huh? PDF of this particular session will be uploaded after the session on my Telegram. I think all of you are there in my Telegram, right? I think all of you all. So do you know Tamil? I have stayed in Tamil Nadu for 5 years, but I mean, I know few basic words. Few basic words I know. It's not like everything I know. All right, I'll try to upload the PDF in lesser size. Yes, do not worry. Do not worry. Like, are you feeling confident now? I mean, with all the preparation, everything you have done, are you getting that confidence? What class on Sunday? Sunday we'll have top 30 most repeated concepts. Top 30 most repeated concepts in NEET. Most repeated concepts. It will be a combined session for physics, chemistry, biology. The session duration will be more than, 3-4 hours it will be. Top 30 concepts we'll be discussing. Those concepts which have been like frequently asked in your NEET examination. On Sunday at, are you from Kashmir? Of course, yaar. Don't I look Kashmiri? All right, so let's begin then. Yes, I'm going to do it in the way I have planned. You just do not worry. Everything will be properly done with you. Okay? So chalo, let's start with the ionic equilibrium now. Okay? Let's start with something called as ionic equilibrium. And we'll be again starting from the basics only. Perfect. So dear students, the first and the basic topic in ionic equilibrium which you must know, what is that? That is electrolyte. What is an electrolyte? How do you define the electrolyte? Any such substance which on dissolving in water dissociates into its ions. Any substance which you put into water, that substance in water dissociates into its ions. That's something which you call as electrolyte. Okay? Electrolyte is that substance which on dissolving in water dissociates into its ions. Right? Now, if I talk about electrolytes basically, we classify electrolytes into two types. One is strong electrolyte, one is weak electrolyte. Now the point is, what are strong electrolytes and what are weak electrolytes? Okay? What are strong electrolytes and what are weak electrolytes? Strong electrolytes are the ones which are completely dissociated into their ions when we put them into water. These are completely ionized. These are completely dissociated into its ions, into their ions, right? For example, you have got an electrolyte AB. You are putting it into water. Now, if it is completely getting dissociated, 100% getting dissociated into its ions, you'll be calling this electrolyte as a strong electrolyte, as simple as that, right? Do remember, in case of strong electrolytes, the degree of ionization, the degree of dissociation, that's equal to 1. For strong electrolytes, degree of ionization is 1. What are the examples of strong electrolytes? All the strong acids, all the strong bases, and even the water-soluble salts. They are the examples of the strong electrolytes. All the strong acids, all the strong bases, all the water-soluble salts, they are the examples of strong electrolytes. That means when you put them into water, they dissociate 100% into their ions. Now you must be thinking, what are these water-soluble salts? What are the examples of the water-soluble salts? It is basically the general salts of alkali metals. Whatever general salts of alkali metals are there, number 1. Salt of NH4 positive, salt of NO3 negative. These are all the salts which are basically the water-soluble salts. And water-soluble salts, generally, what they are? They are considered as strong electrolytes. So again, I'm telling you, all the strong acids, all the strong bases, all the water-soluble salts, right? All the water-soluble salts. What are the examples of strong acids? For example, you have got HCl, right? Strong base, for example, you have got NaOH. Water-soluble salts, all the general salts of alkali metals, even the salt of NH4 positive. What is the salt of NH4 positive? For example, you have got NH4Cl. NH4Cl is the salt of NH4 positive. Salt of NO3 negative. What is the salt of NO3 negative? Let's say I have got NaNO3. It is a salt of NO3 negative, right? All these are basically the examples of what? The strong electrolytes, which on dissolving in water, dissociates completely into its ions. Okay? Very simple and basic thing. And one important thing, the degree of ionization for the strong electrolytes, it's taken as 1. What about weak electrolytes? Weak electrolytes are not 100% ionized. They are not 100% ionized. They are partially ionized when we put them into water, right? Their degree of ionization, it will be definitely greater than 0, but it will be less than 1. The degree of ionization, it will be definitely greater than 0, but it will be less than 1, right? Now the examples, all the weak acids, all the weak bases, they are considered as weak electrolytes. What are the examples of weak acids? For example, you have got CH3COH. For example, you have got HCOH, formic acid, acetic acid. These are the weak acids, right? Similarly, weak bases, you have got NH4OH. It's a weak base. It's a weak electrolyte. It won't get 100% dissociated into its ions. Okay? Similarly, all the sparingly soluble salts, this is something which I'll teach you afterwards. All the sparingly soluble salts, they are again considered as weak electrolytes. And the examples of sparingly soluble salts are AgCl, PbCl2, Hg2Cl2, Ag2SO4. These are all the examples of sparingly soluble salts. And sparingly soluble salts, again, they are considered as the weak electrolytes. And weak electrolytes, they are partially ionized in water, right? Their degree of dissociation is greater than 0, less than 1. There is one very important point from where I'm going to start the chapter. I did not start this chapter yet. Now I'm going to start the chapter. And I'll be starting the chapter from a very important statement. All the weak electrolytes, they will remain in equilibrium with their ions. All the weak electrolytes, they will remain in equilibrium with their ions. From this particular statement, we are starting the chapter. Whenever you see a weak electrolyte, be it weak acid, be it weak base, right? When you put them into water, they are going to remain in equilibrium with their ions. Important. This is very important. Okay? This is very important. Now guys, let's start the chapter in detail. This was all the basic stuff. Okay? Now we are starting. The first topic here is ionization constant of a weak electrolyte. ionization constant of a weak electrolyte. What is ionization constant of a weak electrolyte? How do we calculate it? Let's have a look. This is something which is very, very, very important. This is something which is very important. For example, I have got a weak electrolyte AB. I have got a weak electrolyte AB. I'm introducing in water. I'm introducing in water. Right? Now this weak electrolyte is going to remain in equilibrium with its ions, and its ions are A positive aqueous plus B negative aqueous. A positive aqueous, B negative aqueous. Wait. You want me to open the door?
Open it.
Is there some prank?
Open.
Are you going to do something first? Tell me.
No. I'm just coming.
Guys, should I open the door? It's Ambika ma'am. But I'm really worried she's going to do something. It might be a revenge.
But I'll do it for sure.
It might be a revenge.
No. Revenge I'll take soon, but not now. Open it.
Are you sure?
Yes.
100%. You're not going to do anything.
Nothing.
Show me your hands first.
Nothing.
Guys, wait. Just 2 minutes.
Nothing. Arey, you're so scared, है ना? Don't worry, I'll take revenge, but not now. Now तो you're prepared, na? Not now.
हाथ दिखा पहले.
नहीं है, see. How are you, everyone? Hello. Is he teaching you nicely? You know, yesterday I taught him how to teach chemistry. Tell them. Why are you so scared? Just wait. Now you are prepared. Don't worry. Now you are just prepared. Now he's just prepared. So I'm not going to do anything, but I'll take revenge. See, I nothing.
Okay,
See, he's so scared. Women power. He's so scared. Isn't it? Don't worry. I'm going to take the revenge because I was not aware that he's going to put that video there. Don't worry, I'll take the revenge. Nari Shakti Amar Rahe. Nari Shakti Amar Rahe. है ना? So is he teaching you nicely? Yesterday I taught him how to teach chemistry.
Yeah,
How
taught
to-
me how to teach chemistry.
How to teach chemistry. See? है ना? Don't worry, I'll take the revenge. But your number of likes are less. You know, mine were too much. And even, you know, they subscribe the channel. Subscribe it. He's awesome in teaching. I am teaching him. I'm telling him that how to write, how to draw the diagram. Right? I'm telling him everything. Don't worry.
Correct. Yes, she's right.
Anna, now he's so
I
scared.
I
Today he's
swear on
saying,
her, she's right.
see, today he's so scared. He's like, you don't have anything? But I'll take revenge. You just wait and watch.
जलवा है हमारा यार.
No jalwa. Please, guys. देखा? He's scared. He's literally scared. I'm so happy. Yes, एक नारी सब पे भारी. He is the best. He is the best. But I'm teaching him how to teach. You know? How to teach.
Yeah.
है ना?
Yeah.
So guys, if you're new to our
Psychology.
channel, to subscribe that. He doesn't even know that it is physiology, not psychology. See? See?
Someone is asking कैसा revenge.
Kaisa revenge, you'll see. Check the shots.
अरे,
Munna
don't
bhaiya.
यार, seriously, please.
ऐसे कैसे please? Just wait and watch.
Oh. She's gone. She died. She passed away. अरे दरवाजा तो बंद कर ले. Just a second. Wait, guys. Okay, should we start now? She's one mad girl. So should we start, people? Ready again? Okay. All right, the ones who have not subscribed to the channel yet, do subscribe it right now, okay? Chalo, let's move on. Let's see. So now we are going to start the ionization constant of weak electrolytes. So basically, what I have done, I have taken a weak electrolyte, AB, introduced into water, and you know, the weak electrolytes, they remain in equilibrium with their ions. Point number one. Point number two, Initially at time t is equal to 0, let's assume the concentration of weak electrolyte was C. This is 0, this is 0. Let's assume the degree of ionization is alpha. Now at equilibrium, if I ask you, at equilibrium, when equilibrium is established, at equilibrium, if I ask you, what is the concentration of this AB left in the container? The way we used to do in chemical equilibrium, here also we have to do the same, right? So the initial concentration of the electrolyte was C. Now from C, C alpha is going to ionize. So we'll be left with C minus C alpha. This is the concentration of the weak electrolyte left in the container at equilibrium, right? 1 mole of reactant gives 1 mole of A positive. So from this C alpha, you are again going to get C alpha only. Similarly, 1 mole of AB gives 1 mole of B negative. So from C alpha, you get C alpha. So what did I get till now? Just tell me, what did I get? I got the concentration of AB aqueous present in the container at equilibrium. I got the concentration of AB positive present in the container at equilibrium. I got the concentration of B negative present in the container at equilibrium. Since the reaction is at equilibrium, and I got the concentration of each species, each reactant and product present in the container at equilibrium, right? My dear students, do you know how to write the expression for Kc? Absolutely, you should be knowing now. Expression for Kc. What is Kc? It used to be equilibrium constant. Now here, instead of Kc, I'll be writing it as Ki. It's same only. Kc, Ki, it's same. It is just the terminology is different. It is just the terminology is different. This Ki, now I'll be calling it as ionization constant. I will be calling it as ionization constant for the weak electrolyte. And how do I write this? Its expression? The similar way as we used to write the expression for Kc. We'll be starting with the product. It's going to be concentration of A positive at equilibrium raised power stoichiometric coefficient. Concentration of B negative at equilibrium raised power stoichiometric coefficient divided by concentration of AB at equilibrium raised power stoichiometric coefficient. That's 1. I hope it's clear till here. Now, dear students, if I ask you one thing, from here the things will start, and understand them properly, okay? Since I need to write the expression of Ki, which is the ionization constant of weak electrolyte, it's going to be equal to A positive concentration at equilibrium is C alpha, B negative concentration at equilibrium is C alpha, and AB concentration at equilibrium is C minus C alpha, correct? So from here you can easily calculate Ki value. It's going to be C square alpha square divided by C multiplied by 1 minus alpha. So 1C gone. So Ki value from here, I got to know it's C alpha square divided by 1 minus alpha. This is the first relation which I want you guys to remember. This is how you write the expression of Ki. Number one. Number two, understand properly. Dear students, after writing the expression of Ki, now we are going to assume certain things. After writing the expression of Ki, now we are going to assume certain things. Let's assume the alpha value, the degree of ionization of weak electrolyte is less than 0.05. Remember this number. Let's assume the degree of ionization of the weak electrolyte is less than 0.05. So do remember, if we assume that alpha is less than 0.05, that means instead of 1 minus alpha, you can only write 1. You can neglect this alpha from here. You can neglect this alpha. Let's assume alpha is less than 0.05. That means instead of 1 minus alpha, you can just write 1. And after doing this, what we'll get? This is something very important, guys. Okay, so focus on properly. So focus on this properly now. Since I've assumed alpha value to be less than 0.05, so instead of 1 minus alpha, we are only going to write 1. Now I'm going to write the expression again. Now it's going to be Ki is equal to C alpha square, and here alpha is going to be under root of Ki divided by C. Alpha is going to be under root of Ki divided by C. So in the question, we will be given with Ki value. We will be given with the C value. After putting these values here, you'll be getting the value of alpha. And if alpha value actually comes out to be less than 0.05, after putting the values, if the alpha value after solving comes out to be actually less than 0.05, that means whatever assumption we have done here, that's absolutely right. Otherwise, our assumption would be wrong. Is it clear? Is it clear? And once you get the value of alpha from here, once you get the value of alpha, if they ask you to calculate the concentration of A positive at equilibrium, then you can say the concentration of A positive at equilibrium, that is C alpha. C value will be given to you and alpha value you have calculated, so you can calculate easily the concentration of A positive. Similarly, if they ask you to calculate the concentration of B negative at equilibrium, it's again C alpha. C value is given to us, alpha we have calculated, so we can easily calculate B negative concentration. Yes? Right? Now, let's utilize the same concept in the questions. Let's see what kind of questions can be asked here. Have a look. Let me show you one question. Let me show you one question. Understand properly what I'm going to say. Calculate the concentration of each ion at equilibrium for 0.1 molar solution of weak electrolyte AB. So as per the question, again, I'm taking the weak electrolyte AB. And you must be knowing this weak electrolyte, it remains in equilibrium with its ions. And its ions are A positive aqueous and B negative aqueous. Right? Perfect. Now, the first question says take the Ki value as, the first question says take the Ki value as 10 raised power minus 5. Alright, let me take it as 10 raised power minus 5. Now, dear students, let's say initially the concentration of AB, which I'm denoting with C, that's given to us as 0.1 molar. Concentration of electrolyte, this is going to be 0, this is going to be 0. Now at equilibrium, you already know this is going to be C minus C alpha, this is going to be C alpha, and this is going to be C alpha. Now dear students, if I write the expression for Ki, you know it's C alpha square divided by 1 minus alpha. Few minutes back only we discussed this, right? Few minutes back only we discussed this. Now after this, what I told you to do, now it's going to be the time for the assumption. Let's assume alpha value is less than 0.05. So if this is the case, that means instead of 1 minus alpha, I can write 1. Instead of 1 minus alpha, I can write 1. Now dear students, if instead of 1 minus alpha, you can write 1, so you got something like this. Ki is equal to C alpha square. And from here, you can get the value of alpha. Alpha is again going to be under root of Ki divided by C. Now you tell me, what is the value of Ki given to us? Ki value given to us is 10 raised power minus 5. C value is 10 raised power minus 1. So it's basically going to be under root of 10 raised power minus 4, which comes out to be 10 raised power minus 2. Now look at this value of alpha which we got. Look at this particular value of alpha which we got. We got the alpha value as 10 raised power minus 1. Sorry, 10 raised power minus 2, which is 0.01. Since you got the value of alpha, now check basically whether this alpha is actually less than 0.05 or not. Yes, it is less than 0.05. That means whatever assumption we have done here, that's absolutely right. So this is the actual value of alpha. This is the actual value of alpha, right? So if this is the actual value of alpha, what are we supposed to calculate? Calculate the concentration of each ion at equilibrium. So basically, we are supposed to calculate the concentration of A positive at equilibrium, and concentration of A positive at equilibrium is C alpha. Concentration of B negative at equilibrium is C alpha. So I must say concentration of A positive is equal to the concentration of B negative, and both are equal to C times alpha, and C value is given to me as 10 raised power minus 1. Alpha value we got to know as 10 raised power minus 2. So the answer of the question is going to be 10 raised power minus 3 molar. This is basically going to be the concentration of each ion present in the container at equilibrium. I'm sure it's clear to everyone. Quickly let me know in the chats with the thumbs ups. Quickly guys. Quickly everyone with the thumbs ups if it is clear. Quickly people with the thumbs ups, you got the concept? All right, wonderful. Perfect. Let's do one more question of the similar pattern, or before the question, let's do one more thing. What are the examples of the weak electrolytes generally? What are the examples of the weak electrolytes generally? Weak acid, weak bases. These are the examples of the weak electrolytes, right? You know it. Now, for example, I'm taking a weak acid. Now I'm taking a weak acid. I'm taking a weak acid as HA. This is weak acid. If it is weak acid, it's going to remain in equilibrium with its ions, and its ions are H positive aqueous plus A negative aqueous. Right? Let's assume its initial concentration is C. This is 0. This is 0. So at equilibrium, it's going to be C minus C alpha. This will be C alpha. This will be C alpha, right? Now, till now, particularly in case of weak electrolytes, we used to write Ki. But remember, when the weak electrolyte is weak acid, then Ki is replaced by Ka. It is just the terminology is different, rest the meaning is same, right? And what do we call this Ka as? Ka I'll be calling as ionization constant, or you can call it as dissociation constant of what? Of a weak acid. And what will be its expression? The same expression which we got, C alpha square divided by 1 minus alpha, right? C alpha square divided by 1 minus alpha. Correct, people? Correct? Simple and basic. Now, after this, what do we do? I've told you a few minutes back only. After this, what do we do? Let me just write it again so that I get some space here. Just a second. I told you for Ki, we use the term Ka now. It's going to be C alpha square divided by 1 minus alpha. Now, our assumption is going to be the same. Let alpha value is less than 0.05. Therefore, instead of 1 minus alpha, I'm going to write 1. And after writing 1, then you can again do one thing. You can write Ka is equal to C alpha square, and alpha value you can calculate from here, which is going to be under root of Ka divided by C. Now, there is something which I need to tell you. See, guys, as you can see, Ka and alpha, they are directly proportional to each other. More the value of Ka for the acid, definitely more will be the value of alpha. More alpha means more degree of ionization. What does that mean? That means this acid has dissociated, it has ionized more into the ions. If this acid has ionized more into its ions, in the container, will the concentration of H positive be more or less? The concentration of H positive in the container will be less. More the concentration of H positive, definitely more is going to be the acidic strength. More acidic strength means less will be the value of the pH. Do remember this particular statement. I hope it's clear to everyone, right? Similarly, dear students, if I take the weak electrolyte as weak base, for example, I am taking the weak base BOH. This is our weak base. So this is a weak base, that means it's a weak electrolyte. So it is going to remain in equilibrium with its ions, and its ions are B positive aqueous plus OH negative aqueous. Correct? Again the same procedure. So I'm writing the final scenario. Kb is going to be C alpha square divided by 1 minus alpha. Since I'm taking weak base into consideration, so instead of Ki, I'm writing Kb. Right? Now again the assumption, let alpha be less than 0.05. So instead of 1 minus alpha, I'm only going to write 1. Okay? So Kb hence is equal to C alpha square. So alpha is going to be under root of Kb divided by C. The same procedure. Perfect. Now you tell me one thing. More the value of Kb for a base, more will be the value of alpha. More alpha means more ionization. More ionization means more OH negative concentration in the container, and more OH negative concentration means more is going to be the basic strength. More is going to be the basic strength. More is going to be the pH. Right? So do remember these few things as well. Right? Let me know once in the chats if it is clear. Let me know once in the chats if it is clear. Let's try to do one question. Calculate the concentration of H positive of 0.05 molar CH3COH. So basically, as per the question, we have taken a weak acid CH3COH. So how it's going to get dissociated? It is going to get dissociated in this manner. CH3CO negative aqueous plus H positive aqueous. This is how it's going to get dissociated, right? Initially, at time t is equal to 0, its concentration C is given. That's 0.05 molar. So this will be 0 and this will be 0. Now at equilibrium, it's going to be C minus C alpha. This will be C alpha. This will be C alpha. The same procedure. Now dear students, since it's a weak acid, so write the expression for Ka. Ka expression is going to be same, C alpha square divided by 1 minus alpha. Now let's take our assumption, let alpha be less than 0.05. So instead of 1 minus alpha, I can only write 1, right? Instead of 1 minus alpha, I can only write 1. Okay, now dear students, have a look. Instead of 1 minus alpha, I'm only writing 1 here now. So Ka, I can say, is equal to C alpha square, or I can say alpha is equal to under root of Ka divided by C. Correct? Now tell me what is the value of Ka. Ka value is given to us as per the question, which is 1.25 into 10 raised power minus 6. C value is given to me 0.05. Just solve it a bit. It's going to be under root of, this is 1, this is 25 times. So it's under root of 25 into 10 raised power minus 6, which comes out to be 5 into 10 raised power minus 3. So alpha is 5 into 10 raised power minus 3. Alpha is 5 into 10 raised power minus 3, right? So if alpha is 5 into 10 raised power minus 3, the concentration of H positive, which I was supposed to calculate as per the question, the concentration of H positive in the container, which is basically C times alpha. C is given to me as 0.05, which means 5 into 10 raised power minus 2. Alpha value I got to know as 5 into 10 raised power minus 3. So the final answer of the question is going to be 25 into 10 raised power minus 5 molar. This is the concentration of H positive in the container, which we were supposed to calculate. Say yes or no in the chats if it is clear. Say yes or no in the chats if it is super clear to everyone. Quickly. Quickly, guys, everyone. Everyone means everyone. Quickly in the chats. Quickly in the chats, everyone. Everyone in the chats, quickly. Perfect? Wonderful. Look at one more example. Look at one more question. Have a look properly how to solve these. Calculate ionization constant of a weak base. Ionization constant of weak base means Kb, right? Ionization constant of a weak base means Kb. So the weak base which we are given with, that's NH4OH. Now you tell me how this weak base is going to go dissociated. It will undergo dissociation as NH4 positive aqueous plus OH negative aqueous. This is how it will undergo dissociation. Correct? Now dear students, initially the concentration of NH4OH, that's C, it's given to me as 0.05 molar. The concentration of NH4OH aqueous, it's given to me, right? Now this is going to be 0, this is going to be 0. If I ask you at equilibrium, how much will be left? C minus C alpha. This will be C alpha. This will be C alpha. Now if I ask you to write the expression for Kb, you know it's going to be C alpha square divided by 1 minus alpha. Now it's going to be again our assumption. Again it's going to be our assumption. Right? Let alpha value be less than 0.05. Therefore, instead of 1 minus alpha, I can only write 1. Okay? Therefore, my Kb becomes C alpha square and alpha becomes under root of Kb divided by C. Under root of Kb divided by C. Now, you tell me what is the Kb value which we are given with? Oh, wait. We have to calculate Kb, I guess, yeah? Just a second. Just a second. We don't have to calculate alpha. We have to calculate Kb. All right. So, since we have to calculate Kb, right? And Kb, you know, it's C alpha square divided by 1 minus alpha. There is one thing which is given in the question. The question is, if the concentration of OH negative, in the solution, guys, just a second, I think we have taken the value wrong. If the concentration of OH negative in the 0.1 molar solution, wait, this is not 0.05, this is 0.1. Oh my God. Just a second. Concentration of this electrolyte, that's given to me as 0.1 molar. Okay. Now, as per the question, concentration of OH negative in the solution, that is given to me as 0.05. But you must be knowing, concentration of OH negative in the solution, that's basically C times alpha, which is equal to 0.05. So alpha from here can be calculated as 0.05 divided by C, and C is nothing, that's 0.1. So the alpha value is coming out to be 0.5. Alpha value is coming out to be 0.5. Guys, just have a look on one thing. You got the value of alpha 0.5. Is it less than 0.05? Check it out. Is it less than 0.05? No, it's not less than 0.05. If it is not less than 0.05, can we do the assumption? Can we do the neglection? Can we say 1 minus alpha is equal to 1? No. Here you cannot neglect alpha. So you have to keep this alpha in the denominator only. You cannot neglect alpha here. I hope you got it. So now get the Kb value. Kb is equal to C. C is 0.1. Alpha square. Alpha square. Alpha is 0.5. Cos square divided by 1 minus alpha. 1 minus 0.5. Comes out to be 0.5. 1.5. 1.5 cancel. So the final answer is 0.05. This is the value of Kb. Got it? Got it everyone quickly? Got it? Is it super clear? Is it super clear to everyone? Perfecto. There is something called as Oswald's dilution law. Oswald's dilution law. What is this Oswald's dilution law is all about? Oswald's dilution law simply tells you one thing. What is that? On dilution, the degree of ionization, of a weak electrolyte increases. Upon dilution, the degree of ionization of a weak electrolyte increases. That's all. That's all. So what it means and how it came. Have a look. Let's say you've got a weak electrolyte AB again, and this weak electrolyte AB is in equilibrium with its ions, and its ions are A positive aqueous plus B negative aqueous, correct? Do you agree with this? Yes. Initially this is C, this is 0, this is 0. At equilibrium, C minus C alpha, this is C alpha, this is C alpha. Now write the expression for Ki. Ki is going to be C alpha square divided by 1 minus alpha. Let's do the assumption. Let's assume alpha is less than 0.05. If alpha is less than 0.05, at that point of time, what am I going to say? At that point of time, I can say Ki is equal to C alpha square, and alpha is just going to be under root of Ki by C. Alpha is equal to under root of Ki by C. Now you tell me one thing. What is the C here? C stands for concentration. Concentration means number of moles per unit volume, right? Now people, one more thing. This electrolyte, I have introduced the electrolyte in the container basically, right? And that container already had water in it. Introduction of electrolyte in the container already having water in it. It dissociated into its ions. That's something which happened. Now if I do one thing, if I put more solvent here is water. If I put more water into the container, that means I'm doing the dilution. Upon dilution, what is going to happen? If I put more solvent, more water into the container, can I say volume of the system will increase? Entire volume of the system will increase. If volume increases, can I say concentration will decrease? And if concentration decreases, it is inversely proportional to alpha. If concentration decreases, that means alpha value will increase. And what is alpha? That's degree of ionization. That's what I told you, right? Upon dilution, degree of ionization of a weak electrolyte increases. And if you continuously keep on diluting, the degree of ionization of a weak electrolyte will keep on increasing, and a time will come, that's what we call as infinite dilution. At infinite dilution, this weak electrolyte would have got 100% ionized and alpha would have attained its maximum value. That means at infinite dilution, your weak electrolyte will be behaving now like a strong electrolyte. Got it? Quickly in the chats if it's clear. Is it clear to everyone, people? Tell me quickly. So upon dilution, the degree of ionization of a weak electrolyte increases. And if you continuously keep on diluting, what happens? If you continuously keep on diluting, there will be a stage when your weak electrolyte will start behaving like a strong electrolyte. Right? Perfect. Yes or no in the chats? Everyone? Perfect, guys. Wonderful. Let's move on. Let's move on. There is one very, very, very important concept. Very important concept. Common ion effect. It's almost used everywhere in equilibrium. Common ion effect. Understand this concept carefully. And remember what I say. Okay? Remember what I say in this. Yes, Oswald's dilution law is applicable to weak electrolytes only. All right, have a look now. See what this common ion effect is all about. If we look at its statement, the suppression of degree of ionization of a weak electrolyte, the suppression means decrease, right? Suppression means decrease. The decrease in the degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added to it. Have a look what it means. For example, imagine that you have got a weak electrolyte. Let's say you are taking a weak electrolyte, CH3COH, in the container. And you know, this weak electrolyte will be it will be in equilibrium with its ions, and its ions are CH3CO negative aqueous. With this, you are going to write the H positive aqueous. This is the weak electrolyte which you have taken in the container. Number one. It is a weak electrolyte which you have taken in the container. I'm assuming alpha value for this weak electrolyte is already less than 0.05. Alpha value for this weak electrolyte is already less than 0.05. Let's assume its concentration initially was C. This will be 0, this will be 0. Now at equilibrium, it's going to be C minus C alpha. This will be C alpha and this will be C alpha. Absolutely. Right? Right, people? Now, the container in which CH3COH is in equilibrium with its ions. In the same container, I'm introducing a strong electrolyte HCl. Now this HCl, it is going to get completely dissociated into its ions because it's a strong electrolyte. It's going to get dissociated completely into its ions, H positive and Cl negative. Let's say its concentration was C1, this was 0, this was 0. Now it's completely getting dissociated. So now this will be 0 because it's completely getting dissociated, right? It will be 0. 1 mole gives 1 mole. From C1 you get C1. This is also going to get C1, right? Now look at this particular scenario which we have. In the same container, we have got a weak electrolyte and a strong electrolyte. Both are having one ion common. Whenever you see such kind of a scenario in which you have got a weak electrolyte and a strong electrolyte, present in the same container, having one ion in common, you are going to use the common ion effect. Now what common ion effect says? What this common ion effect says? Understand what it says. Since you have introduced HCl, that means in the container you are increasing the concentration of H positive, right? In the container you are increasing the concentration of H positive. Already this particular reaction was in equilibrium. Now in the same container wherein CH3COH was in equilibrium with its ions, right? Now you are introducing this HCl. So you are increasing the concentration of H positive. So what Le-Chatelier will do? What Le-Chatelier is going to do? As per Le-Chatelier principle is concerned, if you increase the amount of products, equilibrium will try to decrease it. Since you are introducing HCl, you are increasing the H positive concentration. So equilibrium will make sure that H positive concentration decreases. So it will make sure that this particular reaction shifts in the backward direction. It will make sure that this particular equilibrium shifts in the backward direction, right? What will happen due to that? If this particular reaction shifts in the backward direction, can I say the degree of ionization of this weak electrolyte will further decrease? It was already less than 0.05. Now due to the introduction of this strong acid, this particular reaction is shifting in the backward direction, right? So I would say the degree of ionization of weak electrolyte, has it increased or decreased? It has decreased, right? That decrease in the degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added, this particular decrease, this particular suppression in the degree of ionization of a weak electrolyte is something which we call as what? That's something which we call as common ion effect. Yeah? Got it? Got it? Now people, you tell me one thing. Just tell me one thing. If I ask you, in the final solution, what is going to be the H positive concentration? From this electrolyte, H positive concentration was C alpha. From this electrolyte, H positive concentration is C. So total H positive concentration would have been C1 plus C alpha. Total H positive concentration would have been C1 plus C alpha. One more thing. Already alpha value was less than 0.05. Now due to backward reaction, alpha value further decreased. So you can neglect alpha wherever you want to, because it's confirmed now alpha value has decreased. So instead of C1 plus C alpha, you can only write C1. You can only write C1. Now talking about this weak electrolyte, if you want to write its ionization constant is going to be concentration of CH3CO negative, multiplied by concentration of H positive divided by what? Divided by concentration of CH3COH. Correct? Now this Ki can be written as concentration of CH3CO negative is C alpha, concentration of H positive is just C1, concentration of CH3COH is C minus C alpha. So take C as common, 1 minus alpha. C cancel. So Ki is equal to C1 alpha. Instead of 1 minus alpha, you can anyways write 1 now. Right? So from here, you can calculate alpha. Alpha will be equal to alpha will be equal to Ki divided by C1. Alpha will be equal to Ki divided by C1. This is not the old alpha. This is the new alpha. This is not the old alpha. This is the new alpha. This is the alpha after this suppression is done. This is the alpha after this decrease in the ionization of weak electrolyte is done. I hope you got it. So do remember, whenever you see a strong acid, weak acid in the same container, the alpha value after the common ion effect is done, the alpha value will be always calculating as Ki divided by C1. Ki divided by C1. Ki is the ionization constant of weak acid, and C1 is the concentration of common ion which is coming from strong acid. C1 is the concentration of common ion which is coming from the strong acid. C1 is the concentration of common ion which is coming from strong acid. So let me write it like this. You know alpha now we got to know as Ki divided by C1, right? Or you can write it's going to be Ki, ionization constant of weak acid, divided by. What is C1? What is C1 here? C1 is basically the concentration of common ion coming from strong acid. Concentration of common ion coming from strong electrolyte. This is how you are going to calculate alpha from now onwards in case of what? In case of your common ion effect, right? At the same time, if they ask you about what is the common ion concentration in the final solution, common ion is your H positive. Common ion concentration in the final solution, directly you can write C1. So from this particular statement, what is C1? C1 is actually the concentration of common ion coming from the strong acid. So can I say the entire common ion concentration is governed by the strong electrolyte? Yes, this is one more important statement. Entire common ion concentration is decided by the strong electrolyte. Strong electrolyte is the one which decides the entire common ion concentration. Okay, let's try to do one question of this so that you can understand it properly. One question I'm going to give you. Just a second. Just a second. Okay. Well, this is not only one question, these are two questions. This is not one question, these are two questions. Someone is saying, sir, I could not understand the common ion effect. Just take the video a little back. It will be automatically repeated, okay? Alright people, look at this particular scenario now. Calculate the concentration of each species at equilibrium in an aqueous solution containing. The first question is we have got a solution in which you have got NH4OH aqueous, which is a weak base. That means it's going to remain in equilibrium with its ions. Its ions are NH4 positive aqueous plus OH negative aqueous. Right? NH4 positive aqueous plus OH negative aqueous. Now the first question says initially the concentration here is 0.1 molar. This is 0, this is 0. Degree of ionization is alpha. Now at equilibrium, if I ask you, what will be the concentration left? C minus C alpha. This will be C alpha. This will be C alpha. Finally, if I ask you, Kb will be equal to C alpha square divided by 1 minus alpha, right? If I do the assumption, let alpha be less than 0.05, then instead of 1 minus alpha, I can write only 1. I can only write 1, right? Now people, at the same time, now I can say your Kb is nothing, it is just C alpha square, and from here alpha will be just equal to under root of Kb divided by C, correct? What is the value of Kb that's given to us? Kb value is given to us as under root of, so it is 1.8 into 10 raised power minus 5. C value is 0.1. C value is 0.1. Do remember from now onwards, alpha is equal to under root of 1.8. This value frequently you will have to use here. Under root of 1.8 is nothing, it is just 1.34. 1.34. This will be 10 raised power minus 4, ka root is 10 raised power minus 2. So alpha value you got to know as 1.34 into 10 raised power minus 2. Correct? Calculate the concentration of each species at equilibrium. So concentration of NH4 positive and OH negative we have to calculate. Concentration of NH4 positive will be equal to concentration of OH negative, and both are equal to C times alpha. C value is nothing, it is 10 raised power minus 1. Alpha is 1.34 into 10 raised power minus 2. So from here you got the concentrations of each ions, which is 1.34 into 10 raised power minus 3 molar. This is the concentration of each ion in the container at equilibrium. This was the first question. No common ion effect till here. No common ion effect till here. Right? No common ion effect till here. Just remember this alpha value. Remember this alpha value. Now comes a question. Now the question comes, if 0.1 molar NH4Cl along with NH4OH. So already in the container you had NH4OH whose alpha was this much. Now in the same container you are introducing 0.1 molar NH4Cl. After the introduction of NH4Cl, what will happen to the concentration of each ion? How will you get it? How will you get it? See guys, have a look. Have a look. First question was done, right? Now talking about the second question. See, till here everything is same. I'm just erasing all this. So alpha value of this weak acid we got to know a few minutes back. We solved it, 1.34 into 10 raised power. What was it, 10 raised power minus 3 or minus 2? Alpha value, how much we calculated? Can you tell me alpha? How much we calculated? How much was it? How much was the alpha value? Was it 10 raised power minus 3 or minus 2? Can you tell me quickly? Ten raised power minus 2, huh? Okay. 10 raised power minus 2. Now comes the question. The container in which you have got NH4OH, which is in equilibrium with its ions, in the same container you are going to introduce NH4Cl. You are going to introduce NH4Cl. Now tell me whether NH4Cl is a strong electrolyte or weak electrolyte. NH4Cl, it is a salt of NH4 positive. Salts of NH4 positive and salt of NO3 negative. They are all the water soluble salts. I told you in the beginning. And all the water soluble salts are considered to be strong electrolytes. You know it, right? So it's a strong electrolyte. It would have gone completely dissociated as NH4 positive and Cl negative. Correct? Let's assume its concentration is C1. You know it. And C1 value is given 0.1 molar. Its concentration is given. This is going to be 0. This is going to be 0. Now it will be getting 100% dissociated. So this is 0. This is C1 and this is C1. Correct? Now dear students, you tell me one thing. In the same container, we have got a weak electrolyte and a strong electrolyte, and both are having one ion in common, which is NH4 positive. Can you tell me what will be the net common ion concentration? C alpha plus C1. C alpha plus C1. Can I say this is the scenario of common ion effect? Common ion effect is going to operate here. Can I say common ion effect is going to operate here? Absolutely. Weak electrolyte, strong electrolyte, both having one ion in common. So common ion effect is going to operate. So this upward reaction, it will shift backwards, due to which this alpha will decrease. Due to which this alpha is decrease, it will decrease. So instead of C1 plus C alpha, Alpha was already less than 0.05. As you can see, it was already less than 0.05. Now it would have further suppressed. So you can neglect alpha wherever you want. So instead of C1 plus C alpha, you can only write C1. Got it? So the first thing which I got till now, that is the concentration of NH4 positive, which is the common ion concentration. As I told you already, common ion concentration is entirely decided by the strong electrolyte. So you could have directly written it as C1, and C1 value already you know, that's 0.1 molar. This is the net common ion concentration in the container. Right? Okay. Similarly, what else do we need? Concentration of OH negative. Alright, one more thing. If I want the new alpha value will be under root of Ki divided by C1. Few minutes back only we discussed. Ki means Kb here. How much is Kb? 1.8 into 10 raised power minus 5. C1 value is 0.1. So the value is 1.8 into 10 raised power minus 4. This is the new alpha value. Old alpha value was 10 raised power minus 2. Now due to common ion effect, you check whether alpha has increased or decreased. Alpha has decreased. It's 10 raised power minus 4 now due to common ion effect. Alpha has decreased. Alpha has decreased, right? This is the new alpha value. So the concentration of OH negative in the container will be C times alpha. Here it's C times alpha, and C value is given to be as 10 raised power minus 1. Alpha value is equal to 1.8 into 10 raised power minus 4. So it's going to be 1.8 into 10 raised power minus 5 molar. This is the concentration of OH negative in the resulting solution. Let me know once in the chats if it's clear. Let me know once in the chats if it is super duper clear. Quickly. Can you let me know the answer of this question without even solving it? I just want to see how brainy you guys are. And the ones who have not subscribed to the channel yet, please do subscribe to the channel here. This is not done. Let's make it 17K right now. It's 16.9, right? Let me check. Let me check. Yeah, it's 16.9K and 1.7K likes. So just increase it right now. Increase it right now quickly. The ones who have not done yet. So majority has already come up with the answer. Calculate the concentration of H positive. If 0.1 molar HCl, strong electrolyte, is added in an aqueous solution containing 0.1 molar CH3COH. So in the same container you have got CH3COH, and with the CH3COH you are introducing HCl. Correct? So what is the common ion? Common ion is H positive, right? We are supposed to calculate the H positive concentration, and we know the common ion concentration is entirely decided by the strong electrolyte, and strong electrolyte concentration here is 0.1 molar. So common ion is going to decide that. I mean, common ion concentration is decided by that only. So the answer is directly 0.1 molar, right? I hope this is super clear to everyone. Now let's move on. Let's move on to something called as ionic product of water. There is something called as ionic product of water. Let's have a look. Ionic product of water. This again one simple topic and you will understand it easily. I'm damn sure about that. Guys, is it clear? Is every single thing clear till here? Give me some thumbs ups in the chats first, then only I can start this. I want everyone to say it quickly. I want everyone to say it quickly. Quickly guys, everyone with the thumbs ups. Everyone with the thumbs ups. Is every single thing clear till here? I want the thumbs ups, continuous thumbs ups I want. Perfect. Let's have a look on this particular topic, that's ionic product of water. So what this ionic product of water is all about. See guys, if you talk about the pure water, pure water is considered to be a weak electrolyte. Pure water is considered to be a weak electrolyte. And this pure water, since it's considered to be a weak electrolyte, so it's going to remain in equilibrium with its ions, and its ions are H positive aqueous and OH negative aqueous, something which you already know, right? Now dear students, since this pure water is a weak electrolyte, so you can write its ionization constant. Its ionization constant is going to be concentration of H positive raised by stoichiometric coefficient, concentration of OH negative raised by stoichiometric coefficient divided by concentration of H2. Correct? Now, since you can write it like this as well, Ki multiplied by concentration of H2O is equal to concentration of H positive multiplied by concentration of OH negative. Now, this is a constant, this is a constant. The multiplication of these two constants will give us new constant, that's Kw. So, Kw is OH negative concentration multiplied by H positive concentration multiplied by OH negative concentration. And this Kw over here, this is something which we call as ionic product of water. This Kw is something which we call as ionic product of water. What do we call it as? We call it as the ionic product of water. We call it as the ionic product of water, Kw. Now, here comes the thing. Here comes the scenario. Have a look. Since people, I told you this Kw. How do we define it? Concentration of H positive multiplied by concentration of OH negative. This particular result, it's valid at all temperatures. It is valid at all temperatures, this particular result, okay? This particular result is valid at all temperatures. Now, let me tell you, at 25 degrees centigrade, particularly, at 25 degrees centigrade, water is neutral, right? At 25 degrees centigrade, the concentration of H positive in water is always equal to OH negative concentration, and both are equal 10 raised per minus 7 molar. So, you can say your Kw here, it is equal to concentration of H positive multiplied by concentration of OH negative, 10 power minus 7, 10 power minus 7 means 10 power minus 14, correct? Now, if we just do one thing, one thing I'm going to ask you first of all, what is pH? What is pH? You will tell me power of hydrogen, right? I don't need all those 10th class definitions. What is pH? What is this P here? What is this P here? What is this P here? P is just the mathematical operator which stands for minus log. P is just the mathematical operator which stands for minus log. Okay? P stands for minus log. It's a mathematical operator. That's it. Okay? That's all. Now, if I multiply this equation throughout by minus log, it's going to be minus log of Kw is equal to, it's going to be minus log of H positive concentration, OH negative concentration, which will be minus log of 10 raised per minus 14, correct? This minus log stands for P, so it's P of Kw is equal to. Finally, when you solve this, you will find it like this, pH plus POH is equal to. When you solve this, it will come out to be 14. So this is one particular result which I would want you guys to remember. And this result is only valid at 25 degrees centigrade. So that's your pH scale, 0 to 14 basically. pH plus POH is equal to 14. Correct? One simple question. One more thing. If you talk about Kw, Kw depends on what? Kw depends on temperature. Kw depends on temperature. On increasing the temperature, do remember Kw increases. On increasing the temperature, do remember your Kw increases. Okay. Now I have got one simple question for you. Let me see how many of you can solve that. One simple question I have. For example, I have got water in the glass. This is a glass of water, right? One simple question. It's a glass of water. Correct? the temperature of this particular water right now will be approximately 25 degrees centigrade. Temperature of this water right now will be approximately 25 degrees centigrade, okay? Yes. Now, dear students, if I increase the temperature of this water a bit, will the pH of water increase or decrease? What do you think? Will the pH of water increase or decrease? What do you think? What do you think? Quickly. Will the pH of water continuously increase or decrease? I'm asking you a very simple question. Let me see how brainy you guys are. A simple question I'm asking you. On increasing the temperature of water, will its pH increase or decrease? Let's see. Let's see. A lot of people are saying same, increase, decrease. All the options you are saying. Huh? All right. So have a look. See what happens. See what happens basically. First statement which you guys are going to remember. On increasing the temperature, when we talk about the pH scale, on increasing the temperature, pH scale shrinks. Number one, pH scale shrinks. Number one. Number two, the scale which we normally see from 0 to 14, right? The scale which we normally see from 0 to 14, this particular scale is only valid at 25 degrees centigrade. This scale is only valid at 25 degrees centigrade. Take the middle point, which will be somewhere here, 7. This 7 represents the neutral medium. It represents neutral. Before this, it represents acidic. After this, it represents basic. Correct? This is something every one of you would be knowing. Now people, I had a water in the container, which was at 25 degrees centigrade. Its pH was 7, so it was neutral. Now if I increase the temperature of same water, the pH scale will shrink now. The pH scale will shrink now. At 25 degrees centigrade, the pH scale was from 0 to 14. Now let's say, for example, at 35 degrees centigrade, let's say it's the random value, imaginary value I'm giving. At 35 degrees centigrade, let's say the pH scale now is from 0 to 13. pH scale now is from 0 to 13, right? What is the middle point here? This is the middle point, which is 6.5, correct? Which is 6.5. You tell me, when I increase the temperature of water, KW increases. KW increases. How will KW increase? KW increase if concentration of H positive as well as concentration of OH negative increases. If concentration of H positive as well as concentration of OH negative increases. So basically the water which you have in the container, if you increase its temperature, its KW increases. That means this water will start to ionize more into H positives and OH negatives. But the increase in the number of H positives will be same as that of the increase in the number of OH negatives. If the increase in the number of H positives and OH negatives will be the same, so neutrality of water is not going to change. Number one, neutrality of water is not going to change. At this 25 degrees centigrade one, 7 represented neutral, but in this particular scale, it's going to be 6.5 which represents the neutral. We got to know on increasing the temperature of water, neutrality does not change. At 25 degrees centigrade, the neutral point was 7. At 35, the neutral point is 6.5. So when we increase the temperature of water, neutrality should not change. That means at 25, water had a pH of 7. Now at 35, water should have the pH of 6.5. Then only its neutrality won't change. So what is happening to the pH? pH is decreasing from 7 to 6.5. pH of water decreases on increasing the temperature. But neutrality remains the same. Is it clear? Do take a note of this point. Perfect? Clear to everyone? Yes or no in the chats? Yes or no in the chats? Yes or no quickly in the chats? In order to maintain the neutrality, pH has to decrease, right? From 7 to 6.5. Okay? Say yes or no. Give me some thumbs ups in the chats, yaar. Quickly. I want the Josh to be high or else the class will die. I don't want that to happen. Perfect? Should I move ahead? Alright, I'm moving ahead, people. I am moving ahead now. Now we are going to discuss something called as pH. One of the important topics here, pH. Okay? It has got different cases, this pH. Let's discuss one by one. Calculation of pH of strong monoprotic acids and bases. Before talking about this particular topic, whenever you hear this term pH, P stands for minus log. Minus log of what? H positive concentration. Whenever you come across this term POH, P stands for minus log, and then you have got OH negative concentration. Whenever you come across this term pKa, P stands for minus log of what? Ka. pKb, minus log of what? Minus log of Kb. Right? P of Kw, P stands for minus log, so minus log of what? Minus log of Kw. Okay? So basically, I'm going to show you the calculation of pH. First of all, whenever you need to calculate the pH of any solution. Whenever you need to calculate the pH of any solution, you should know first of all what is the H positive concentration present in the solution. If you got to know the H positive concentration, just multiply that with minus log, you'll be getting the pH. That's it. That's it. That's all what you have to do. Whenever you need to calculate pH of any solution, what you are supposed to do? Calculate the total H positive concentration in the solution. Multiply with minus log, you'll get the pH. That's all. That's all, right? So first case which I'm going to give you, that is calculation of pH of strong monoprotic acids and monoprotic bases. Let's directly see all this with the help of questions. Let's see all this with the help of questions. The first question is, we are supposed to calculate the pH of 0.1 molar HCl. See what the question is. You have got HCl basically. You are putting this HCl into water. HCl is a strong acid, strong electrolyte. It will dissociate completely into its ions. Right? Now, if I ask you, initially, what is the concentration of HCl do you have? The concentration of HCl is 0.1 molar. This will be 0. This will be 0. Now, the point is this HCl. It's a strong acid. Strong acid means strong electrolytes. सर एवरी चैप्टर 2 आवर दीजिए, सब खत्म हो जाएगा, नहीं तो एक क्लास लग जाएगा. ब्रो मैं तब से पढ़ा ही रहा हूँ, राइट? आई एम नॉट टॉकिंग नॉनसेंस हियर, आई एम जस्ट टीचिंग यू. करेक्ट? आई एम गोइंग सुपर फास्ट ऑलरेडी. You are coming after 2 hours. You are coming and just texting in the chats. Now you will again disappear. You will come back after 3 hours, sir. 1.5 hours something, right? So should I focus on you or should I focus on the rest of 500 people who are watching me? Huh? Tell me. Tell me quickly. All right, so look here now. He's gone. He's ignored. He's already gone. Okay, look here now. So basically, I have taken an acid HCl, right? I've introduced this HCl into water. It got dissociated completely into its ions, right? Now, dear students, the concentration of HCl is given to me as 0.1 molar. Now, if I ask you whether this HCl is strong acid or weak acid, it's definitely strong acid. It is definitely strong acid. It would have got completely dissociated into its ions. And when it would have got completely dissociated into its ions, can I say at the end, I'll be left with, this is going to be the concentration of HCl at the end? Because it is a strong electrolyte. It would be completely dissociated into its ions. There'll be nothing in the container, right? Now, 1 mole of HCl gives 1 mole of H positive. So 0.1 molar is going to give me 0.1 molar. 1 mole of HCl gives 1 mole of Cl negative. So 0.1 molar is going to give me 0.1 molar. Now you guys tell me, what is the concentration of H positive in the container? What is the concentration of H positive in the container? It's 0.1 molar, means 10 raised power minus 1 molar. So in the solution, in the container, I got the concentration of H positive. If we got the concentration of H positive, can we calculate pH? Absolutely, we can calculate pH. How do we calculate pH? P stands for minus log. So minus log of total H positive ion concentration in the container. So it's going to be minus log. H positive concentration is 10 raised power minus 1 log of m raised power n. And log m minus 1 comes to the front. So pH of the resulting solution comes out to be 1. Simple, right? pH of the resulting solution comes out to be 1. Let's have a look on one more. You have got again HCl. You are introducing it into water. It is going to get dissociated as H positive, and with this H positive you are getting Cl negative. The concentration of HCl here is 10 raised power minus 3 molar, right? This is going to be 0, this is going to be 0. Now this is going to be 0, this is going to be 10 raised power minus 3, this is going to be 10 raised power minus 3. So basically, you got the concentration of H positive in the resulting solution. That's 10 raised power minus 3. So calculate the pH of the resulting solution. P stands for minus log. Minus log of what? H positive concentration. So it's minus log of 10 raised power minus 3. The value comes out to be 3. So 3 is the pH of the resulting solution. Simple? Simple, right? Now here you can do a mistake. Here you can do a mistake. Let's see exactly what kind of mistake you can do. The question is, calculate the pH of 10 raised power minus 7 molar HCl. Calculate the pH of 10 raised power minus 7 molar HCl aqueous solution. Calculate its pH. Now see where you can commit the mistake. Have a look. First thing, if I talk about this particular HCl, when we put HCl into water, it's going to get dissociated as H positive plus Cl negative. This is how you are going to dissociate it. Now the concentration of HCl which you have kept here, that's 10 raised power minus 7 molar. This is 0, this is 0. Now it's a strong electrolyte, would be dissociated completely. 0. 1 mole gives 1 mole. 10 raised power minus 7 is going to give 10 raised power minus 7. Even this is 10 raised power minus 7. Now you tell me, as per this particular scenario, what is the concentration of H positive in the container? I would say the concentration of H positive in the container. Concentration of H positive in the container is 10 raised power minus 7 molar. So if I ask you calculate the pH, you will say P stands for minus log, and minus log of what? H positive. So pH of the solution comes out to be how much? Minus log of 10 raised power minus 7. So the pH has to be 7. The pH has to be 7, but pH has to be 7, but HCl is an acid. Can pH of acid be 7 at 25 degrees centigrade? pH of acid can never be 7 at 25 degrees centigrade. It has to be less than 7. So that means there is some mistake which we are doing. Let's identify that mistake. Let's identify that mistake. Let's identify that mistake, right? Let's identify that mistake. So basically, this H positive, this is the concentration of H positive coming into the container. This is the concentration of H positive which is coming into the container from the acid, from HCl. But already in the container there was water, right? Already in the container there was water, and water is a weak electrolyte. Water also dissociates into its ions. From water also you will be getting H positives. So if I ask you what will be the total H positive ion concentration in the container, you will say H positives which we got from the acid and H positives which we got from the water. This is basically the net H positive ion concentration. What is going to be the H positives coming from the acid? It's 10 raised power minus 7 molar. What is going to be the H positives coming from the water? It's again 10 raised power minus 7 molar. We know it at 25 degrees centigrade, right? So if I ask you what is going to be the net H positive ion concentration, you will say net H positive ion concentration is just going to be 10 raised power minus 7 plus 10 raised power minus 7 will be 2 into 10 raised power minus 7 molar. This is the net H positive concentration. If you got the net H positive concentration, calculate pH. P stands for minus log of net H positive concentration. So it's going to be minus log of net is 2 into 10 raised power minus 7. So just use the property of log minus times log of m into n. It's going to be log of m plus log of n, correct? So minus you are going to keep as such. Log of 2 is 0.3, right? Log of m raised power n is n log m, so minus 7 comes to the front. So when you solve this, the value comes out to be 6.7. So 6.7 is the actual pH of the solution. Got it? 6.7 is the actual pH of the solution. Is it clear? Perfect. 6.7 is the actual pH of the solution. Oh. Wow. Guys, wait. Guys, just a second. कुछ पानी वानी तो नहीं है?
नहीं है. Trust me.
Guys, it's Ambika ma'am. I don't know what she's going to do. Okay, just be there. Are you sure? कुछ? Are you making any video? Are you making any video?
No.
Are you sure?
I'm sure.
Swear on someone?
Why should I?
No. Swear on someone.
Open it. Why are you so scared?
Ambika यार कुछ नहीं करना please.
I'm not doing anything. It's just a cup of coffee for you. See, how can I throw a
Zara,
cup
zara.
of coffee?
इसमें क्या है ये?
It's a cup of coffee.
पी ले थोड़ा पहले.
See?
नहीं तूने नहीं पिया. थोड़ा पिया
I'm
अच्छे
so
से.
scared. It's just a cup of coffee.
अरे.
Come on,
Okay.
it's so. I mean, it's just a cup of
साइड में हो जाए. तुम गिराओगी यार.
Yeah, look.
Oh.
It's just a cup of coffee. Have it. One more. Revenge. Yes. So how are you all? See, I'll put a short video. You all can check that what was there in that coffee. You guys can check what was there in that coffee.
इसमें क्या था? नमक
You have to check the whitey shot.
अरे यार.
Enjoy. Bye.
But you had it too, no?
No.
इसमें क्या था ये बोलना?
Check the shot.
मैं seriously बोलना इसमें क्या था? अच्छा मुझे तो बोल दे at least. अरे it was full of salt यार. It was that sea water. I'm going to kill her. Now just wait. Let me finish the class. I think I did a mistake. I got her in the team. Just a second. Okay, should we start? It's a big mistake, I swear. Huh? I was not reading your chats. Let me see. Exactly, she's so annoying, yaar. Psychology teacher. pH was high, it seems. Huh? अच्छा चलो let's move on now. So this is how This is how you calculate what? This is how you calculate pH of strong monoprotic acids, right? Now, how do I calculate pH of strong bases? Let's see that. Let's see that. For example, you have got 10 raised power minus 4 molar NaOH aqueous solution. Okay, 10 raised power minus 4 molar NaOH aqueous solution you have. I need to calculate its pH. Let's see what is to be done. See, first of all, when I talk about the NaOH, okay, NaOH, it's a strong base basically. When I put it into water, it will be 100% dissociated into its ions. It will be 100% dissociated into its ions because it's a strong base basically. What is the concentration of this base which I kept? I kept it as 10 raised power minus 4 molar. So this will be 0 in the beginning, this will be 0. Now it's a strong base, so it will be completely dissociated into its ions, so I'll be left with nothing. 1 mole gives 1 mole from 10 raised power minus 4 molar, you get 10 raised power minus 4. 1 mole gives 1 mole from 10 raised power minus 4, you get 10 raised power minus 4 molar. So if I ask you in the resulting solution, what is the OH negative concentration? OH negative concentration in the resulting solution is 10 raised power minus 4 molar. That is the OH negative concentration, right? Now, dear students, if you got the OH negative concentration, can we calculate directly the POH value? P stands for minus log of OH negative concentration. The value comes out to be 4. You got the value of POH. Since you got the value of POH, you can calculate pH. So pH plus POH is equal to 14. So I must say pH is equal to 14 minus POH. So 14 minus 4 comes out to be 10. So 10 is the pH of the resulting solution. Is it clear? Is it clear to everyone? Give me some thumbs ups in the chats. Like this, you should be able to calculate the pH of strong bases as well. Okay? You should calculate the pH of strong bases as well. Right? Perfect. Perfect, guys. Now comes one more question. For example, I'm going to give you a question like this, just a second. Yeah. Now comes one more case. The case is, if in the same container I'm adding two strong acids, the resulting solution which we get, how do we calculate its pH? Okay. The question is, I've got a container. In the container, I'm introducing two strong acids. I'll be getting the resulting solution, right? I need to calculate the pH of that resulting solution. How do I do that? Let's have a look on this question. The question is, calculate the pH of the following mixture. And the mixture which we are getting, this is something which we are getting on adding H2SO4 with HCl, correct? H2SO4 with HCl. So basically, we have taken H2SO4. We have taken one solution as H2SO4. Another solution which we have taken, that's HCl. And both the ones we are introducing in the same container. Correct? This H2SO4, it's a strong electrolyte, strong acid. It would be dissociated as 2 times H positive aqueous plus SO4 dinegative aqueous. This is how it's going to get dissociated. Similarly, the HCl in the same container would have dissociated in this format. H positive aqueous plus Cl negative aqueous. This is how both the acids would have dissociated. Now, dear students, here you have to remember one thing. And what is that? Have a look. If I ask you whether you are given with the molarity of the first solution, yes. Whether you are given with the volume of the first solution, yes. Do remember, molarity multiplied by volume in ml. It gives me the number of millimoles of solute. Do remember this thing. Molarity of H2SO4 solution is given. Volume of H2SO4 solution is given. If I multiply the two, I will be getting the millimoles of solute. And what is the solute in the H2SO4 solution? The solute is H2SO4, right? So if I ask you, how many millimoles of H2SO4 do we have in the beginning? How many millimoles of H2SO4 we have in the beginning? 0.5 into 400. That comes out to be 200. So we have got 200 millimoles of H2SO4 in the beginning. This will be 0. This will be 0. How many millimoles of HCl we have in the beginning? molarity multiplied by volume. So it's again 200 millimoles of HCl in the beginning. This is 0, this is 0, correct? Now dear students, this H2SO4 is a strong acid, will be getting dissociated completely into its ions. So this will be 0. Now 1 mole of H2SO4 gives 2 moles of H positive. So 200 millimoles will give 400 millimoles of H positive, right? So from this H2SO4, we are getting 400 millimoles of H positive in the solution. Similarly, this will be 0. From 1 mole, 200 means 200. So from HCl, you are also getting 200 millimoles of H positive. So from this acid, H positives are being introduced into the solution. From this acid, H positives are being introduced. If I ask you, how many total millimoles of H positive? Total millimoles of H positive in the resulting solution will be equal to 400 plus 200 comes out to be 600. These are basically the total millimoles of H positive in the resulting solution. Right? In the resulting solution. Total millimoles of H positive. Now, if I ask you, what is the total H positive concentration? Net H positive concentration will be millimoles divided by total volume in ml. Total volume is 400, 400, 800. The value comes out to be 3 by 4. These are basically, this is going to be the net H positive ion concentration in the final solution. If you got to know the net H positive ion concentration in the final solution, calculate pH, which is minus log of H positive net, right? So pH has to be equal to minus log of 3 divided by 4. So it's going to be minus log of 3 minus log of 4 minus log of 4. So it's minus log of 3 is, log of 3 is 0. How much is 0.47? Log of 4 is 0.6. So the pH has to be 0.13. So this is the pH of the resulting solution which I was supposed to calculate. I hope you can easily solve this sort of question from now onwards. Yeah? Is it clear? Is it clear? Perfect. I hope you can solve this sort of equation also, right? So now let's see, till now I was talking about strong acids, strong bases, a mixture of strong acids, right? Now by chance, if you'll be having a weak acid, how will you calculate the pH of a weak acid? How will you calculate pH of the weak base? Let's have a look. Let's have a look. pH of a weak acid or pH of a weak base. For example, you have got a weak acid as HA. You are introducing it into water. This HA, since it's a weak electrolyte, it's a weak acid, it will be in equilibrium with its ions, and these are its ions. Okay. Let's say its initial concentration is C. This is 0. This is 0. Degree of ionization is alpha. Now at equilibrium, I'll be left with what? C minus C alpha. This will be C alpha. This will be C alpha. If, for example, the dissociation constant, ionization constant of this weak acid is Ka, then I can write the expression for Ka. K is simply going to be C alpha square divided by 1 minus alpha, right? Let's do certain assumptions. Let alpha value be less than 0.05. Therefore, 1 minus alpha can be written as 1, and Ka value, it can be written as C alpha square, correct? It can be written as C alpha square. Now people, the similar scenario which we have been doing till now. Alpha is equal to under root of Ka divided by C, right? Alpha is equal to under root of Ka divided by C. Now if I ask you, since you have taken a weak acid, you have introduced it into water, now it is in equilibrium with its ions. If I ask you in the resulting solution, what is the net H positive ion concentration? You will say the net H positive ion concentration is C alpha, right? Which is going to be C times alpha is going to be under root of Ka divided by C, which is going to be under root of Ka divided by C multiplied by, take this C in the square root, it's going to be C ka square. So C got cancelled. So what I got from here, I got the concentration of H positive net is going to be under root of K into C, or you can write it as Ka multiplied by C whole raised power 1 by 2. This is the net H positive concentration. What do I need to calculate? I need to calculate pH. P stands for minus log. H positive concentration is nothing, that's Ka multiplied by C whole raised power 1 by 2. So you can calculate pH, it is minus log of m raised power n log m, so minus 1 by 2. Then you'll be writing log, then you'll be writing Ka multiplied by C, correct? So this is something which you're going to write now, minus 1 by 2. Log of m into n is basically log of m plus log of n. So pH is going to be equal to 1 by 2. It's going to be minus log of Ka plus, or it's minus here, minus log C. Minus log C. One formula I got here which I want you guys to remember directly from now onwards. pH is equal to 1 by 2. This is going to be P of Ka because it's minus log of K means P of K minus log of C. This is the result which you'll be using to calculate the pH in case of weak acids. But do remember, this is the formula which is used only if alpha for weak acid is less than 0.05. Right? Then only you can use it. Correct? Simple and basic. Let's try to solve one question on this. Let's try to solve one question on this. For example, let's try to solve one of them. Let's try to solve one of them. For example, I'm solving the first one. Calculate the pH of 10 raised power minus 1 molar CH3COH. So first of all, let me see this CH3COH. Since we know it's a weak acid, now we have to see whether its alpha is less than 0.05 or not. Let's calculate its alpha. Alpha is under root of Ka divided by C, right? So under root of Ka is 1.8 into 10 raised power minus 5. C value is 10 raised power minus 1. So as I told you already in the beginning, root of 1.8 is 1.34 multiplied by, after solving it, be 10 raised power minus 2. So this is alpha. Is it less than 0.05? Yes, it's less than 0.05. That means I can directly use the formula to calculate pH. And what is the formula which we derived? I don't remember it. What is the formula which we derived? 1 by 2 pKa minus log C. It's going to be 1 by 2 pKa minus log C. Okay, so it's going to be pH is equal to half of P of Ka. Do remember from now onwards, minus log of 1.8 into 10 raised power minus 5. It's always equal to 4.74. Just to reduce the calculations, I want you guys to remember this particular value. You'll be frequently getting it. Minus log of 1.8 into 10 raised power minus 5 value is 4.74 basically. So P of K is nothing, it is 4.74 minus log of C. C is the concentration, which is 10 raised power minus 1. So 10 raised power minus 1, right? So pH will be equal to half of 4.74 minus log of m raised power n log m. So minus 1 comes to the front, so it becomes plus 1. Okay, so it will be 5.74 divided by 2. 5.74 divided by 2, the value comes out to be 2.87. So 2.87 is the pH of the resulting solution which we were supposed to calculate. Is it clear? Is it clear, people? Is it clear? Let me know quickly in the chats. I hope you can solve these sort of questions from now onwards. Yeah, I hope you can do that. I hope you can do that. Let me know once in the chats. All clear till here? All clear till here? Say quickly in the chats, everyone, with the thumbs ups. All clear? Okay, let's have a look on one more topic now. Relative strengths of two weak acids. Relative strengths of two weak acids. Now have a look. For example, I have got a container which contains an acid HA1. It's a weak acid. So it's going to remain in equilibrium with its ions. Its ions are H positive aqueous plus A1 negative aqueous. This is one weak acid which is present in one container, right? Similarly, I've got one more container which contains one more weak acid. it contains one more weak acid, right? Let's say the degree of ionization of this weak acid is alpha 1, this is alpha 2. Let's say initially the concentration of this weak acid is C1, this will be 0, this will be 0. This is C2, this will be 0, this will be 0. Correct? These are the two weak acids which are present in two different containers. Two weak acids present in two different containers, okay? So when equilibrium will be established in both the containers, it's going to be C1 minus C1 alpha 1. This will be C1 alpha 1. This will be again C1 alpha 1. So this is going to be C2 minus C2 alpha 2. This is going to be C2 alpha 2. And this is going to be C2 alpha 2 as well. Okay? Perfect. Let's say the dissociation constant of this weak acid is K1 and the dissociation constant of this weak acid is K2. Correct? Now, dear students, since two weak acids are present in two different containers. Now, among these two weak acids, if I ask you which one is comparatively strong, among the two weak acids, if I ask you which one is comparatively strong, you know, strength of acid, whenever we talk about the strength of acid is directly proportional to the concentration of H positive, right? So I would say strength of acid 1 divided by strength of acid 2 will be equal to concentration of H positive coming from this particular acid 1 divided by concentration of H positive coming from acid 2. What is the concentration of H positive coming from acid 1? It's C1 alpha 1. Concentration of H positive coming from acid 2, that is C2 alpha 2, right? Or you can write it in different way as well. You can write C1 alpha 1, you know, that's under root of Ka1 divided by C1. Alpha 2, you know, that's under root of Ka2 divided by C2. Now you can make one more result. It's under root of K1 C1 divided by K2 C2. This is how you can compare the strength, the acidic strengths of two weak acids. Whenever you'll be given with two weak acids and you have to compare their acidic strengths, this is how you can compare the acidic strengths of two weak acids as well. Okay? Either you can use this particular result or you can use this particular result. Depends on what all things are given to us as with the question. I hope this is again super clear to you. Right? Perfect. All right. What should be the answer of this question? I have already given you the concept of it. What do you think? What should be the answer of this particular question? Quickly. What do you guys think? What do you guys think? I've already taught its concept. I've already given its concept. By the way, we are the family of 17K now. That's great. Just keep on sharing. Keep sharing this channel to everybody, okay? Quickly, what should be the answer of this question? Everyone. They are asking about the pH. Quickly here. See, again you have got strong electrolyte, weak electrolyte in the same container, right? So that means, what is the common ion in between? It's H positive. Entire common ion concentration is decided by what? Entire common ion concentration is decided by the strong electrolyte. So I'll take the directly concentration of common ion as 0.1 molar, right? This is the net H positive ion concentration. So calculate the pH directly. No need to do calculation, etc., etc. If you remember the concept, it's minus log of H positive. It'll be minus log of 0.1. Minus log of 10 raised power minus 1. The value comes out be 1. This is the pH of the resulting solution. That's all. Nothing else, right? Yes? Nothing else. I hope it's again clear. I hope it's again clear. Now, people, we are going to enter into one more topic. That's salt hydrolysis. This is again one important topic, but from which I'm not going into the details of salt hydrolysis. From this particular topic, questions can be formula based, right? And I'll be giving you the formulas first. And then we are going to relate this salt hydrolysis with a buffer from where actual good questions come. Okay? So let's have a look on what the salt hydrolysis exactly is all about. Salt hydrolysis, how do you define it first of all? It is defined as the interaction of ions of a salt with water to produce either acidic or alkaline solution. The interaction of ions of salt with water to produce either acidic or the alkaline solution. What is meant by that? For example, you have got a salt AB. Let's say this is your salt. Okay, this is your salt AB. In the salt, you have got the cation and anion. In the salt, you have got the cation and anion. Now you are introducing this salt into water. You are introducing the salt into water. Now in the water, you have got two types of ions, you know, H positives and OH negatives. You have got two types of ions, right? Now basically, two possibilities arise here. Either the cation of the salt is going to interact with the water, or the anion of the salt is going to interact with the water. Let's say it is the cation of the salt. Let's say it is the cation of the salt which is going to interact with water. Now tell me, cation of salt will interact with OH negative. Cation of the salt will interact with what? It will interact with OH negative. Perfect. It will interact with OH negative and it will lead to the formation of AOH. Right? Whenever cation of the salt interacts with water, this type of hydrolysis is what we call as cationic hydrolysis. Whenever you see the cation of the salt interacting with the water, right? This kind of hydrolysis is what we call as cationic hydrolysis. Similarly, if I talk about the anionic hydrolysis, right? In case of anionic hydrolysis, the anion of the salt is going to interact with the water, and anion of the salt is going to interact with H positive basically, right? From the water, it's going to lead the formation of HB, right? So basically when I talk about salt hydrolysis, in case of salt hydrolysis, the phenomenon of interaction of ions of salt with water to form either acidic or the alkaline solution. This is something which we call as salt hydrolysis. This salt hydrolysis can be of your cationic type or anionic type. Cationic means cation of the salt is going to interact with the water, cationic hydrolysis. Anion of the salt is going to interact with the water, anionic hydrolysis. That's all. Number one. Number two. Before giving the results and all, I would want you guys to know about the types of the salts. That's important, okay? Types of the salts. You should first of all know about the types of the salts. Types of the salts. First category is the salt of strong acid and strong base. The salt of strong acid and strong base. Dear students, let's say I'm taking an example. Let's say I'm taking HCl. I'm making HCl to react with NaOH. So HCl plus NaOH, acid plus base, gives you salt and water. So you get NaCl here, and with this NaCl, you get water. So basically, acid plus base gives salt. This is a salt. Now, which type of salt it is? It is a salt of strong acid and strong base. How do you identify exactly this is the salt of strong acid and strong base? Say, you have got Na positive here, you have got Cl negative here. Can I say this Na positive has come from NaOH? Absolutely. And this Cl negative, it has come from HCl. You know it. So this is your strong base, this is your strong acid. So this is basically going to be the salt of, it is going to be the salt of strong acid and strong base. It is going to be the salt of strong acid and strong base. As simple as that. Nothing else. Okay, this is the first type of salt. Second, let's say I'm taking the salt of weak acid and strong base. Let's say I'm taking the case of salt of weak acid and strong base. Let me take one weak acid as CH3COH. Let me take a strong base over here as NaOH. Nowadays, students, CH3COH plus NaOH, what do you think it's going to give me? It's going to give me CH3COONA, and with this you'll be getting water as well. Now, if I ask you what about the type of this particular salt, this is going to be the salt of weak acid and strong base, right? It's going to be the salt of weak acid and strong base. Now, similarly, the third type of the salt which we have, that is the salt of strong acid and weak base. Strong acid and weak base. For example, strong acid you are taking HCl, weak base, let's say you have got NH4OH. So what does it form? It forms NH4Cl here. This NH4Cl, it is basically the salt of what? It is a salt of strong acid and weak base. The fourth one, you have got a salt of weak acid and weak base. Weak acid and weak base. Your weak acid is CH3COH. Your weak base is NH4OH. Let them react, let them form the salt, and the salt here is going to be CH3COONH4. So this is basically going to be the salt of weak acid and weak base, right? So these are the 4 types of the salt. Do remember, out of all these 4 types of salts, there are only 3 types of salts which undergo hydrolysis. This one, and this one. Salt of strong acid and strong base, it does not undergo hydrolysis. Okay, this is one important point. Do take a note of it. Salt of strong acid and strong base, it does not undergo hydrolysis at all. Yes? Clear? Now in case of salt hydrolysis, what all questions are asked to us? What all questions are asked? I'm directly going to give you the results and I'll show you how to apply those results. Just have a look on what I say now. Just have a look and do remember this particular table as well. Here I'm mentioning the, is it visible on the screen? Here I'm mentioning the type of the salt. Here I'm mentioning the KH value. KH is what you call as hydrolysis constant. Hydrolysis constant. Then you have got H. H is called as degree of hydrolysis. Degree of hydrolysis. And how do we calculate pH? So these are the 3 questions which are asked. Calculate the degree of hydrolysis constant, calculate the degree of hydrolysis, calculate the pH. Okay. Now, let's say I've got the salt of strong acid and weak base. Salt of strong acid and weak base. How do I calculate hydrolysis constant for this particular salt, KH? What is KH all about? KH is going to be equal to Kw, which is 10 raised per minus 14 at 25 degrees centigrade, divided by, which is the weaker part here. Base is the weak, so I'll be writing Kb. KH is equal to Kw divided by Kb over here, number 1. Number 2, degree of hydrolysis H. H is going to be under root of Kw divided by Kb multiplied by C. This C is basically the concentration of salt. C is the concentration of salt, right? Similarly, pH. How do I calculate pH here? It is the salt of strong acid and weak base. Strong acid means pH has to be 7 minus. pH has to be 7 minus. Strong acid, right? Half of. Now, weaker part is base, so it's going to be P of Kb plus log of C, where C is the concentration of salt. These are the 3 questions which can be asked when we do the hydrolysis of the salt of strong acid and weak base, number 1. Number 2, if you will be having the salt of weak acid and strong base. If you have the salt of weak acid and strong base, first of all, how do I calculate the hydrolysis constant KH? Hydrolysis constant is going to be equal to Kw divided by. Now the weaker part is acid, so it's going to be Ka. If I talk about H, H is going to be under root of Kw divided by Ka multiplied by C. Similarly, if I talk about the pH, pH is going to be, this is weak acid strong base, so it has to be 7 plus half of P of Ka plus log C, where C is the concentration of salt. The last case which we have here, that is the salt of weak acid and weak base, right? Let's calculate its KH value. KH is going to be Kw divided by Ka multiplied by Kb, right? So H is going to be equal to under root of Kw divided by Ka multiplied by Kb. Perfect. And its pH is going to be equal to 7 plus half of P of Ka minus P of Kb. This is how you guys are going to do it, right? Just remember these results. From these particular results, you'll be directly getting the questions. And first of all, you should remember these results, then only you can utilize these results, okay? Perfect till here? Is it clear till here? Quickly. Is it clear till here? So these are the results which I mentioned here. So let's do the questions. Let's do a few questions on this. You'll get the idea. Right now, I'll be only showing you the formula-based ones, okay? The actual questions on salt hydrolysis can be only solved if we first of all study the buffer solutions. After buffer, I can show you some good questions based on salt hydrolysis, okay? Abhi ke liye, they'll ask you like questions which will be directly formula based. And let me show what kind of formula based question. I'll show you one, okay? Calculate the degree of hydrolysis. Degree of hydrolysis means H. H value we need to calculate. And pH. All right, pH also we have to calculate. Of the solution obtained by dissolving 0.1 moles. 0.1 moles of what? CH3CONa. So you have taken the salt as CH3CONa. And these many moles of salt are introduced in water to get 100 liter solution. So we have 100 liters of solution as well. And Ka for acetic acid. Ka for acetic acid is given to us as 2 into 10 raised power minus 5 as well. See how you can solve this question. It's very simple. It's very simple. First of all, what do we need to calculate? We need to calculate H. Okay, we need to calculate H. How do we calculate H exactly? H is equal. First of all, identify which kind of salt this is. CH3CO negative, Na positive. CH3CO negative has come from CH3COH. Na positive has come from NaOH. So this is the salt of weak acid and strong base. This is the salt of weak acid and strong base. Now how do we calculate H? It's going to be under root of Kw divided by Ka multiplied by C. This is how you calculate H. Correct? This is how you calculate H. Number one. Number two, we have to calculate pH as well. Is that? We have to calculate pH as well. pH is going to be what? pH, it's a strong base. pH is going to be 7 plus half of P of Ka plus log of C. So, since I remember these results, now I can easily solve them. Otherwise, it was impossible for me to solve such question, right? So, that's why I gave you the results. You have to remember all them. Now, people, have a look. It's going to be under root of Kw value at 25 degrees centigrade. That's 10 raised power minus 14. Ka value is given to us as per the question. That's 2 into 10 raised power something, minus 5. What is C? C is the concentration of salt. Concentration of salt means number of moles of salt divided by volume of solution in liters. How many moles of salt we have? 0.1. What is the volume of solution in liters? 100. So the value is going to be 10 raised power minus 3, right? So into 10 raised power minus 3. So solve this, get the result, get the H value, get the degree of hydrolysis, okay? Get the degree of hydrolysis. At the same time, pH. pH is going to be 7 plus half of P of Ka. P stands for minus log of this particular value. You'll get plus log of C. C is the concentration of salt, right? You can get it too. So till now, these are all the formula-based questions. Till now, these are all the formula-based questions. The actual questions on salt hydrolysis will only come when we do the buffer solutions. And buffer solutions, let's do after the break, okay? So, giving you the break. Do you want the break now or after some time? let's take a break, okay? I'll also have some food. I have not had anything. So I'll see you again at 4:30. Okay? But be back soon, okay? Be back. I'll exactly start at 4:30 because this buffer is something which you will never understand from the books. Okay, it's very difficult to understand basically. So be here again sharp at 4:30. Otherwise, your buffer is gone. Okay? Chalo, see you. Bye bye. Guys, am I audible? Can you all see me? Yes? Am I again audible, visible to everyone? Quickly, quickly. I took 5 more minutes, sorry. I was eating basically. So now, so let me know quickly in the chats if all of you can hear me. Quickly, everyone, quickly. Yes, yes, you'll be getting the notes today for sure. For sure, you'll be getting the notes today. Call up everyone, guys. Call up everyone. Quickly, we'll start. Quickly, call up everyone. We'll start. Mock test and all, I'm arranging for all of you. You just need to give me one day, okay? Tomorrow evening or day after tomorrow, I'll be giving you some 5 to 6 like killer mock tests, I would say, okay? Right? Perfect, guys. So let's get going then. So now, let's start with something called as buffer solutions. So how do we define the buffer solutions first of all, and what kind of questions can be asked out of these buffer solutions? Let's have a look on the definition first. Buffer solutions are basically defined as, these are the solutions whose pH does not significantly change on adding the small amount of acid or base. Any such solution whose pH does not significantly change on adding small amount of acid or base into it, we call that particular solution as buffer. Number one, right? So what's a buffer solution? Buffer solution, it is a solution basically whose pH does not significantly change on on adding the small amount of acid or base into it. So what do they do basically? They show resistance towards the change in pH. They show resistance towards the change in pH. They show resistance towards the change in the pH. Right? They show resistance towards the change in the pH. My dear students, let's go into the buffer a bit more in detail, right? Well, we generally classify buffers into two types. One is called as simple buffer, one is called as mixed buffer. What is a simple buffer? Simple buffer is basically made up of a single substance. It is made up of a single substance. For example, when you talk about the salt of weak acid and weak base. If I talk about the salt of weak acid and weak base, for example, you have got CH3CONH4. This is basically the salt of weak acid and weak base. It can act like a buffer. It can act like a buffer. It is made up of only one component. It's only one component here. It's a salt. It's only one component here in the container, right? So you'll be calling this particular buffer as the simple buffer. In this simple buffer, if you add small amount of acid or base, right, the pH won't significantly change. It will show resistance towards the change in pH. It will show resistance towards the change in pH. Number one. Number two, when you talk about the mixed buffers are made up of two substances. Mixed buffers are made up of two substances. Here the simple buffer was made up of only one substance. But when we talk about the mixed buffers, these are made up of two substances, right? And we further classify them into acidic and basic buffer. Now, this is something which we have to discuss in detail. Acidic buffer and basic buffer. let's have a look what this acidic and basic buffer is all about. Have a look, guys. Let's have a look on the acidic buffer first of all. How this acidic buffer is made. First of all, this acidic buffer, it is the example of what? It is the example of the mixed buffer. It is the example of the mixed buffer, right? How many components it contains? It contains 2 components. It contains 2 components. Does it show resistance towards the change in pH? Yes, since it's a buffer, it shows resistance towards the change in pH. It shows resistance towards the change in pH. Now the point is, how do we make the acidic buffer? In order to make the acidic buffer, what do we do? What do we need? We need a weak acid. We need a weak acid and the salt of same weak acid with a strong base. Whenever you see such kind of a thing, whenever you see weak acid and the salt of same weak acid with a strong base, you call this particular mixture over here as the acidic buffer. For example, have a look. Let's say I'm taking CH3COOH in the container. I'm taking CH3COOH in the container. And with CH3COOH, I'm for example taking CH3COONA. CH3COONA. Right? CH3COONA I'm taking. So dear students, do you see this CH3COOH? It's a weak acid. It's a weak acid. And this is a salt of same weak acid with a strong base. So this is something which I'll be calling as acidic buffer here. It's something which I'll be calling as acidic buffer here. So in short, wherever you see a weak acid and the salt of same weak acid with strong base, right, you'll be calling it as the acidic buffer. So this is the example of the acidic buffer, number 1. Number 2, if I talk about the basic buffer, how do we get the basic buffer? Basic buffer is again the example of the mixed buffer, which is actually made up of 2 components. It is actually made up of 2 components, right? And it also shows resistance towards the change in pH. It also shows resistance towards the pH change. Right? And how do we get the basic buffer? In order to get the basic buffer, we should have a weak base and we should have the salt of same weak base with a strong acid. Salt of same weak base with a strong acid. Salt of same weak base with a strong acid. Let me give you one example. For example, I am taking NH4OH in the container, which is the example of weak base. Let me take the salt of same weak base, which it would have formed with the strong acid. For example, I am taking NH4Cl. So it's a weak base. And salt of same weak base with a strong acid. So I'll be calling it definitely as what? I'll be calling it as basic buffer. Right? This was the example of the acidic buffer. Now the question comes, what the question comes exactly? The question comes, how do we calculate the pH of the basic buffers and acidic buffers, right? How do we get the pH of basic buffers and acidic buffers? Have a look. I'm not going into the details how the buffer and all works, right? That's not the question which is asked in your exam. Perfect. I'll just show you the application of calculation of pH of these buffers, from which the question actually comes. Well, dear students, if I ask you what this is it acidic or basic buffer? Weak acid, salt of same weak acid with a strong base, acidic buffer. How do I calculate its pH? This is the result. pKa plus log of concentration of salt divided by concentration of acid. It is basically here the conjugate base, concentration of conjugate base. But in your NEET, right, I mean, you can consider it as a salt. Perfect? Right? So this result, you need to take a note of. This is how you calculate pH of the acidic buffer. P of Ka plus log of concentration of salt divided by concentration of acid. Number 1. Similarly, in case of basic buffer, we have got the formula to calculate POH. In case of basic buffer, we have got the formula to calculate POH. And this is the result by means of which we calculate pOH of a basic buffer. It is basically pKb plus log of concentration of salt divided by concentration of base. Right? In the acidic buffer, we calculate pH directly. In the basic buffer, we calculate pOH. Okay? We calculate pOH. You call these equations as the Henderson's equation. Now the point is, how do we use these equations and how do we solve the equations? That is our motive, right? That's the main thing here. One simplest question. One simplest and the formula-based question. Let's start with this. Have a look. Calculate the pH of 1 liter solution containing 0.01 molar CH3COH and 0.02 molar CH3CONA. So basically, we have got CH3COH, and with CH3COH, what do we have? We have got CH3COONA. First of all, it's a weak acid, and this is the salt of same weak acid with a strong base. So what do I call this? I call this as the acidic buffer. So basically, I have got a buffer in this container. This is the acidic buffer in the container. What am I supposed to calculate? I am supposed to calculate pH of this acidic buffer. How do we calculate pH of this acidic buffer? We know it. It is P of Ka plus log of concentration of salt divided by concentration of acid, right? Divided by concentration of acid. Now, dear students, let's have a look what all parameters are given to us. P of Ka. Ka is 1.8 into 10 raised power minus 5. And P of Ka, what does it mean? P stands for minus log. So basically, they are asking about minus log of 1.8 into 10 raised power minus 5, which comes out to be equal to 4.74. 4.74. So P of Ka is basically directly equal to 4.74 plus a log of. What is the concentration of salt? Salt concentration is given to us as per the question, 0.02 divided by. Acid concentration is given to us as 0.01. So it is basically log of 2, right? It's coming out to be log of 2, and log of 2 is how much? Log of 2 is basically 0.3. Perfect. So the final answer of the question comes out to be 4.74 plus 0.3. The value comes out to be 5.04. Right? This is how you solve this question. Simple. Yeah? Is it clear to everyone quickly? Okay. Now let's move on to some good questions. Let's move on to some good questions so that you can analyze it properly. Acid-base titration, everyone would have heard. Acid-base titration. So now we are going to do some questions of the acid-base titration. Okay? Right? Perfect. Let's start with this particular question, guys. Calculate the pH of the solution obtained on mixing 100 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. So as per this particular question is concerned, you guys are making CH3COH, you guys are making CH3COH to react with NaOH. To react with NaOH. And you know, when acid reacts with a base, it leads to the formation of salt. It leads to the formation of salt, and this you will be getting water as well. Right? So you're starting with the acid. As per the question, you're making it to react with the base, and what do we get? We get salt and we get water as well. Number one. Number two, if I ask you at time t is equal to 0, at time t is equal to 0, are we given with the molarity and volume of this particular solution? Molarity and volume of CH3COH solution is given to us. If I just multiply molarity with the volume of the solution, what do I get? I get millimoles of CH3COH. Now you tell me how many millimoles of CH3COH we have. 0.1 multiplied by 100, that comes equal to 10. So we have got 10 millimoles of CH3COH initially, right? How many millimoles of NaOH we have? 100 multiplied by 0.1. We have got 10 millimoles of NaOH also initially. So this will be 0, this will be 0. Since you're taking NaOH and you're mixing NaOH and CH3COH solution, right? When you will mix NaOH with CH3COH, a reaction will happen basically, right? When acid and base comes into the contact, a reaction happens. Perfect. What is the reaction? This is the reaction which is going to happen. Salt and water will be getting formed. That's what we are doing. That's what we are doing. Correct? We took one acidic solution, one basic solution, put them into the same container, a reaction happened, salt and water formation takes place. That's all, right? Now you tell me one thing. We got the millimoles of all the reactants. Whenever we are given with the amounts of all the reactants, we use the concept of limiting reagent. So over here also we'll be using the concept of limiting reagent. And how exactly? Divide the given millimoles of reactants by the stoichiometric coefficients. So 10 by 1, 10 by 1. Value comes out to be 10, right? So this is the case of complete neutralization basically. I'll be left with 0 millimoles of this. I'll be left with 0 millimoles of this one as well, right? Now how many millimoles of salt and water would have got formed? 1 mole of this gives 1 mole. From 10 millimoles, you'll be getting 10 millimoles. Similarly, you'll be getting 10 millimoles of water as well. Perfect. So finally, when the reaction has stopped, can you let me know in the final container what do we have? In the final container what do we have? We are not left with any acid. We are not left with any base. We are left with salt. We are left with water. We are left with salt. We are left with water. Right? So what do we have in the final container? In the final container, we are left with salt and water. Perfect. We are left with salt and water. And salt plus water, what is going to happen? Salt plus water. The ions of salt are going to interact with the water to form either acidic or alkaline solution. So, should I be using the buffer wali formula to calculate pH, or should I be using the salt hydrolysis result to calculate pH? I can say over here now salt hydrolysis is going to happen. So, the pH of the resulting solution will be given by the salt hydrolysis result, right? So, this is the salt of weak acid with strong base. Weak acid with strong base. Weak acid with strong base. So 7 plus half of. 7 plus half of. It's going to be P of Ka plus log of C. This is the result which you guys will be using. Right? This is the result which you guys will be using. Correct, people? So look at this one. Now if I talk about pH, it's going to be equal to 7 plus half of P of Ka. Ka value is given to us. P of Ka minus log of this comes out to be 4.74 plus log of C. C is the concentration of salt. Concentration of salt means millimoles of salt divided by total volume. Millimoles of salt divided by total volume. Total volume is 100 plus 100. That comes out to be 200. Right? Now a bit of calculation is needed. Calculate the pH. That's it. Bit of calculation is needed. Calculate the pH of the resulting solution. Is it clear to everyone? Is it clear to everyone quickly? So first of all, whenever this sort of a question comes, you have to see what will be left in the container at the end of the reaction. Accordingly, you have to use the result to calculate the pH. I hope you get it. Let's try to do one more question. Let's try to do one more question. Let's try to do one more question. A similar type of question I'm giving you. A similar type of question I'm giving you. And there is only one change which has been done and whole question has been solved. Right? Have a look, guys. Understand. Understand. Calculate the pH of the solution. Calculate the pH of the solution obtained on mixing 100 ml of 0.1 molar CH3COH with 50 ml of 0.1 molar NaOH. Right? Now, dear students, again what you guys are going to do is CH3COH, you are making it to react with NaOH and it leads to the formation of the acid plus base, salt and water, right? It's going to be CH3CONa and with this you will be getting water. With this you will be getting water, right? Now, dear students, initially at time t is equal to 0, how many millimoles of CH3COOH we have? This molarity multiplied by volume in ml, 100 into 0.1 comes out to be 10. So we have got 10 millimoles of CH3COH. How many millimoles of NaOH we have? 50 multiplied by 0.1. We have got 5 millimoles of NaOH. So this will be 0. This will be 0. Correct? Now, dear students, again I got the millimoles of all the reactants. Again I'll be using the concept of limiting reagent. Again I'll be using the concept of limiting reagent, right? Yes? So just tell me in the charts which one is the limiting reagent among the two. Divide the given millimoles by the respective stoichiometric coefficients. The one which gets the lesser value, that is the limiting reagent. So which one? So it's going to be NaOH, which is the limiting reagent. If NaOH is the limiting reagent, out of 5 millimoles, I'll be left with 0 millimoles of NaOH, right? Perfect. Entire product formation will be decided by this limiting reagent. So can I say 1 mole of NaOH gives 1 mole of salt? So 5 millimoles are going to give us 5 millimoles of salt, right? Similarly, you'll be getting 5 millimoles of water as well. If I ask you how many millimoles of acid will be left, 1 mole reacts with 1 mole. So 5 millimoles will react with 5 millimoles. So I'll be left with 5 millimoles of acid as well. So at the end of the reaction, see what all things are left in the container. We are left with a weak acid. And this is the salt of same weak acid with a strong base. This is the salt of same weak acid with a strong base. So weak acid and the salt of same weak acid in the strong base, they are present in the same container. So what they'll form? They'll make the acidic buffer. They'll make the acidic buffer, right? Over here, these two can form, these two can do the salt hydrolysis as well. But as a shortcut, as a trick, do remember, whenever you get confused whether to use the acidic buffer formula to calculate pH, whether to use buffer formula to calculate pH or salt hydrolysis. Whenever you get confused whether to use buffer formula to calculate pH or salt hydrolysis, okay, you'll be giving priority to buffer formula. So I'll be using the buffer formula to calculate the pH. Okay, so you can say pH is equal to P of Ka plus log of concentration of salt divided by concentration of acid in this case, right? P of Ka minus log of this value, you know, that's 4.74 plus log of, what is concentration of salt? What is concentration of salt? Concentration of salt means millimoles of salt divided by total volume. Total volume is 100 plus 50, 150, whole divided by. Concentration of acid, millimoles of acid divided by total volume. Millimoles of acid is 5, total volume is 150. So this term cancel, log 1 is 0. So final answer of this particular question will be 4.74. Let me know quickly in the chats if it's clear. Everyone quickly in the chats if it is super clear. Let's have a look on the last topic of the ionic equilibrium. So till now we are done with 2 chapters. One is chemical equilibrium, one is ionic equilibrium. These are actually 2 chapters, right? Okay. Someone just came into the session, he's asking about the break. Wow. That clearly tells me you are not in the session, you are just coming and asking for the break. Alright, now let's have a look on something called as solubility product. Okay, not going into the details, something which is required at this point of time. Okay, see guys, if I say solubility of any salt is equal to 5 moles per liter. If I say solubility of any salt is 5 moles per liter, what does that mean? What does that mean? That means 5 moles of salt are dissolved to get 1 liter of saturated solution. To get 1 liter of saturated solution. This is something which it means. If I say solubility of some salt is 5 moles per liter, what does that mean? That means 5 moles of salt are dissolved to get 1 liter of saturated solution. Okay. If I say I've got a salt whose solubility is 0.2 moles per liter, what does that mean? That means 0.2 moles of salt are dissolved. 0.2 moles of salt are dissolved to get 1 liter of saturated solution. To get 1 liter of the saturated solution. Correct? This is something which I want you guys to know. Perfect. And whatever salt that is soluble basically, whatever salt that is dissolved, that salt which is dissolved basically, that remains in the solution in the form of ions. What does that mean? For example, I've got a scenario like this. Let's say I've got the salt as AB. I've got the salt as AB, right? I've got the salt as AB. Let's say its solubility is, for example, 0.02 moles per liter. Let's say its solubility is 0.02 moles per liter. Its S value is 0.02 moles per liter. I'm assuming it's a sparingly soluble salt. Its solubility is very, very, very low. Do remember, all the sparingly soluble salts, we treat them in equilibrium with their ions. So this is A positive aqueous plus B negative aqueous. I'm assuming the salt is a sparingly soluble salt, for example. Its solubility is 0.02 moles per liter. Its solubility is 0.02 moles per liter, right? That, what does it mean? It means 0.02 moles of salt are dissolved in 1 liter of solution to make it saturated. Okay? Now, whatever moles of salt are dissolved, those moles of salt will remain in the solution in the form of ions. And how? I'll say 1 mole gives 1 mole. From 0.02 moles, you would have got 0.02 moles of A positive. So I got the concentration of A positive in the resulting solution. Similarly, 1 mole gives 1 mole. From 0.02, you get 0.02 molar. So this is the concentration of B negative in the resulting solution. Right? Perfect. So now basically, what we have to deal with, something called as solubility and solubility product. Let me tell you, any salt whose solubility is greater than 0.1 molar, or you can say 0.1 moles per liter, right? We call that particular salt as the soluble salt. Any such salt whose solubility lies in between 0.01 to 0.1, we call that particular salt as slightly soluble salt. And similarly, any salt whose solubility will be less than 0.01, we call that particular salt as the sparingly soluble salt. We call that as the sparingly soluble salt. And we have to deal with the sparingly soluble salts here. And do remember, sparingly soluble salts are treated in the similar way as we treat the weak electrolytes. I told you we keep weak electrolytes in equilibrium with its ions. In the similar way, whatever sparingly soluble salts we have, we'll be keeping them in equilibrium with their ions. Just to make your questions, etc., easy. Okay? Just to make your questions, etc., easy. Perfect. Now let's have a look on something called as solubility product. Understand now what I'm going to say. For example, I have made a saturated solution of AB. I have made a saturated solution of AB, right? Let's say I have made a saturated solution of AB. I'm assuming the solubility of this salt is S moles per liter. Its solubility is S moles per liter. That means S moles of this particular salt, whatever salt that is dissolved, that's going to remain in the solution in the form of ions. Now tell me, 1 mole of AB gives 1 mole of A positive, so S moles will give us S moles only. Similar, 1 mole gives 1 mole, so S moles are going to give us S moles only. Perfect. So what is this S moles here? Can I say the concentration of A positive in the solution we got to know as S moles per liter? Concentration of B negative in the solution we got to know as S moles per liter, right? Now, this AB, let's write the ionization constant expression for this particular AB over here. Ionization constant is going to be concentration of A positive raised by stoichiometric coefficient, concentration of B negative raised by stoichiometric coefficient divided by concentration of AB, right? Now, this Ki is a constant, concentration of AB will be also a constant, so constant multiplied by constant will make a new constant, which is something which I call as KSP, solubility product. And how do I write it? Concentration of A positive raised power 1, concentration of B negative raised power 1. So this is how you write basically the solubility product of any salt basically, right? This is how you write the solubility product of any salt. I hope this is clear. I hope this is clear. Now, let's see exactly how do we write the KSP for different types of salts. Let's say I've got the salt of the type AB2. This is the salt. If I ask you how it's going to get dissociated, it will get dissociated in this manner. A di positive aqueous plus 2 times B negative aqueous. Plus 2 times B negative aqueous. This is how it's going to get dissociated. Number 1. Number 2, if the solubility of this salt is S, so 1 mole gives 1, so S moles are going to give S moles. 1 mole gives 2, so S moles are going to give us 2 S moles, right? Now, if I ask you to write KSP expression, how do I write the KSP expression? KSP expression I'm going to write as concentration of A di positive raised power 1, concentration of B negative raised power 2, stoichiometric coefficient. Okay? Now, people, KSP will be equal to concentration of A dye positive, that's S, concentration of B negative, that's 2S raised power 2. So this expression comes out to be 4S ka cube. So this is the KSP expression of this particular type of salt. As simple as that, right? Okay. In the similar way, guys, in the similar way. For example, I've got the salt of the type AB3. I've got the salt of the type AB3. How it's going to get dissociated? A tri-positive aqueous plus 3 times B negative aqueous. Let's say its solubility is S. This will be S. This will be 3S directly. Just write the KSP expression, solubility product expression. It's going to be concentration of A tri-positive raised power stoichiometric coefficient, concentration of B negative raised power stoichiometric coefficient. So KSP value from here is going to be concentration of A tri-positive is S, concentration of B negative is 3S raised power 3. So it's going to be 339327 S raised power 4. That's how you do it, right? That's how you do it. Perfect. Right? In the similar way, guys, for example, in general, if you have got the salt of this type, AXBY, how you are going to dissociate it? General form I'm showing. It's going to be X times AY positive plus Y times BX negative. This is how you are going to dissociate this particular salt. Number one. Number two, let's say its solubility is S. So its concentration is going to be X times S. Its concentration is going to be Y times S. If you want to write the KSP expression is going to be concentration of AY positive, concentration of AY positive raised power stoichiometric coefficient, concentration of BX negative, raised power stoichiometric coefficient. So it's going to be KSP is equal to X times X, Y times Y, and it's going to be S raised power X plus Y. This is how you are going to write the KSP expression in general for any salt. Okay? Perfect. I hope this is clear. Let me know quickly in the chats if it is super clear to everyone. Quickly, everyone. Let's see what kind of questions can be asked from the solubility product. Let's see what kind of questions can be asked from the solubility product. You always get very simple questions from solubility product. Let me tell you that honestly, okay? This 10 raised power minus 14, okay? KSP for MgOH whole twice is given. We need to calculate its solubility in water. Yeah? So basically, first you need to tell me how this MgOH whole twice will undergo dissociation. It will go undergo dissociation as Mg di positive aqueous plus 2 times OH negative aqueous. This is how it will dissociate, correct? Now, if its solubility is S, this is going to be S, this is going to be 2 times S, correct? Now, dear students, if I write the expression of KSP expression is going to be concentration of Mg di positive raised power stoichiometric coefficient 1, concentration of OH negative raised power stoichiometric coefficient 2. If I want to write the KSP expression, it's going to be equal to Mg di positive concentration, that's S, OH negative concentration, that is 2S, raised power 2 comes out to be finally 4S cube. So from here, you can write S is equal to KSP divided by 4 whole raised to the power what? Whole raised power 1 by 3. Now, KSP value is given to us. 3.2 into 10 raised power minus 14 divided by 4 whole raised power what? Whole raised power 1 by 3. So it's going to be 0.8 into 10 raised power minus 14, which is going to be 8 into 10 raised power minus 15. Whole raised power what? 1 by 3. So the value comes out to be 2 into 10 raised power minus 5. And since it's solubility, its units are going to be moles per liter. I hope it's also clear to everyone. Yeah? Clear? Is that clear, guys? Let's try to do one more question. First, let me know in the chats if everything is clear. Let me know first in the chats if everything is clear. Quickly guys in the chats. Like, can you all see me properly? All right. Perfect. Calculate the solubility of mercurous chloride, Hg2Cl2. First of all, do remember it's a special case. How it undergoes dissociation? It undergoes dissociation as Hg2 dye positive, 2Cl negative. It undergoes dissociation as Hg2 dye positive and 2Cl negative. Let's assume its solubility is S. Let's assume its solubility is S. Its concentration is going to be S. Its concentration is going to be 2 times S. Why? Because the stoichiometric coefficient here is 1, here it's 2. Now you just have to write the KSP expression. Rest everything is same. It is just do remember how it undergoes dissociation. That's important. Hg2 dye positive, 2Cl negative. Right? Now guys, KSP. KSP, how you guys are going to write? Hg2 dye positive, concentration. Concentration of Hg2 dye positive, which is basically S, raised power stoichiometric coefficient. Concentration of Cl negative, which is 2S, raised power stoichiometric coefficient. So KSP is going to be equal to 4 S ka cube, right? So S is going to be equal to KSP divided by 4 whole raised power what? Whole raised power 1 by 3. Now KSP value is given to me 10.8 into 10 raised power minus 23 divided by 4. Correct? It's going to be 4 2s are 8, 2.7 into 10 raised power minus 23 whole raised power 1 by 3 already is there, right? Now it's a bit of calculation. It will be 27 into 10 raised power minus 24. 27 into 10 raised power minus 24 whole raised power 1 by 3. So it's going to be 3 into 10 raised power minus 8 moles per liter. This is going to be the solubility which you are supposed to calculate, right? Clear to everyone? I hope this is super clear to everyone. Done? All right, so with this, your chemical equilibrium as well as ionic equilibrium is done and dusted. Now, which chapter do you want me to start? Tell me in the chats, everyone. Everyone in the chats, which chapter do you want me to start? Yes, these are all PYQs. We are done with chemical and ionic equilibrium. Which chapter should be the next now? Quickly, everyone. Which chapter should be the next? So majority is coming up with thermodynamics. So let's start with the thermodynamics only. Yeah. You want me to teach the thermodynamics in detail, or should I do the important topics of the chapter thermodynamics? Important topics, I mean. How do you want it? Important or detailed? Quickly. Chalo, I'll see then. I'll see. Wherever I'll feel to elaborate more, I'll do there. whatever topic I feel is least important, I'll give less time for that. Yeah, that's cool then. Okay, have you studied thermodynamics before? Say yes or no in the chats. Have you done this chapter before? Guess who is there again, yaar? Wait, let me open the door once, huh? Then we'll start the thermodynamics.
मैं फिर आ गई. सर. अच्छा एक मिनट.
रुको सब साथ में देंगे यार.
This is
नहीं,
collective
नहीं,
gift.
नहीं,
Collective gift.
ऐसे थोड़ी देखते हैं.
Happy birthday.
रुको फोटो please.
Happy birthday.
Click the pic. A gift for you.
No, it seems. No, Amika.
It's not my birthday, guys.
चलो. So please
Acha,
accept it.
From the
Psycho
core.
teacher.
They are not going to leave you now.
Please, I'm not at all psycho. I'm so smart, intelligent.
Students, do they know what has happened before?
That prank, na, they
Yeah,
know that.
prank,
See,
acha.
again, we brought some fruits. Now
No.
it's perfectly fine.
Yeah. So this is also very important, guys. You also should keep eating, and you should keep studying, and you should tag us on Instagram when you eat, watch. And I also want to know how
Dekha, it's
our
fine now.
students.
Let's do one thing. Just try to find out.
अरे छोड़ो ना, अभी
अरे
खाने दो
chemical
ना यार.
formula मत
Wait,
बोलो
wait,
यार.
wait.
No,
Just
no.
try to find out how many types of fruits are there, and whatever the color is there.
अरे they are already exhausted. They cannot think of anything now.
Whatever the color is there, at least write down the name of chemical compounds having just like orange, potassium dichromate, yellow, potassium chromate. Then rest of the other colors, try to find out chemical compounds.
Papaya is good for
Biology चालू कर
digestion.
दो.
बैठ दो मिनट बैठ दो.
हाँ, then I'll start physics. Apple.
Guys, 2 minutes, huh?
Have something. Till then, I can ask few questions from them.
Yeah. Can we solve some
Okay.
questions?
Tell me one thing when it comes to the sodium potassium ATPase pump, whether the sodium will go in or the potassium will go. Tell me. You have to answer it.
Potassium will go.
Inside.
I don't know.
Potassium will go. Make a poll. No.
Orange, green, yellow.
You know, na, you told them about our fight, that we challenged each other for that number of subscriber. Don't you know?
What
going
were
to-
you expecting?
See, I was expecting yesterday it was 15.1,
Right.
15.2, and after
Today
my
it is
session it was 16 point something.
Right.
So he told me that he's going to get 17. He'll make our family 17k subscriber family.
Done. It's done. You lost. It's under 1 point. Why?
The number
you should
was-
at least check the phone and come, no?
The number was 18. The number was 18.
The number was 18. Okay.
The number was 18. The number was 18.
Oops. Hey, come on, guys. If you like Ambika ma'am, then you should make it 18k. Yeah.
If you like.
Ambika ma'am.
If you like HSP sir, then make it 19. If you like Stair sir,
Make it 25. If you like Wassim sir, make it 100.
Let me concentrate on food. HSB sir. Tamil kunjam.
Kunjam, do some
Terila.
Kunjam.
Tamil Terila.
So what I
अबे
can
मैं तो
say.
खाने देना यार.
So also number of types of fruits are like 1, 2, 3, 4, 5. Please.
Ancha.
I don't know
No,
anything.
I will. You just hold on.
Okay, I'll just hold it. Okay.
Anche, are, 20. Now I, 1, 2, 3, 4, 5, 6, 7, 8, 9.
चुप कर यार. मरवाओगे.
You are setting a lot of expectations.
Ah,
Then I don't know. I'll also have to learn new languages then. Yeah, and guys, see, we told for Ambika ma'am it is 18k, this k, that k for each one of us.
Bro.
But for the entire team, it should be 1 million.
25K.
Yes, for the entire team, it should be 1 million subscribers,
अभी तक
guys.
बस केमिकल इक्रम हो गया एनिकर हो गया
Exactly.
I took the session for 11 hours. We'll see. We'll see.
Oh, guys, by the way, tomorrow, do not forget my marathon at 11 o'clock.
प्रमोशन स्टार्टेड
Hey, come on, man.
That we have learned from you only, okay? We have learned it from you only.
Which other platform is better than coming over here? Wassim sir's class for promotions.
I was...
Okay, do one thing, sir. Vitamin A deficiency. Which disease?
Night blindness.
Now, what is another name of night blindness?
Tell them.
HSB sir
Nyctolepia. Am I right? Xerothalmia. Am I right? Okay, just let me know these fruits are having vitamin A or not.
I think they have.
Okay, just do let me know
2 minutes.
which vitamin is maximum in these fruits.
C.
Oh, great.
See, guys, did you notice something? Yesterday I was taking the class. I was calling them ki please bring some tea or coffee. And today, because I am not taking class, although I'm doing something else, right? I am bringing everything. See, girls are always the best.
No, I'll tell you.
Girls
the reason.
are always
I'll
the
tell you
best.
the reason behind that.
for my brother. What they are going to do with my brother?
Who is the brother? See, basically, students, the reason is very simple. If Ambika ma'am is there outside the studio, no, then lot of time pass will happen. And then we can easily spend our time. Our whole work-life balance is maintained. Now, when you're in the studio, how will our work-life balance happen?
Oh, he's so nice.
I'm
Do
not-
attend his session tomorrow.
Thank you. I was saying you are doing time pass.
Okay, just do let me know.
Girls bringing namak wali coffee.
Some people used to have this what to say
Pineapple?
papaya when they are cooking meat, and they are not increasing too much temperature, and they want to cook their meat, means mutton, in less time.
Babaji started.
What's the reason behind it?
Babaji started.
Salt.
guys ignore
He's our group papa. है ना? He's our group papa.
Exactly. Wassim sir studied in Chennai. Why he didn't learn Tamil? Answer that question, Wassim
And
sir.
see, they say you
Poor
were so
Wassim sir.
caring. You brought salt wali coffee. Salt wali coffee is good for throat. Okay.
पिलाऊंगा आज
मैंने पी भी थी. Ma'am, revenge video. You'll get it soon.
See-
Girls are always the caring one.
Everybody is doing pak. Wassim sir aram se is
I'll
eating
eat.
fruits.
I'll eat.
So carry on
Yeah. Continue the
Chalo,
marathon.
I'll teach them thermodynamics. Do you know the first law of thermodynamics?
Do you know what is there before first law? Ma'am, first law is not the first law of thermodynamics.
Okay, fine. Thank you so much. Tata, bye bye.
Are she's not believing?
seriously
That I know. I
what's
just
before
forgot.
it?
I don't know.
what
is
comes before 1
Zero. Zero.
Zero thought.
Okay,
Zero.
which law came first? Zeroth law or first law?
बोलो
Tell them it is first, then zeroth was wanted on, then.
It is was then and the zeroth was, they discovered
What
it.
kind of
and
numbering system? 1, 0, then 2.
They were fool.
They are fools.
And now you tell me, what about the photo system 1 and 2? Which came first?
1.
One, but it is not
I
like
have
that.
got one question. I have got one question.
Okay, now I'm scared.
Green leaves,
Huh.
they have chlorophyll.
Huh.
C55, H72, O4, O5 and 4 Mg. Now 6 times CO2 plus 6 times H2 in the presence of sunlight and chlorophyll, they are preparing food C6H12O6, and they releases fresh oxygen 6O2. Now this this is coming out from CO2 or water. Hillman took 56 years. To prove this. Who is going to give oxygen, CO2 or water? Just this is the question.
He's on my side today. Finally.
No, I didn't understand the point.
6 times CO2.
I know that I know. But what are you supporting her?
No, I don't know.
Acha.
Hey kids, my question is okay or not? Oh, they have started giving the answer.
Wow.
H2O.
See, our
they're
kids
my
took only 1
students.
second.
Wow.
Hey, what is this 1.9k likes? Yeah, come on.
Yeah.
Only then we'll leave.
After all, they are students of Ambika ma'am. That's why they have given the correct answer.
Yes,
Oh,
yes,
great,
yes,
great.
yes.
She teaches them psychology, you know.
Physiology. That is physiology.
Psycho.
He was saying that.
Now, once I was see kids, see. Once I was having cold drink, and I told that man, this is having CO2, and CO2 is not good for health. Then that shopkeeper, what he has given the answer, very good answer. He said, sir, it is having only 1 atom of carbon, but still 2 atoms of oxygen, and oxygen is good for health.
Mind blown. Mind blown. Mind blown. Mind blown.
In CO2 there is only 1 atom of carbon but 2 atoms of oxygen. That was the reply of the shopkeeper. It's good for health.
Ma'am, I can draw better.
चलो बस हो गया.
Okay.
Hey, then likes have not gone till 2k. We are not going.
Niklo. Niklo.
Poda.
Okay kids.
Poda.
No, po.
Poda means go.
Po means jao and poda means
निकलो.
हाँ wait.
ये क्या? I'm Wassim.
Bye.
Bye.
Bye. Bye. फिर मिलेंगे. Bye.
Bye. Ambika ma'am, see you never. Sorry. Where is the marker? I love it.
Is there?
This is digital board.
Oh, you know. My God. Guys, am I audible? I mean, videoable. I was about to say videoable. Huh? All clear? All clear, guys? Say yes or no in the chats quickly. Now we are going to start the thermodynamics, yeah? Quickly, let me know in the chats with the thumbs ups. Ready for thermodynamics? Exactly, I was enjoying eating. I just wanted them to talk, huh? That's why I was sitting silent. Perfect, guys. So let's get going. Let's get started with the thermodynamics. All right, just a second. The first topic which we are going to deal with in thermodynamics, what is that? That's extensive and intensive properties. Let's have a look first of all what the extensive and intensive properties are all about. See, guys. If I particularly talk about the extensive properties, these are the properties of the system whose value changes on changing the size or amount of substance, present in the system. What is meant by that? Let's have a look properly and let's see what it exactly means. Extensive properties are those properties basically whose value changes on changing the size or amount of substance present in the system. For example, I have got an object. Let's say this is the object. this object, this complete object is my system right now. It is under thermodynamic investigation. I'm assuming this object which I have taken over here, right? This object is my system. It is under investigation. I'm investigating this object and I'm assuming the mass of this object is capital M, volume is capital V, temperature is capital T. Okay. Now what exactly I'm going to do? I'll divide this object into two parts. I divided this particular object into two parts. Now my reference is only this part. Now I'm investigating only this shaded part. If I'm investigating only this shaded part, can you let me know what will be the mass of this shaded part? It's going to be M or M by 2? It is going to be M by 2. Is its volume going to be V or V by 2? It's going to be V by 2. Is its temperature going to be T or T by 2? Its temperature is still going to be T, right? So my dear students, when the size of the object was bigger, the mass of the object was M, volume was V, temperature T. Now I have changed the size of the object. On changing the size of the object, is the mass remaining the same or the mass is changing? The mass of the object is changing from M to M by 2. Volume is changing from V to V by 2. Temperature is remaining the same. Any such property of the system whose value changes on changing the size of the system, on changing the amount of substance present in the system, what do you call that? You call that as the extensive property. So I would say the value of mass changed from M to M by 2, volume changed from V to V by 2, temperature did not change. Any such property whose value changes, that's what you call as extensive property. So mass is extensive, volume is extensive, temperature, it did not change, so it's going to be intensive. I hope you got the idea of what are extensive and intensive properties, right? Those properties whose value change on changing the size, those are extensive. Those properties whose value do not change on changing the size, those are intensive. Number one. Number two, there are few important features related to these extensive and intensive properties, right? Few important features which are related to these extensive and intensive properties. But before that, few examples are there which you need to remember about extensive and intensive properties. Anything can be asked. Extensive properties mein mass comes, volume comes, number of moles, heat capacity, internal energy, enthalpy, entropy, Gibbs-Free energy. All these terms we have to discuss in detail in this chapter, right? Mass, volume, number of moles, heat capacity, internal energy, enthalpy, entropy, Gibbs-Free energy, all these are extensive properties. Their value changes on changing the size of the system. Their value changes on changing the amount of substance present in the system. Now pressure, density, concentration terms, specific heat capacity, molar heat capacity, EMF, all these are basically the examples of the intensive properties. Their value does not change on changing the size of the system, right? Dear students, let's have a look on this property over here, that is pressure. There is something interesting which I'm going to tell you. For example, I'm taking a container. Let's say this is the container here. In this particular container, I'm keeping the ideal gas. This is the ideal gas in this particular container. I'm assuming the ideal gas which I'm taking in the container is my system. It is under thermodynamic investigation. It is under thermodynamic investigation, this ideal gas. So this ideal gas is my system right now. I'm assuming the number of moles of ideal gas in the container are N. I'm assuming volume is V, temperature is T, and pressure, for example, is P. If this is the ideal gas in the container, then it has to follow the ideal gas equation. I'll say P is equal to nRT divided by V. The pressure of this particular ideal gas right now is equal to nRT divided by V. Now, dear students, let's do one thing. And what's something which we are going to do? Let's divide this container in two pieces in such a way that the moles of gas in the shaded part of the container now is N by 2. Let's say the volume of this shaded gas is V by 2 and its temperature is still T. Let's say its pressure is P dash. Okay, right? My dear students, can I say I'm changing basically the amount of substance present in the system? Initially, the whole gas in the container was under investigation. Now the whole gas is not under the investigation. Only this part is under investigation. Right? So, if I talk about this particular part, this particular gas, this shaded gas in the container, its pressure is P dash, volume V by 2, moles N by 2, temperature T. Since it's the ideal gas only, right? So this shaded gas, it has to follow the ideal gas equation. Pressure is P dash is equal to number of moles means N by 2 R T divided by. Instead of volume, you are going to write V by 2. So 2 got cancelled. So I must say P dash is equal to nRT divided by V. Now what can you conclude from here? Initially, the pressure of the system was nRT by V. Finally, this shaded part, its pressure is also nRT divided by V. So is the value of pressure changing on changing the size of the system? When you are changing the size of the system, when you are changing the amount of substance present in the system, is the value of pressure changing? Initially, it was nRT by V. Now also it's nRT by V. The pressure is not changing. So which property pressure is? Is it extensive or intensive? Which property is it extensive or intensive? It is definitely the intensive property, right? Now few parameters which you need to know about these extensive intensive properties. Understand. Dear students, the first important thing is extensive properties, these are basically additive in nature. When we talk about the extensive properties, these are additive in nature. You can add or subtract the extensive properties directly. You can add or subtract extensive properties directly, right? For example, M plus M, you can make it 2M, right? Perfect. Extensive properties, these are additive in nature. Intensive properties are non-additive. I'm writing whereas intensive properties are non-additive. Okay, number one. Number two, when you divide the two extensive properties, extensive property divided by extensive property, the new property that comes, that will be intensive in nature. When you divide two extensive properties, the new property that comes, that is intensive in nature. For example, you have got the object whose mass is m, the volume of the same object is v. Now mass is extensive, volume is extensive. Mass by volume is something which you call as density. So density has to be the intensive property. I hope you got it, right? So division of two extensive properties makes it intensive. Okay. Next point. Do remember, when an extensive property is expressed per unit mass or per unit mole or per unit volume the new property becomes intensive. What it means exactly? Let's have a look. What it means exactly? See, there is something called as heat capacity. Which I am representing with C. Heat capacity is the example of extensive property. Okay. Now, heat capacity per unit mass. This is something which we call as specific heat capacity. Heat capacity per unit mole, it's called as molar heat capacity. So extensive property, when expressed per unit mass, the new property which comes into play, it is always intensive. It is intensive in nature. Similarly, extensive property, when expressed per unit mole, the new property that comes into existence, that will be intensive in nature. Similarly, entropy, it is extensive in nature. Entropy per unit mole, that gives you the molar entropy. And this molar entropy is intensive. Entropy, it's extensive, but molar entropy is intensive, right? So do remember all these things. These are very simple things only, but these are important ones, right? Do have a look on these things as well. All right, now we are moving into the actual stuff. What is that? Let's have a look. State functions and path functions, I'm sure every one of you would have come across once, right? What are state functions? State functions, actually, they depend on the initial and final state of the system. State functions, they depend on, their value depends on the initial and final state of the system. They are path independent quantities basically. State functions are path independent, right? They are path independent. They only depend on the initial and final state of the system. Number one. Number two, what are the examples of the state functions? Okay, before talking about the examples of the state functions, let me tell you, we always calculate change in the value of state function. We always calculate change in the value of state function. Okay, we always calculate change. Right? We always calculate change in the value of state function, and that change in the value of state function is represented by delta SF, change in the state function, which is equal to final value of state function minus initial value of state function. Minus initial value of state function. This is again important. So state functions, their value only depends on the initial and final state, whereas if I talk about the path functions, I'm writing it over here. If I talk about the path functions, path functions are the ones which actually depends on, they also depend on initial and final state. They also depend on the initial and final state. But apart from initial final state, they are path dependent quantities as well. They are path dependent quantities as well. Their examples are very important. Examples of state functions are internal energy. You have got enthalpy. You have got Gibbs free energy. You have got entropy. These are all the examples of the state functions. When we talk about the path functions, the two general examples here are heat and work. These are the two general examples of the path functions. Okay? These are the two general examples of the path functions. There is one more important thing which I would want to tell you right now. What is that? See, for example, A is a state function. Let's say B is the path function. A is the state function and B is the path function, for example, right? If I multiply this A by D, this dA will be called as small change in state function. It's called as small change in state function. Okay. Similarly, B is a path function. If I multiply this B with D, I won't be calling it as small change in path function. This is something which I'll be calling as small amount of path function. This is called as small amount of path function, right? Now, dear students, if you integrate this dA, what do we get? We get delta A. Delta A is something which I call as large change in A. It is called as large change in A. Whereas, if I integrate this dB over here, we don't write it as delta B. We write it as capital B. And capital B is called as total change in B. Sorry, total amount of B. This is called as total amount of B. Do remember, this is just the complete basics which you must be knowing before starting, right? If it is clear, let me know once in the chats quickly. Now, from where exactly we are going to start? This was just the complete basics. Or let me tell you one more point. There is something called a cyclic process which we have to start after some time. Cyclic process is the one in which system returns to its initial state after going through a lot of steps. Whenever system returns to its initial state after going through a lot of steps, that process is called a cyclic process. For example, I started from point A. From point A, I'm going to point B. From B to C, then from C to A again, right? So, any such process in which system returns to its initial state after going through a lot of steps, we call that process as the cyclic process, right? In the cyclic process, I would say the initial state and final state is always same. In the cyclic process, I would say the initial state and final state is always same. If the initial and final state is same, the change in the value of state function, or let me tell you like this, if the initial state and final state of the system is same, I would say the initial value of state function and final value of state function will be also same, because state function only depends on initial and final state. It is path independent, right? So, if the initial and final value of state function is same, I must say change in the value of state function for a cyclic process, it's always what? It's always 0. Change in the value of a state function for a cyclic process, that's always 0. Do remember this thing as well. Well, I'm going to its details in some time, right? If I ask you delta U for a cyclic process, what should be your answer? For a cyclic process, delta U is 0. Delta U net for a cyclic process 0. Delta H net for a cyclic process is 0, right? Right? Delta G net for a cyclic process is 0. Basically, this internal energy, enthalpy, Gibbs free energy, these are all state functions. And we know change in the value of a state function for a cyclic process, that's always 0. I hope this is clear, right? I hope this is clear to everyone. Right? Now we are going to discuss about something important from where the chapter exactly starts, okay? From where the chapter exactly starts. Just a second. Okay. Now let's talk about something called as heat and work. From here we are going to start the chapter. Till now I was teaching you some basic stuff. This is also basic only, but this is something which is frequently used in the chapter. Heat and work. First of all, if I talk about heat, what is heat basically? Heat is defined basically as, it is the mode of transfer of energy. You know, heat is defined as the mode of transfer of energy. What is meant by that? Whenever exchange of energy between system and surroundings has to happen, whenever exchange of energy between system and surroundings has to happen, the exchange of energy between system and surroundings, it can happen via heat. So what is heat? It is just the mode of transfer of energy. Now, if you ask me why the heat flows, heat always flows due to temperature difference. Heat always flows due to temperature difference. And remember, heat always flows from higher temperature to lower temperature. This is something which you all must be knowing. Higher temperature to the lower temperature. Heat always flows from higher temperature to the lower temperature. There is one thing which is important about heat. What is that? That is the sign conventions. Do remember, when system absorbs heat, Q value is taken to be positive. When system releases heat, Q value is taken to be negative. These are two important things. When you see system absorbing heat, Q value take positive. When you see system releasing heat, Q value just take as negative. Okay. Similarly, if I talk about work, what is work? If I talk about work in general, what is work? Work is first of all represented by W. Asha, one more thing about heat. Heat is the example of what? Heat is the example of path function, right? That's something I told you already. Now, first of all, what is work? Work is again defined as, the mode of transfer of energy. Work is again defined as the mode of transfer of energy. Between what? Between system and surroundings. Between system and surroundings. Whenever the exchange of energy has to happen between system and surroundings, the exchange of energy can happen via work as well. Whenever exchange of energy has to happen between system and surroundings, this exchange of energy can happen via work as well, right? Something important about this work, do remember? First thing, in our syllabus, we have to discuss only the thermodynamics of ideal gases. We have to discuss only about the thermodynamics of ideal gases, okay? So whenever I talk about ideal gas, remember that ideal gas is something which will be my system. Matlab whenever I say I have got system, that means I have got ideal gas which is under thermodynamic investigation. Ideal gas which is under thermodynamic investigation. Okay. Now, dear students, whenever you see volume of system increasing, volume of ideal gas increasing, whenever you see volume of system increasing, increase in the volume of the system is something which you call as expansion. Whenever there is expansion, we always say work is done by the system. Work is done by the system. And as per sign conventions, W value is taken to be negative. W value is taken to be negative. Something which you need to remember. Whenever you see volume of the system increases, whenever you see volume of the system increasing, do remember expansion is taking place. Whenever there is expansion, we always say work is done by the system. W value is taken to be negative. Similarly, whenever you see volume of system decreasing, whenever you see decrease in the volume of the system, let me tell you, decrease in the volume of the system is something which you call as compression. Decrease in the volume of the system is something which you call as compression. And whenever there is compression, we always say work is done on the system. And whenever work is done on the system, W value is taken to be positive. Okay. Now, how do we calculate work basically? That's one more important point. How do we calculate work? Right? It's also simple. How do we calculate work basically? There is a general expression by means of which you can calculate work. Work is minus integral initial volume of the gas to final volume of the gas. This is P external multiplied by dV. Right? This is the general formula by means of which you can calculate work. You can calculate work. Right? But here you have to do a few modifications. See, basically, you have two types of, let me tell you have two types of processes which I'm going to discuss with you. One is called as a reversible process, one is called as irreversible process. In case of reversible processes, always you will find P gas almost equal to P external. In case of irreversible processes, you will always find external pressure to be constant. You will always find external pressure to be constant. This is something which you will find always. Now, in case of reversible processes, see, this is the general way by means of which you can calculate work. Now, in case of reversible processes, how do we calculate work? Minus integral V1 to V2. Instead of P external, you can write P gas multiplied by dV. This is how you calculate work done in case of reversible processes. But in case of irreversible processes, how do we calculate work? It is P external is constant, take it out. So it's minus P external, it's integral of dV. That's V, upper limit, lower limit. So it's going to be P delta V, V2 minus V1. So this is how you calculate work done in case of irreversible processes. This is something which you need to remember. This is something which you need to remember, okay? General form to calculate work. Work done in reversible processes, work done in irreversible processes. Now there is, for example, one simple question which I can ask you here. And what is that? Have a look. Identify in which processes work is done by the system and work is done on the system. Tell me quickly, what do you think? See guys, if you look at the first reaction, the reaction is taking place at STP. The reaction is taking place at STP. Okay? Reaction is taking place at STP. That means the reaction is taking place at constant pressure and temperature. And you know when pressure and temperature is constant, as per ideal gas equation, PV is equal to nRT. Now pressure and temperature is constant. I can say volume is directly proportional to moles. So if moles will be increasing, volume will be increasing. If moles will be decreasing, volume will be decreasing, right? Look at the first reaction. All the reactants products, they are in gaseous phase, right? Now on the reactant side, how many moles do you have? 7 plus 4, 11. On reactant side, we have got 11 moles. On product side, how many do we have? 6 plus 4, 10, right? So in the forward direction, are the moles increasing or decreasing? Moles are decreasing in the forward direction. In the backward direction, moles are increasing, right? Now, I have to see in this process whether work is done by the system or on the system. Now you check in the first process whether moles are increasing or decreasing. In the first process, moles are decreasing. If moles are decreasing, that means volume will be decreasing. Decrease in the volume of the system is something which you call as compression. Decrease in the volume of the system is something which you call as compression. Whenever there is compression, we always say work is done on the system. And whenever work is done on the system, W value is taken to be positive. So in the first case, the value of W is positive. Work is done on the system, right? Work is done on the system. Now look at the second case. Gas, liquid. So on reactant side, you have got gases. On product side, you have got liquid. On reactant side, you have got gas. On product side, you have got liquid. So when the reaction is happening, gas is getting converted into liquid. So gas is getting compressed basically. Gas is getting converted into liquid. So volume of the system will be again decreasing. Volume of the system will be decreasing. Decrease in the volume of the system is called as compression. Whenever there is compression, work is done on the system, and whenever work is done on the system, W value as per sign conventions is taken to be positive, right? Is taken to be positive. Is it clear? Yes? Is it clear, guys, till here? Look at the third case quickly. Solid to liquid. Solid to liquid. Solid to liquid. Solid is getting converted into liquid, right? But this is ice basically. It's ice. This is liquid water. This is ice, this is liquid water. You must be knowing, when we talk about ice, volume of ice is more than that of volume of liquid water, right? Due to special cage-like structure of ice. When this process happens, is the volume increasing or decreasing? Volume is decreasing. Volume is decreasing. Decrease in the volume is something which you call as compression. Whenever there is compression, work is done on the system, right? W ka sign is taken to be positive. Then you have got solid to gas. Solid to gas. Solid to gas, right? If solid to gas process is there, that means volume of the system increases. Increase in the volume of the system is called as expansion. Expansion, right? Whenever there is expansion, work is done by the system. And whenever work is done by the system, W value is taken to be negative. So in this particular case, W value is negative. Clear? Perfect. I hope this is clear to everyone. Now we are going to have a look on the units of energy. Do remember these units as well. They are useful while solving the questions. SI unit of energy is joule. CGS unit is erg. 1 joule is equal to 10 raised power 7 ergs. The other units of energy which we are going to use in this chapter, that's ATM liter, bar liter, calories, right? 1 ATM liter is equal to 101.3 joules, 1 bar liter is equal to 100 joules, 1 calorie is equal to 4.2 joules, 1 ATM liter is equal to 24.2 joules. This is something which you need to remember basically. These are all used while solving the questions. These are all solved by perfect. Is it clear to everyone quickly? Let me know in the chats with the thumbs up, people, quickly. Quickly, let me know in the chats with the thumbs ups if everything seems clear till here. Quickly, quickly. All clear? So do remember all this as well. This is something which is important. Huh? Perfect. Perfect, perfect. Now there is something called as internal energy. Internal energy is basically the total energy present in the system. The total energy present in the system is something which you call as internal energy, right? Yeah? Now, first of all, if I talk about internal energy, which is represented basically by U, or you can represent it with capital A. The internal energy, it is defined as the sum of all the possible energies. The sum of all the possible energies present in the system. The sum of all the possible energies present in the system. What that means exactly. First thing, you know, whenever I talk about system, I'll be either talking about the real gas into consideration, or I will be talking about the ideal gas into consideration. Those are the only two things which I'll be dealing with. Number one. Number two, for example, if I say I have a container which contains a real gas. This is the container which contains the real gas. These are the real gas molecules here. Okay. Now you must be knowing, between the real gas molecules there will be force of interaction. There will be force of interaction between the real gas molecules. Absolutely. And these real gas molecules will be definitely moving as well. Due to the force of interaction, these real gas molecules will be having some potential energy, and due to the moment, the molecules will be possessing the kinetic energy. So if you want one more way to define this, internal energy is basically the sum of kinetic and potential energy present in the system. As simple as that. It is a sum of kinetic and potential energy present in the system. Let me tell you, this potential energy, it arises due to the force of interaction between the molecules, and kinetic energy, it arises due to the motion. It arises due to the motion. As simple as that. Now, my dear students, if I talk about the ideal gas, let's say there is no real gas in the container. Let's say there is the ideal gas in the container. Let's assume there is the ideal gas in the container. We know the molecules of ideal gas, they do not have any interaction. They do not have any interaction between each other. If there is no interaction, there will be no potential energy at all. So in case of your ideal gas, whenever I'll be defining the internal energy, internal energy of an ideal gas, it's nothing. It is just the total kinetic energy present in the system, because potential energy in the system will be zero. Right? Yes? Simple and basic. Now, dear students, there are few more things which I would want you guys to remember. Internal energy, which is represented by U, it is basically a state function. It is a state function. Internal energy is a state function, number one. Number two, this internal energy, it is an extensive property. It is an extensive property as well. Intensive property, it's an extensive, internal energy is an extensive property as well. Okay. Whenever I talk about a cyclic process, in case of cyclic processes, delta U, internal energy change, is equal to 0. In case of cyclic process, internal energy change, delta U, has to be 0. Perfect. Now this particular internal energy, it is the function of volume and temperature for the real gases. But for the ideal gas, internal energy only depends on temperature. Okay. For the real gas, internal energy depends on two parameters, volume and temperature. But for the ideal gas, internal energy depends only on temperature. And what does it mean? It means whenever you have got the ideal gas present in the container, if you change the temperature of the ideal gas, then its internal energy will change. If you change the volume of ideal gas, its internal energy does not change. Okay, its internal energy does not change. Internal energy of an ideal gas depends only upon temperature. On changing the temperature, internal energy changes. Now, how do you calculate the change in the internal energy due to change in temperature? That is given by this result. Delta U is equal to N CV T2 minus T1. This is the result which you guys are going to follow from now onwards to calculate the internal energy change. To calculate the change in internal energy due to change in temperature of an ideal gas, basically. Right? So for example, Okay. So for example, let's assume this is the container, and in this container we have got the ideal gas. Let's say in this container we have got the ideal gas. I'm making the temperature of the gas to change from T1 to T2. I'm making the temperature of the gas to change from T1 to T2. That means definitely its internal energy will change. Its internal energy will change. Now I have to calculate the change in internal energy, delta U, due to change in temperature. It will be equal to NCV T2 minus T1. Do remember this particular result. It's important. You'll use this particular result afterwards. Okay? Change in internal energy due to change in temperature in case of ideal gas. Apart from that, for example, I'm writing a statement. Whenever an ideal gas undergoes isothermal process, whenever the ideal gas undergoes the isothermal process. In case of isothermal process, temperature of the system is kept constant. So I must say change in temperature is 0, and you know your delta U for the ideal gas, which is basically NCV delta T. Since if delta T is 0, that means delta U is 0 as well. That means delta U is 0 as well. Delta U is 0 as well. Okay? Whenever the ideal gas undergoes isothermal process, its temperature is constant, delta T is 0, that means delta U is 0 as well. Right? Similarly, when you talk about enthalpy in particular, enthalpy which is denoted by H first of all, right? In case of enthalpy, there are few parameters related like your internal energy. What is that? Say, in case of your enthalpy, it's first of all again the extensive property like your internal energy. It's extensive. It is a state function. It is a state function. For a cyclic process, delta H is 0. For a cyclic process, delta H is 0. For an ideal gas, right? For an ideal gas, or let me write it like this. On changing the temperature of ideal gas, enthalpy changes, which can be calculated as delta H is equal to NCP delta T. Let's say you have got the ideal gas whose temperature you are changing from T1 to T2. There will be change in its enthalpy as well. And that enthalpy change will be calculated by this particular result. Delta H is equal to NCP delta T. I want you guys to remember this as well. Okay? Delta H is equal to NCP delta T. In the similar way, an ideal gas undergoing isothermal process. Okay, isothermal process. That means temperature is kept constant. If temperature is constant, that means delta T is 0. If delta T is 0, so delta H automatically for the ideal gas becomes 0. So whenever an ideal gas undergoes isothermal process, its delta H is equal to 0. Done? I hope it's clear. I hope it's clear to everyone. Similarly, one mathematical statement of first law of thermodynamics, then we can do some questions. Okay? Let's have a mathematical statement of first law of thermodynamics. First law of thermodynamics. Its mathematical statement. Delta U is equal to Q plus W. Delta U is equal to Q plus W. Whenever you use this particular equation, you have to take care of the sign conventions, right? And sign conventions already I have given you. Right? So let's try to do certain questions so that you can understand how all these concepts are used basically. Just a second. Okay, one very common question which is frequently asked in your exams. Look at the question carefully. A system expands from 5 liter to 10 liters. A system expands from 5 liter to 10 liters. So initial volume of the system is basically 5 liter. Final volume of the system is kept as 10 liter. So the ideal gas undergoes expansion in volume. The ideal gas undergoes expansion in volume against a constant external pressure. External pressure is kept constant, which is kept as 2 atm, right? So first of all, it is mentioned that the external pressure is kept constant, and you must be knowing when the external pressure is kept constant, the process is taken as irreversible. So it is basically the irreversible expansion which is happening for the gas. If it absorbs 800 joules of heat, Q value has to be taken as plus 800 because system is absorbing 800 joules of heat. What do I need to calculate? I need to calculate the value of delta U. I need to calculate the value of delta U, right? I need to calculate the value of delta U. You must be knowing your delta U is equal to Q plus W, right? So in order to calculate delta U, we should have Q as well as W. Q value already we have, W we have to calculate. The process is irreversible in nature. So W irreversible first of all will be calculating. W irreversible will be calculating minus P external, V2 minus V1, right? So minus P external is given to us as how much? P external is given to us as 2 atm. V2 minus V1. Final volume minus initial volume. That will be 5. So the value comes out to be minus 10, but the units now are going to be atm liter. Now let's take it in joules. 1 atm liter is 101.3 joules. The value comes out to be minus 1013 joules. This is the value of delta U, sorry, W. So delta U has to be equal to Q. Q is 800 joules. W is minus 1013 joules. The answer is going to be minus 213 joules. So delta U, which you were supposed to calculate, is minus 213 joules, right? Perfect. Perfect. So till now, we are done with solid state, we are done with electrochemistry, we are done with chemical kinetics, we are done with chemical equilibrium, ionic equilibrium. Thermodynamics is going on, right? Mole we have done, right? Are we done with mole? Mole, atomic, are we done with them? Just let me know. Are we done with mole, atomic, redox? Are we done with mole, atomic, redox? I think yes, I have taught you, right? Yeah, in the final lab series, I'm telling you. Final lab series, I have taught that. Is that? I think you have not seen the final lab series. So in the final lab series, what all chapters are done? Mole, atomic, and stoichiometry. Huh? All right, all right. Okay. So this question is done. This question is done. Now guys, let's have a look on one more. Something important which you must be remembering from now onwards. Okay? Whenever in a question they ask you about the heat exchange, whenever in a question they asked you about the heat exchange means if they ask you, calculate the amount of heat absorbed or amount of heat released by the system, something like that. Calculate the amount of heat absorbed or amount of heat released by the system. If they ask something like that, how you guys are going to calculate it? See, I'm writing two things here. One is QV, one is QP. QV is something which you call as heat absorbed or released. Heat absorbed or released by the system. Heat absorbed or released by the system at constant volume. At constant volume. Whenever they ask you to calculate the amount of heat absorbed or released by the system at constant volume, remember at that point of time you will have to calculate the value of delta U. Remember at that point of time you'll have to calculate the value of delta U. Just a second, guys. So what I'm telling you, whenever they ask you to calculate the amount of heat absorbed or released by the system at constant volume, remember they are indirectly asking you to calculate the value of delta U. And delta U for the ideal gas you already know, that's NCV T2 minus T1. That's NCV T2 minus T1. Okay. Whenever they ask you to calculate the heat absorbed or released by the system at constant pressure. So indirectly they are asking you to calculate the value of delta H, and delta H you know, that is NCP T2 minus T1. Remember this particular result as well. From these two results, two questions will be asked. Right? Perfect. And dear students, one thing which you must be knowing before doing the questions, one thing which you must be knowing. What is that? See. Oh my God. Just a second, guys. All right. So basically, I gave you two results. One is to calculate delta U. One is to calculate delta H. Now here are some terms. As you can see, CV and CP. You must be knowing CP and CV values for different types of gases. First of all, if I talk about the monoatomic gas, like helium, like neon, like argon, these are the monoatomic gases. For the monoatomic gases, CV value, that's equal to 3 by 2R. CP value, that's equal to 5 by 2R. And gamma value, gamma is basically CP upon CV, that will be equal to what? That will be equal to 5 by 3, which will be 1.66. Okay. Similar, this is first type of gas, that is the monoatomic gas. Number 2, we have got diatomic gases as well. Diatomic gas like O2, or we have got triatomic linear gases. Triatomic linear, like carbon dioxide. Like carbon dioxide. Carbon dioxide is first of all triatomic, at the same time it's linear as well. Okay. Let me tell you, for diatomic gases or triatomic linear gases, CV value is 5 by 2R, CP value is 7 by 2R, and its gamma value is 7 by 5, and 7 by 5 is nothing, it's just 1.4. Similarly, if I have triatomic non-linear gas, like SO2. In case of SO2, the CV value is 3R, CP value is 4R, and the value of gamma, that's 4 by 3, or you can make it as 1.33. One thing which you can notice over here, what is that? One thing which you can notice over here, first I took the monoatomic gas, then I took the diatomic, then I took the triatomic. As I move from top to bottom, is the atomicity of gas increasing or decreasing? Atomicity of the gas is increasing. on moving from top to the bottom, atomicity of the gas is increasing. Is the value of gamma increasing or decreasing? Value of gamma is decreasing. So you can generalize a statement here as the atomicity of gas increases, the gamma value decreases. The gamma value decreases. Few more important results, then we'll be solving the questions. You know, Cp minus Cv is equal to R for 1 mole of ideal gas. For 1 mole of ideal gas, Cp minus Cv is equal to N times R for N moles of ideal gas. You must be knowing. Whenever I want to define gamma, gamma is nothing, it is Cp upon Cv, right? Similarly, Cv is equal to R divided by gamma minus 1 as well. These are few important results which I would want you all to take a note of before doing the questions. Okay? Before doing the questions. Let's try to solve certain questions now. Let's try to solve certain questions. Look at this particular question. Will you be able to solve this question? What do you think? Will you be able to solve this question quickly? Will you be able to solve this question? Calculate delta U and delta H when 10 decimeter cube of helium at STP is heated to 100 degrees centigrade, assuming ideal gas behavior. It's a simpler one. It's not difficult. See guys how it's to be done. See, as per the question is concerned, we have taken 10 decimeter cube of helium. Helium is first of all a monoatomic gas. So its Cv you must be knowing, that's 3 divided by 2R. Its Cp you all must be knowing, that's 5 by 2R. Correct? Now first of all, 10 decimeter cube of helium means 10 liters of helium. So basically we have got 10 liters of helium. And these 10 liters of helium are kept at STP. That means temperature of this helium, which I am representing with T1, it's kept as 0 degree centigrade, 273 Kelvin. Pressure of this helium is kept as 1 bar, or you can say 1 atm. So 10 liters of helium is kept at STP. As per the question, 10 liters of helium is kept at STP. Now as per the question, you are changing the temperature, you are heating this gas. You are heating this gas till 100 degree. Initial temperature was 0 degree. Now the final temperature of the gas is 100 degree. 373 Kelvin. I need to calculate delta U and delta H for the gas, right? Since we know when the temperature of the ideal gas changes, its internal energy automatically changes, right? Even enthalpy changes. Now that enthalpy change, that internal energy change, how do we calculate that? It's simple. See, first of all, how many moles of gas we have? Given volume of the gas in liters divided by 22.4. So these many moles of gas we have. These many moles of gas we have, number one, right? These many moles of gas we have, right? Now dear students, have a look. What do we need to calculate delta U? What is delta U? Delta U is nothing, that's NCV T2 minus T1. Now understand whether all the terms are given to you or not. N value is 10 divided by 22.4. CV value, that's 3 divided by 2R. T2 minus T1. T2 is 373, T1 is 273. So 373 minus 273, the value comes out to be 100, right? Okay, the value comes out to be 100. Perfect. Now you need to just put the values over here. So it's going to be 10 divided by 22.4 multiplied by 3 by 2. R value is nothing, it is 8.314 joules per Kelvin per mole multiplied by 100. Solve this equation and get the answer of delta U in joules. Similarly, you can easily calculate delta H as well. Delta H is nothing, that's NCP T2 minus T1. N value you know, Cp value you know, T1, T2, everything, all the parameters you have, you can easily, right? Perfect. Who is this Rumasa Bashir? What kind of acting did I did, madam? Is it clear? Quickly let me know in the chats if everything is clear. All right. Perfect. There is one more important topic, that is one more very important topic. What is that? That is the relation between delta H and delta U. A lot of questions are asked from this. A relation between delta H and delta U. Questions have been frequently asked from this particular topic. Okay? A relation between delta H and delta U. What kind of questions and how we are going to solve them? Let's have a look. First of all, the general relation between delta H and delta U, that's given like this. Delta H is equal to delta U plus delta of PV. This is the general relation between enthalpy change and internal energy change. Number one. Number two, now we have to do certain modifications. If pressure of the gas is kept constant, then I can say delta H is equal to delta U plus, take P out, it's going to be P, then it's going to be delta V. P delta V. This is going to be the relation between delta H and delta U when pressure of the system is kept constant. In the similar way, if volume of the system is kept constant, take V out of this delta, you can say delta H is equal to delta U plus V delta P. Change in pressure means P2 minus P1. This is the equation which we'll be using when volume of the system is kept constant, right? In the similar way, if pressure and volume both will be changing, then what is the equation which I'll be using? Delta H is equal to delta U plus, it's going to be P2 V2 minus P1 V1. This is one more equation which we'll be using when pressure and volume both will be changing. And my dear students, at the same time, for a gaseous phase reaction, carried out at constant temperature, do remember delta H is equal to delta U plus delta Ng RT. And already we have seen in equilibrium how to calculate delta Ng. Okay. Now let's try to utilize all these equations and let's see exactly what kind of questions can be asked. Okay. Just a second. The first question which is on your screen. Look at the question carefully and think how to solve it. Let me know in the chats. What do you think? What do you think? Quickly. Clear? Anyone done with this? Anyone done with this? All right, let's see exactly how this sort of equation is to be solved. See guys, as far as this particular equation is concerned, 1 mole of ideal gas, 1 mole of ideal gas undergoes a change in state, from 2 atm, 3 liters to 2 atm, 7 liters. So basically, the initial pressure of the gas is given as 2 atm, the initial volume is given as 3 liters. The final pressure of the gas is given as 2 atm, the final volume of the gas is given as 7 liters, right? So we have taken a gas basically, right? And we are not changing the pressure of the gas. It is just we are changing the volume of the gas. During the change in volume, it is mentioned that the internal energy of the gas, we have taken 1 mole of gas which undergoes a change in state with the change in internal energy delta U of 30 atm liter. 30 atm liter. What do I need to calculate? I need to calculate delta H. Delta H needs to be calculated. Now, my dear students, one important thing. Since no doubt we are changing the state of the system, but we are making sure pressure remains constant. So, pressure is kept constant, delta H is equal to delta U plus P, it's going to be delta V, which is V2 minus V1, right? Now, delta H we need to calculate is equal to, delta U is equal to 30 atm liter plus P is 2 atm, V2 minus V1, 7 minus 3 comes out to be 4. The value will be 38 atm liter. This is the value of what? This is the value of delta H which we were supposed to calculate, right? Perfect. This is the value of delta H which we were supposed to calculate. This is the first type of question that can be asked from delta H and delta U relation. Let's see a few more. Look at this question. Let's see what is asked in the question. Which of the following is correct for the following exothermic reaction? First, it's mentioned that the reaction is exothermic. In case of exothermic reactions, heat is released by the system. And whenever heat is released by the system, Q value is taken as negative. So this cannot be the answer. It is mentioned here that Q is positive, but we know in case of exothermic reactions, heat is released, and when heat is released by the system, Q value is taken to be negative, right? But over here it's mentioned that Q is positive, so this cannot be the answer. Number 1. Number 2, the reaction is carried out at constant pressure and temperature. The reaction is carried out at constant pressure and temperature. Now, as per ideal gas equation, PV is equal to nRT. If pressure temperature is constant, I can say volume is directly proportional to moles. Volume is directly proportional to moles. Now, you tell me, during the reaction, are the moles increasing or decreasing? See, this is 1, this is 3. 3 plus 1 comes out to be 4. So, on the reactant side, you have got 4 moles. On the reactant side, you have got 4 moles. What about the product side? Product side is 1 plus 1. Product side, we have got 2 moles. So, during the process, are the moles increasing or decreasing? Moles are decreasing. And if moles are decreasing, that means volume of the system will be decreasing. Decrease in the volume of the system is what you call as compression. Whenever there is compression, work is done on the system, and W value, as per sign conventions, is taken to be positive. But here they have mentioned that W is negative. So, this cannot be the answer. This cannot be the answer. Now, the answer is either 1 or 2. Okay. Now, people, if you look at this particular reaction carefully, calculate delta Ng for the reaction. Number of moles of gaseous products, 1 plus 1, 2, minus. Number of moles of gaseous reactants, 3 plus 1, 4. The value comes out to be minus 2. So, delta Ng is minus 2. If delta Ng is minus 2, we know delta H is equal to delta U plus delta Ng, and this is R, this is T. So, I can say delta H is equal to delta U plus delta Ng is minus 2, and this is R, this is T. So, you can say delta U is equal to delta H plus 2RT. From this particular equation, what all things you can analyze? You can analyze the value of delta U is greater than the value of delta H. Delta U is greater than delta H. By how much amount? By this much of amount. Delta U is greater than delta H. So, this is the correct option. That means it automatically became the incorrect one. Right? So, all these types of questions you should be able to solve, right? Clear? All clear? All clear, guys? I hope this is properly understood. Let's have a look on one more similar type of question. Calculate delta U when 2 moles of liquid water vaporizes at 100 degrees centigrade. So as per the question, we are vaporizing H2O liquid. We are converting H2O liquid into H2O gas. This is something which we are doing, right? So how many moles of gas we have? How many moles of liquid water we have? We are given with 2 moles of liquid water. Temperature 100 degrees centigrade, 373 Kelvin. The enthalpy of vaporization, delta H. Delta H for vaporization is given 40.66 kilojoules per mole. What are we supposed to calculate? Delta U. Delta U is to be calculated. Look at it carefully. See what is asked in the question. As far as this particular question is concerned, H2O liquid, we are converting into H2O gas. Okay. During the process, delta H value is given 40.66. What are we supposed to calculate? Delta U. Okay. There is one relation which you already know. Delta H is equal to delta U plus delta NGRT. Now, first of all, if I ask you for this particular reaction, what is the value of delta Ng? It's simple. Delta Ng is equal to number of moles of gaseous products, that's 1, minus number of moles of gaseous reactant, that's 0. So, delta Ng is 1. So, first thing, I can say delta U is equal to delta H minus delta Ng, and this is R, this is T. Now, first of all, let's calculate delta U. Let's calculate delta U. Delta U, let's try to calculate in kilojoules. In kilojoules is equal to delta H. Delta H is given to us 40.66 kilojoules, right? Minus delta Ng, that's 1. R value 8.314 joules per Kelvin per mole. Temperature 373 Kelvin. I'll be dividing it with 1000. Then only this term also comes out in kilojoules. When you solve this particular term, you'll be getting the value of delta U, right? When you solve this particular equation, you will be getting the value of delta U, and the value of delta U you'll be getting as 37.5 kilojoules. But dear students, this 35.5 kilojoules, it's not going to be the answer of the question. Why is that? Why is that? Why is that? Because this is the value of delta U. This is the value of delta U for the vaporization of 1 mole of liquid water. But as per the question, we have to vaporize 2 moles of liquid water. So, I would say for the vaporization of 1 mole of liquid water, delta U is this much. So, for the vaporization of 2 moles of liquid water, I would say delta U has to be 37.5 multiplied by 2. The value has to be 75.1 kilojoules. Look at the options. Option B, which is the correct answer of the question. Is it clear? Is it clear, people? Right? All perfect? R value I have taken as 8.314. Perfect? All right, let's move on. Let's move on. Let's have a look on different types of processes now. All right, I'll give you a break at 7. Okay, no issues. Break at 7. Okay, cool. Okay, let's talk about isochoric processes. As the name indicates, isochoric means I'm keeping the volume of the system constant. I'm not letting the volume of the system to change. If volume is constant, delta V, change in volume is 0. If delta V is 0, W, work done is equal to 0, right? This is something which is understood, which all of you must be knowing already. During the isochoric processes, W value is equal to 0. Work done is equal to 0. Yeah. Now at the same time, if you want to plot a graph between pressure and volume for the isochoric processes, now volume is constant. That means the graph will be like this, straight line. And this particular graph is something which you call as isochore. Volume has to be constant. And you must be knowing area under the curve. Area under the curve. That gives you the magnitude of work. There is no area under this curve over here, right? That means directly you can say W value is equal to 0, right? Nothing else you have to do in case of what? In case of your isochoric processes. If you talk about the first law of thermodynamics, delta U is equal to Q plus W. In case of isochoric process, W value is 0. So you can say Q and you can write V over here as a subscript. QV is equal to delta U. So from this relation also, QV is equal to delta U, something which I told you already before. QV is equal to delta U, right? Heat absorbed or released by the system at constant volume is equal to internal energy change. And for the ideal gas, it's equal to NCV delta T. This is something already which I told you, right? This is something which I already told you. You should be remembering this as well. Similarly, if I talk about the isobaric process, then we'll be doing some questions. In case of isobaric processes, what happens? In case of isobaric process, pressure of the system is kept constant. So delta P, change in pressure, is equal to 0. So if you want to write the first law of thermodynamics, delta U is equal to Q plus W. But here I'm writing QP plus W, right? Delta U is equal to QP plus W because I'm using the term constant pressure. So I can say delta U is equal to, it's going to be QP, W is equal to minus P delta V, which is going to be P V2 minus V1. V2 minus V1, or you can say delta U is equal to QP minus PV2 plus PV1, right? Or you can just keep it like this, just a second. You can just keep it like this, QP minus P delta V, right? Or you can say QP is equal to delta U plus P delta V, and delta U plus P delta V, you already know that's delta H. And this is something, that's something which I already told you. And delta H for the ideal gas, that's NCP delta T. Perfect. All these things we have discussed. Yeah? Okay? Okay, one more thing. That's something which you all must have studied, open vessel concept. In case of open vessel concept, whenever any reaction takes place in open vessel, right? In case of open vessel concept, we always take pressure of the system as constant, right? And if pressure is constant, then we have to consider it as an isobaric process. And how do we calculate work done? Work done in case of open vessel. In open container, whenever in a question it's mentioned that a reaction is taking place in an open container, you will be using this particular result to calculate the value of W. Okay? Whenever it's mentioned that a reaction is taking place in an open container, this is the expression which you guys will be using to calculate the value of W. Let's try to solve certain questions and let's have a look how these sort of questions are to be solved. The first question on the screen. The first question, can you give it a try? Can you give it a try? Can you give it a try quickly? पानी चाहिए मुझे. Done? Let's see exactly how this sort of equation is to be solved. See guys, first of all, the reaction that's given to us, I would want you guys to calculate delta Ng for this reaction is equal to, just a second, delta Ng is equal to, just you give it a try, you see what is the value of delta Ng which you will be getting in this question. Just see, तो चाय गिर गई Here. तुम लोग का हो गया रिकॉर्डिंग वगैरह सब?
नहीं, there is no pen, no camera.
So what are you waiting for?
I'm just looking for a pen. Any pen.
Okay, did you calculate delta Ng for this? Delta Ng is going to be number of moles of gaseous products, which is 3 by 2, minus number of moles of gaseous reactant, which is nothing. So delta Ng I got 3 by 2. Let's calculate work W. W I told you already to calculate minus delta Ng RT. So W is equal to minus delta Ng value is 3 by 2. R value taken calories. Temperature must be given to me 300. Okay, 2 got cancelled. The value of W over here came out to be minus 900 calories. So W value is equal to minus 900 calories. Okay. So are we supposed to calculate only W? No. W, delta U, delta H. Okay. Since 95 calories of heat is released during the process. This particular process, first of all, it is happening in an open vessel, right? It is happening in an open container. So pressure is kept constant, right? And 95 calories of heat is released at constant pressure. Heat released at constant pressure is represented by QP, which will be taken as minus 95 calories, minus because heat is released. And QP, you already know that's delta H. So basically delta H is given. Basically delta H is given as per the question, which is minus 95 calories. Delta H is equal to minus 95 calories. Since you got delta U, sorry, you got delta H, you got W. What else do you need? You need delta U. As per first law, delta U is equal to Q plus W. Since it's constant pressure process, so you can write QP. So delta U you can calculate from here as QP, which is minus 95, plus W, which is minus 900. The final result comes out to be minus 995 calories. These were the three things which were basically asked to calculate. Okay, perfect. Proper NEET standard questions these are, and I'm damn sure you can easily solve all of them. Yeah? Okay. Let's try to do one more question, or wait. Okay, this is the question let's try to do. Let's try to do this particular question. What do you think about this one? What do you think about this particular question? Calculate the work done in complete decomposition of 5 moles of PCl5. So basically we have got a reaction, PCl5 gas in equilibrium with PCl3 gas plus Cl2 gas. This is the reaction. Calculate the work done. First of all, calculate delta Ng. Number of moles of gaseous products, 1 plus 1, 2, minus. Number of moles of gaseous reactants, 1. So the value over here comes out to be 1. So delta Ng value is 1. Okay. Let's try to calculate W. W is equal to minus delta Ng RT. Okay. So minus times delta Ng is 1. R value taken calories, 2. Right. Temperature is given to me as 300 Kelvin. So the value of W comes out to be minus 600 calories. But this 600 calories, it's not going to be the answer of the question. It is not going to be the answer of the question. This minus 600 calories, it is the value of W. It is the value of W for the decomposition of 1 mole of PCl5. For the decomposition of 1 mole of PCl5, this is the value of W. But as per the question, are we doing the decomposition of 1 mole of PCl5 or 5 moles of PCl5? We have to do the decomposition of 5 moles of PCl5, right? So I would say, for the decomposition of 5 moles of PCl5, what will be the W? For the decomposition of 1 mole, W is minus 600. For the decomposition of 5 moles, it's going to be multiplied by 5. The value comes out to be minus 3000 calories. Right? Done, understood? Perfect. I'm sure it's clear. Perfect. Let's have a look on let's have a look on isothermal processes now. Isothermal processes. Isothermal processes. Okay. As far as this particular name is concerned, in case of isothermal processes, temperature is kept constant, number one. If temperature is constant, I can say change in temperature, delta T is 0. You know, delta U is equal, delta U for the ideal gas is equal to NCV delta T. If delta T is 0, I can say delta U is equal to 0 as well. Delta U is equal to 0. Perfect. Delta U is equal to 0. Now, if delta U is equal to 0, use the first law of thermodynamics. You know, if you talk about your first law of thermodynamics, delta U is equal to Q plus W. Absolutely. If delta U is 0, I must say Q will be equal to minus W. This is a particular relation which is valid only for the isothermal processes. This particular result is valid only for the ideal gas undergoing isothermal process. The ideal gas undergoing isothermal process, right? Okay. Now Q is equal to W. Q is equal to minus W. Let's see what all things we get out of it. First of all, W can have two values. Either W value can be negative or W value can be positive. Either W value can be negative or W value is positive. If the value of W is negative, negative makes it positive, that means Q value will be positive. If the value of W is positive, that means Q value will be negative, right? W positive, what does that mean? That means expansion. That means expansion. W positive, what does that mean? That means compression, right? Q positive, what does that mean? That means heat is absorbed. Heat is absorbed. Q negative, what does that mean? That means heat is released. That means heat is released. I can generalize over here two statements. During isothermal expansion of an ideal gas. During isothermal expansion of an ideal gas, what happens? Heat is absorbed by the system. Similarly, during isothermal compression of an ideal gas, heat is released by the system. So I can generalize these two statements. I can say during isothermal expansion of an ideal gas, heat is absorbed. During isothermal compression of an ideal gas, heat is released by the ideal gas. Mark these two statements, these are important, okay? Perfect. Mark these two statements, these are important. During isothermal expansion of an ideal gas, heat is absorbed by the system. During isothermal compression of the ideal gas, heat is released by the system. Mark these 2 points, these are very, very, very important. There are two results which you need to remember related to how do we calculate work done in reversible isothermal process and how do we calculate work done in irreversible isothermal process. This is the general expression by means of which you can calculate work done in reversible isothermal process, minus 2.303 nRT log of V2 by V1, or instead of V2 by V1 you can use P1 by P2 as well. This is one very important result which you need to remember for sure. Okay. This is how do you calculate the work done in case of what? In case of a reversible isothermal process. And in case of irreversible isothermal process, you can use this particular result directly. This result for irreversible isothermal, this for reversible isothermal, right? Let's try to solve one question so that you can understand when to use which equation. Okay, you have got a question on the screen. What do you think? Question on the screen. Calculate Q, W, delta U and delta H when 2 moles of an ideal gas. So as the question is concerned, we have got 2 moles of an ideal gas expanded reversibly and isothermally from 10 atm to 5 atm. From 10 atm to 5 atm. Okay, expanded reversibly and isothermally. That means the process is reversible isothermal. Correct? And you know, during isothermal process, whenever the ideal gas undergoes isothermal process, delta U as well as delta H both are equal to 0. Right? Delta U as well as delta H both are equal to 0, right? What are we supposed to calculate? We are supposed to calculate W. The process is reversible. It's going to be minus nRT ln of P1 divided by P2. This is the relation. Minus times N value, that's 2. Take the R value, for example, in calories, 2 calories. Temperature, 300 Kelvin. Ln of P1 by P2. P1 divided by P2. 10 divided by 5 is 2. Ln 2 is 0.7. So W value from here, you got to know as minus 840 calories. W calculated, delta U calculated, delta H calculated. Now what is left? Since you know delta U is 0. Delta U is basically Q plus W. That means Q plus W is 0. So Q will be equal to minus times W. So Q will be equal to minus times W is minus 840. So the value will be plus 840 calories. Is it clear? Is everything clear? Guys, I think I'll end the session right here because my head is paining like crazy. Okay. I think I'll end the session here only. चक्कर आ रहे हैं मुझे. I'll let you know about the schedule, okay? By the way, if you're not joined the Telegram yet, do join the Telegram, in which I'll keep you update about the upcoming schedule, okay? That's important. No, it's not about sleep. I think I did not have food, neither yesterday nor today. Okay then, I'll let you know in the evening about the rest of the schedule, or you tell me in the comment section like what do you want in different subjects, okay? Do tell me in the comment section what do you want the next, but I want everyone to write in the comments, not in the chats, in the comments. See, mole concept, atomic structure, states of matter, that's already I have taught in the final lab series, right? You can check it on this channel only. Final lab series, those 3 chapters were done. Thermodynamics, chemical equilibrium, ionic equilibrium is also done. Solid state, electrochemistry, kinetics is also done. So 9 chapters we did till now. Okay, so you tell me in the comment section now, like what do you want the next? I'll take a leave with this. I need to go to the doctor, I think. Okay, I'll let you know in the Telegram. You take care, okay? Bye, 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 bye. God bless you all.